There's no confrontation when fantasy makes you afraid. So much injustice, too many lies. Don't have to look very far, but nothing will change if we leave things the way that they are. If there's something you find to believe, don't you when you know what to do. fall. So you think you can tell heaven from hell, blue skies from pain. Yeah, you tell it to you, but what do you know? Miles in a veil.
Check.
Here we're just two lost souls swimming year after year, running out of pain. Same old feeling. Wish you were here.
So, waiting on the start of day slides, but we'll be there in just a minute. That looks suspiciously like the slides. So welcome to the third day of GUNI Radio Conference. Hopefully everybody's been enjoying the last two and is feeling up for another good day of talks, workshops. And then remember that we do have our dinner this evening. So if you're not burnt out on receptions yet, which I sure hope you aren't, we're over at the Arizona Heritage Center, just about a 10-minute drive north of here. And it should be a really good evening. And there is full food, drinks, and it's a great little venue. So indoors and outdoors. So you can hide in the shade or enjoy and bake in the heat. So I always get ahead of the slides, but we've correctly identified that it's Thursday. Yes, the heat. Please do hydrate, stay safe, drink water. And as I've found out, water is not sufficient. Water and salt and electrolytes, please. So yes, the Wi-Fi remains the same. If you registered on the first day, you probably need to re-register now. It is a 48-hour lease on the Wi-Fi. Same process, should just get you right back on. In terms of the highlights, we do have talks from 9 to 5, same as the other days. The expo hall is open from the AM break. Of course, it's more or less open now. So if you need a little break before the talks are done, you can head over. Our keynote speaker, I'll be introducing in just a minute. And then this morning before the AM break, we'll be going into a deep dive on the GR 4.0 architecture and the progress of the architecture team over the last year. So there's real content there that will hopefully get minds thinking and that we're looking for feedback on. We have 2 workshops today, Embedded SDR and IQ Engine. IQ Engine, if you haven't checked it out, you should Google that and find the domain and take a quick look at it. It's a really fun web interface for storing large data sets of signals. And Embedded SDR says it all in the name, but check out the workshop description for more details. The amateur radio exams are today from 1 o'clock till 5 o'clock. If you haven't started studying, it's not too late. Pretty much anybody in this room can probably pass the first level of exam with maybe an hour of preparation. It's really straightforward. And the higher levels are at will to take, take as many as you like. Please do pre-register if you haven't already. It's not too late, but you can do nice things like sign up on the FCC database and get an FCC ID so that you don't have to give your social security number. Always a nice little perk. Lightning talks, we do have some slots available. Wiley, if you're in the room, you have to let me know whether you wanted that slot. But we do have some slots today and tomorrow for any project, big or small. Stop by the registration desk for that. Speaker slides, same deal. We know you're continuing to work on them. I certainly was for my talk on Sunday night, but please do upload them in time for our wonderful AV team to have them prepared for you when you get up to the stage. The chat server remains the same, chat.gunuradio.org. We also have a Discord server. Sorry, I don't have a QR code for you to scan there, but you should be able to find us pretty easily. And that's the end of the slides there. Wonderful. So if we could roll over to the keynote slides, please, and I'll do a quick introduction. So Eric, if you want to come up, Eric Blossom founded the GNU Radio project as a piece of software in 2001, and he'll be telling us all about the early days. So I won't spoil how it went.
Okay.
But thank you very much.
Yeah. Well, thank you. Just give me a second. I can get my personal speaker notes up here that you won't see, but I'm going to try to tell something like this is one of those based on a true story kind of a things, maybe. Anyhow, it's just the first thing I want to say is it is so great to see all of you here and that the project is alive and well. We started it and I started it with the part of the story I want to tell is that there were always other people involved. And we're going to call out some of those key people along the way, but mostly I want to point to that it's always been a community of people. And that for me personally, having really founded the project and then participated as a full-time person for like 9 years, and then stepping away, I've been away longer than I was like directly in the project. I've been kind of like keeping an eye on it from a distance. And part of it is the experience of like having, adult children that they're all the way through school and they're off in life and they're doing great. So it's been really part of the fun of the whole thing. But I do want to really talk about kind of how it got started, the initial ideas and motivation. And I'll talk a little bit about the user, the design for like low-cost hardware was in there up front. And Matt's here, so he can tell me what I'm missing here. One of my mystery questions is I'll ask you is like, when did you and I meet in person? I know I've got ideas about that. So let's see, the first slide. Okay. So I guess the other thing, so my current position, I'm a principal software engineer at Planet Labs. We're a new space company. We basically are a data company. The data that we provide and generate are images of the Earth, as well as derived data about that, like where are the roads today and stuff like that. I'm not going to really talk too much about that. I am going to mention at the end, we've built a couple of really neat radios. We've done, because of a bunch of restrictions having to do with space and various regulations, there's a link to a paper that we've published. It is in the slide deck. So for details about that, it was a 1.5 gigabit per second radio that we downlink the images from, which is its own accomplishment, getting 1.5 gigabits out of a 3-liter CubeSat. And there are roughly about 180 of those CubeSats in orbit right now, plus another 20 some odd other satellites that have higher resolution, the SkySats, which have about a 50 centimeter resolution. So meanwhile, on to the GNU radio story. Clicker. All right, once upon a time. So I had been on really the backstory is at least a little bit important because it's how I got here. And one of which is it goes back for me to like 1993. And there was this introduction to this thing called the Clipper chip. And this was a thing around a deal put together by AT&T in combination with the National Security Agency. And they created this thing that was going to be this secure telephone device. But the first thing that it did was transmit the key escrow keys in the law enforcement exploitation field of the protocol. And I was like, wow, that seems like not the kind of secure telephone I would want. And I was, I'm a background in electrical engineering, but mostly I've always been kind of in the computer science category. And I was kind of scratching my head and thinking, well, this doesn't, the famous last words, this doesn't seem that like a hard of a problem to solve. And I got started to meet really interesting people. There was a group of people called the Cypherpunks. We were meeting like once a month and had a really great mailing list that's sort of famous for all kinds of crazy business on there. And along the way there, I met, Whit Diffie, and he became a first customer for me and a mentor. And then some other people along the way, John Gilmore, who was at Cygnus Solutions, he was a founder there. They provided paid support for really like the GNU tool chain primarily. So if you were like a, enterprise customer and you wanted to use those free software tools, but you wanted somebody to call, that was a service that they provided. So meanwhile, I started building those things. And then I discovered a couple of things through a series of like 3 different companies along the way, which was, this was a thing that I wanted to have a secure, I wanted to be able to have my own private conversation, But what I really discovered is, as a business idea, it was terrible. The vast majority of people do not care. Some of the people who care, you do not want as customers. And at the end of the day, we built 2 generations of these things. I learned all kinds of things, met interesting people. But finally, it was just kind of like, okay, this is, I was one of those stubborn, not going to pivot things, because there was something I wanted to exist in the world, which we did get 2 generations of them, but at the same time, like not a really great business plan. So meanwhile, as I'm like kind of towards the end of that whole story, and at the time, there were not, cell phones were still, they weren't like smartphones long in the future, right? And the US situation, we originally had like analog, basically FM, our analog cellular phones were FM radios, basically. And then the next thing that came along was 2 digital standards. One of them was IS-136, which is for interim standard, IS-136, which is a TDMA one. And then there was IS-95, which was really the first CDMA, turned out to eventually be CDMA1. And I'd been reading specs on all these things because, my dream would have been, well, if I was going to really want a way to have a secure telephone, secure communication, I would really want something I could carry around. Not something like that I had built that you had to like plug into the wall with your like plain old telephone service. You remember that? Anybody here remember all that stuff? You have a telephone and a cord and all that whole business. So I had built upon that, a gadget that goes between your phone and the wall. very simple, secure and clear. And you'd had a regular kind of just talk. And then if there's somebody on the other end that's got one of the gadgets, you just push the go secure button and comes up and, brings up the modems and does a Diffie-Hellman key exchange, and you can confirm the hash of the key and like have a nice conversation. So anyway, I started reading the cellular standards just because why not? And it came to my attention that in the IS-95, the voice privacy feature, which would have been there to like secure one's communications, was actually had some pretty serious flaws in it. It was basically a stream cipher with a fixed length pattern that just kept repeating. It was, I think, on the order of 42 bits. It also, that this is before the standard is even ratified, that there are papers published about, hey, this thing's got a problem. And it turns out that one of which is these phones, the standard had like a full rate, half rate, quarter rate, 1/8 rate, vocoder rate in them, and then they turned off. So they did discontinuous transmission, save power and bandwidth. Well, one of the things, if you think about if you're talking and the last thing you're going to say is, okay, in any talk spurt, then there's silence. So you statistically have known plain text going into the system, and this thing that just is XORing the thing across. So anyway, there's one paper published, and it's like by some, good, smart people. And then later, there's another one published that is just like, oh, there's a straight up ciphertext only attack because the forward error correction leaks enough bits that you can go figure it all out. So, I mean, this is one of those ones where there's a paper, there's smart people wrote it, it says it's broken. But meanwhile, it's still going to get deployed. And I'm like, well, can't we just pull the bits out of the air and make this point really, make it totally explicit? I don't know if those of you around earlier, before this time, there was the data encryption standard, and we were using it to protect everything, your banking transactions and all this. And folks were, were saying, it's perfectly fine. It's perfectly fine. Don't worry about a thing. It's perfectly fine. But people who had, done the math and said, this is brute forceable. And my friend John Gilmore went and basically funded the development of this brute force DES cracker machine that turned out, he invested like $250,000 and hired a smart person to go build it. And it was built out of, gate arrays, kind of those things don't exist anymore, but kind of the intermediate between an ASIC and this thing is much easier to build. And so they were able to just demonstrate that, for $250,000 and like 2 engineers for a relatively short period of time, one just regular old person off the street could go build this cracker thing. And they published all the, the VHDL to make it and all that good stuff. Anywho, so kind of in the spirit of that, I was like, well, this crypto standard is clearly broken, and I'm kind of at the end of my road with regard to trying to build secure phones because nobody really wants them. And I'm looking at this standard and I go, all right, well, how hard could it be to pull the bits out of the air? That was really my question. So, and I realized if I had any sense and that was all I wanted to do, I would have gone and rented a piece of test equipment, right? There was clearly somebody's got a piece of test equipment that will, most likely, it might not be the primary, output, but there's probably some interface on it that would, give me a raw bit stream out of the back of it. But what's the fun of that? I was kind of like, in doing secure telephones, if you think about what's in there, there's mostly like a voice encoder and a decoder, and there's like a modem in there, like for, your whole dial-up modem kind of a thing. And there's some crypto, but the crypto is really, in one sense, it's got to be implemented properly, but it's the least amount of the volume of everything. So I was looking at all that and I was like, well, maybe what I ought to do as my next thing, because I'm done building secure phones, is I should just like teach myself digital comms. This is like the next thing. There's a standard that I like learning new things. And I talked to my lovely wife, Cheryl, and she's like, that's really great, but I don't want to be poor while you're doing this. And I was like, oh, she is so smart, So anyway, I'm like, you kind of like, okay, but I start kind of shopping around for like, I'm kind of done pretty good at self-teaching myself stuff, or you find people who know and can help. So I started looking for some hardware that would like, well, what do I need? What would I need to start messing around? What's my lab kit look like? And I found this hardware. It was some Canadian company that's still in existence. I don't remember their name, but it had like a pretty good sized FPGA and an RF front end and like the TI DSP and, kind of everything you needed to go play. And it was about $10,000, which was kind of within my personal discretionary funding for gonna go learn something whole new thing. I could do that. It's shorter and cheaper than going to grad school, right? And then there was this little snafu along the way, which was it was going to take $70,000 worth of software licenses to turn it all on. And I was like, not within my personal discretionary budget. So along the way, I'm like, okay, well, I don't know. And then along the way, I go have dinner with my friend John Gilmore. It was just a social dinner, no agenda, just going to go, hey, we're at a Thai restaurant, we're talking. And I'm about, I told him basically this story. He knew about the stuff, but I told him about finding this hardware and that it was like $70,000 worth of software license. And he's like, well, why don't we create a free software project and you should just make me a proposal for funding? And I was like, oh, really? I'm like, okay, that was easy. And Gilmore had been a customer of mine in the secure phones. He knew me for many years, knew my sort of capacity, let's put it that way, had seen me work before. So it turns out that, we found and he introduced me to Richard Stallman, who is the founder of the Free Software Foundation and the GNU project. So we're begun with zero, and we're now officially a GNU project. And we find a, donor-directed charity that Gilmore can send the money through. And it was truly the best arrangement I've ever had. It was classic patron, that it was like, took one phone call a month to keep the money coming. I was not being, was trying to keep it really easy. You don't have to keep track of your hours or anything. Just, go to work, we'll talk every now and then. And so I started out with, well, what hardware can I actually buy right now? And it was like this measurement computing. Hello, National Instruments, measurement computing MC4020. It was a PCI card, not a PCIe card, but a PCI card. It was like a 4-channel A to D thing, but you could run it at single channel at 20 megasamples, which is seems like enough. But that was at least burning up 30% of the total bus bandwidth to run it that fast. And but now you need something to put on the front of this thing. Like, where am I going to get my signals? So kind of a little shopping around, you find that there's eval kits for these cable TV tuner. It's a cable modem tuner box, a little can. It's got an F connector on one side and a little, SPI interface into it on one. And it had a relatively low IF output. Like the channel spacing on US television stations is 6 megahertz. It was on the order of like in the 6.5 megahertz range, so low IF. So at this point, you got enough to actually capture the FM band and television signals. So first thing built is like the FM receiver. And the other part to just talk about, so that was kind of the initial hardware that was available. But again, this board cost as much as a PC. This is not something it's kind of like, okay, part of the, I'll buy this, but you're not going to want a whole bunch of, and it couldn't transmit. And then there was a part about, well, where is there software around that we can use as a starting point? And well, took a look around, read some papers, found this project called P-Spectra at MIT. Now, actually, hang on one second, let me just get my water here. In the staying hydrated mode here. So P-Spectra turns out to have been kind of quite interesting. There are at least 5 or 6 people that got their PhDs by working on this code and through this code and writing it. One of them was like Vanu Bose, and there were some other people. Turns out that down the road, I did meet their advisor, and I was like, oh. And so we built, we're pretty much, there were some examples in there, learned some tricks that are still in the GNU radio code base. Like one of the things was the frequency shifting FIR filter, which was a thing that in software, you do very differently than you would ever normally do it in hardware or in an analog equivalent. It was computationally more efficient. And then what happened along the way? So we kind of get the FM receiver going. And then Gilmore is like also co-founder of the Electronic Frontier Foundation. And at the time, the US was on this transition between the analog television that it's had forever to this new digital standard that it was going to, there was a full specification for it. It was called ATSC, the Advanced Television TSC, who knows? But anyway, it was kind of an odd thing, but from a learning your digital comms universe, it was pretty handy because it kind of had one or two of everything you ever wanted to build, like two kinds of forward error correction in there, some kind of like a non-standardish kind of a modulation scheme in it, and a whole bunch of things. And that at the same time, the thing to know is that that in the US, unlike the cellular networks, right, who basically that was all done by auction, where literally the operators paid billions of dollars for access to spectrum, that in the television stuff was kind of grandfathered in with a simple license, like a fee that was paid annually. And it was on the order of like hundreds of dollars kind of a thing. And it was part of the, public service getting, back in the day when there were 3 television stations and maybe 1 UHF station, if you were lucky. So meanwhile, here comes along this new standard. The Motion Picture Association of America wants to make sure that they're going to transmit this digital stuff, but they propose that we're going to put this little bit in this protocol that's in this public standard that was called B, the B bit, 1 bit in the header. That was like, this is the broadcast flag, which was supposed to say, thou shalt not transmit these bits anywhere. Don't put them on disk. Don't do anything. For us, this proposal came out of their copy protection technology working group. So there's kind of this weird conflict is they're getting access to all the spectrum for free. And they're saying they're trying to do the same thing that they did with like DVRs and all of this stuff where, cable modems, all the whole, like, we're going to lock the whole thing down and you can't get access to it except if we say so. No time shifting that whole business. So out of the whole crypto business in the mid 90s, there was all kinds of things happening around like, well, you could, for example, publish books about crypto, including all the explicit algorithms, but you could not ship the code outside of the United States. And there were some challenges that came around there, and like, I think Phil Karn was involved in it, and then Zimmerman basically worked with the MIT press, and they had the whole code of PGP printed out in a very OCR friendly thing with checksums in the column, and they just printed this big thing that you would just go, get a little guillotine to slide this thing in, and then just machine feed it into your like OCR machine. So the point was made and settled that software is actually First Amendment protected speech, because first, software is a communication between programmers. And secondly, that the machine can execute. You get the compiler in there and you end up with bitstream out of it. So pretty much we were going to just use the same idea that, software is free software. We're going to go build. Gilmore says, let's go build an ATSC receiver in software. Now, this is the thing that in 2001 was possible, but it couldn't run in real time. But at the same time, in 2001, Moore's law it was totally doing its like every 18 months, your computer gets faster. You don't have to do anything. You just have to wait 18 months and go buy a new one. And it was still really, really going to town. So that was the real first, let's go build a complicated piece of software. Anywho, now someplace in the story, Matt Edis, go ahead, Matt, right? Yay, Matt, okay, raises his hand somehow, and we meet. And I know I've met at your office. I know we met in Monterey. I don't know, I assume it was on the mailing list somehow, but we get together. Matt's, has got a back, I'm gonna tell the Matt story, the short version, but Matt knew a whole lot about signal processing. He was doing like Bluetooth basic design and And I'm like mostly software guy. And so, but we get together and we go, we need hardware. Okay. So this is a conversation about what can we, because you could go buy hardware again. There were other things available. They're still like in the order of $15,000. So there's a conversation that begins around, hey, what do we need? What could we build? And somebody was telling the morning, was it Derek, about some of the email conversations that happened. So I don't quite remember them, because it was just, for me, it was like, okay, let's go figure out what we could build. And anyhow, I was looking through some change logs in the original code. When we did releases originally, they were tarballs, and they're still on the Free Software Foundation. If you go to, like, software, blah, 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 you can get the whole history of these releases. And there was like a usurp 0.5 release, which was the earliest one I found. And there looks like in there that we were like, okay, started on that in, well, 2003, July 30th of 2003, where there's a comment that says about the FX2 registers that said that finally changed the bit sequence to this SDCC, which is the compiler for the thing. It's an 8051 knockoff, basically, that they're now allocated where they're supposed to be. So there's evidence that we were working on it then. And then I came across this picture that I don't have in the slide deck because I hadn't talked to Matt yet, but it shows us like sweating in Germany at this like Chaos Computer Club conference, literally 20 years ago. I mean, it was like, it was in 2003. There's a picture. You come by and see me later, I'll show it to you. And so in 2003, there's the beginning of this the thing that became the usurp. There was like a usurp 0. There was like prototypes. There was part of it was we talked to all kinds of people. Could they build this for us? What should we use? USB 2 was a thing, and there was like some parts for it. Again, feel free to ask questions along the way here. This could be audience participation if you've got questions. There's other things about, like, in 2004, there's things like, oh, RX timing problem fixed, okay, great. And then there's evidence in 2004 of August that, there's about copied, common program modified for the time. We've got a different GPIF program for the usurp 0 and the usurp 1. So at this point in 2004, around August, there was the beginning of at least the usurp 1 was being, like, the first one was being prototyped, besides the usurp 0, which was just a little tiny board with just SMA connectors on it and no RF. So meanwhile, back to the EFF and this copy protection technology working group. So we go and make progress on this. And I want to, really, Matt taught me a lot of what I know about signal processing. He was actually way better at it than I ever was. And so it was just, thank you, Matt. And again, I want to point to that there's just a lot of people involved. I mean, there's just as it went on. And that we got this thing working, or it was getting close to working, and that the Motion Picture Association, the MPAA's Copy Protection Technology Working Group, is having this big gathering about the broadcast flag in Los Angeles. And so the EFF says, okay, will you come with us to this thing and, talk about what you're doing, about you're going to build this piece of free software, and we'll put in the code that will, like, honor that bit, but we're going to publish it so that anybody can do it. So, anybody could just ignore that bit. So we went there, and it was all of the kind of consumer electronics companies. So there's like Philips, and there's like a CTO and their chief counsel. And then here's the MPA and their, like, chief counsel, and, Sony and their chief counsel, and Disney and their chief counsel, and the EFF folks and me. And so we're having fun, and I just kind of tell the story. We're gonna build this thing, and there's this bit in there, and we'll write code, we could honor it, but it's pointless because, we're gonna publish this thing and people are just gonna take it out. And then there was, like, some folks from I don't remember, but it was one of the Japanese, communication companies that was like, oh, you must be 7th level analog master to be able to decode the signal. And I was like, okay, we shall see, thank you very much. And so we ended up getting it working. It's still now, in the code base, it is still with us. It's been through many iterations, but it was really the first thing that we built. It was quite complicated, didn't run in real time. I remember that the first thing we did was just be able to capture, point a log piece. Speaking of yesterday, it's like a log periodic antenna, bought at the, like, Radio Shack, TV antenna, and point it at, in Monterey, where I was at the time, there was at least like 1 or 2 stations that occasionally were broadcasting, high def HD at the time, what was HD at the time, signals. And so we could capture in real time. Couldn't decode in real time. So we had some big files. And I remember it was like Law and Order, some episode from Law and Order. It was like one of the very first shows that was like, in digital native format. It really kind of just went from there. There was like the first usurps. There was building the ATSC, which was a whole lot. There was evidence in here about, so we built the ATSC and this thing that really was slight modifications of the P Spectra code. And I was looking at my first commit that was around in the regarding this was like in 2001, September 18th, it was fixed stir length related buffer overrun in P Spectra code. And another piece was return value was off by a factor of, I size of the type. So it was kind of like, okay, this code had managed to get like 5 or 6, PhDs done, but it was nowhere near what would you call production code. I mean, it got its job done and, and it served us because we used, got it kind of shaped up enough that we could go build this ATSC receiver. But given the commitment to actually build a software project that could be used by people who wanted to learn, one of the whole big pushes for it was a tool that people that wanted to learn about digital comms, like particularly grad students, could use this thing, and it would be reliable and it would be production quality code. So at this point, I talked to Gilmore. In one sense, we've accomplished this first goal. We did the thing with the MPAA. And I'm like, well, this stuff it was helpful, but in one sense, it was really kind of like grad student wear. It got the job done. It was designed to do, but it was never designed by people who were going to try to support, something that was going to run all the time and not have any errors or, segfault, for example. And I have to say, and then I went to Gilmore and I was like, okay, I want to start all over again. And I, this is usually the worst thing anybody ever says, like, I want to just start all over. And he was, I guess I made my point well enough that he was like, okay, good, fine, keep going, press on. And so we started, at that point, I started building what it was really the thing that as GNU Radio. Thank you. And we went in there, there's early references to like the IO signature is in there, and there's like the single threaded scheduler showing up, and it like its first releases and all this whole business. And I guess the thing I just really want to say that there was different people started showing up. There were people who knew about various things. There were people who were interested. The mailing list at some point, the other part about this was that then Gilmore introduced us, Matt and I, to Jay LaPro, who was a professor at University of Utah and was running this big network test bed that's still in existence. And basically he bridged us in, and Jay and his whole crew were like the wizards of NSF grants, because they were running this really big, national test bed, and they were willing to sure, we'll put some of your gadgets around campus and we'll wire them into our reconfigurable network. So that was the beginning of all being kind of transitioned into NSF funding for a few years, I don't know. And I know Matt and I were funded to do, they couldn't really believe it that we got this grant through really, Jay's and his whole team of people that were expert grant writers. But Jay was, I remember saying, I've never seen a proposal that was really just bullet points get approved, But we were building something that was needed. It was like this, all of a sudden we're going to have this low cost hardware. So part of it was the development of GNU Radio and support of students and all of this whole business, and the ongoing building of usurps and getting these developed. And along the way, Edis research emerges in some point in there. And so, I think I want to point to is that has always been, in one way or another, it takes support to make any kind of free software project go. So I mean, you could do some things if you have your regular old job and you're just sitting in a corner and you're only doing 2 hours every third day or something, but it's a whole other thing if you can actually bring together some kind of a funding source you know, smart people and people that keep introducing you to other people. And as it went on, that, for example, then I got hooked up with some people from Rutgers. It was Ray and Yvonne at Rutgers at WinLab, and they had a giant, they still do, again, a networking test bed, but theirs was wireless. So they had a whole bunch of usurps put in there and all kinds of stuff. So mostly I want to just point to community funding somehow, so that the key developers figured out some way that they were going to get funding. It wasn't all through NSF. Some of the people, Jonathan Corrigan, who's not here, but he was doing training on GNU Radio. And I was like, wow, brilliant. I think he was making more money than any of us at the time on delivering, you know, training to various customers. And again, he had bundled usurps in it on some kind of a deal, which made his training very useful because it, I don't know, dodged some accounting thing for those customers. Anywho, and then it's about 2009, 2010, that I really kind of had my full of doing this as a full-time job. And I had met Tom Rondeau, who rumor has that he's going to be here today sometime. Anybody back in the corner? No, not yet. No sign of him yet. But I'd met him somehow on the mailing list and had gone to Virginia Tech where he was finishing up his PhD, and we talked, and he was like, great, he's perfect. He actually has a PhD in, like, you know, like digital comms, or, you know. And so I basically picked him as, in one sense, my hand-picked successor. And so it went from me running it for the project for like 9 years, and effectively in this, like, you know, the benevolent dictator kind of a position, to Tom. And then at that point, he got smarter. First of all, he was part of the people that wanted a conference. I was just like, that's really great. I have no bandwidth to even think about that. So there was a part about just keeping the handed off. So this is kind of the end of my personal direct involvement in it. But what grew out of this is the handoff is like, there was Tom, and then there's the people after Tom, and then there's like a foundation, and then there's how do we organize a conference and, you know, keep participation going. And, you know, I think the time I left, we had a couple thousand people, mostly on a mailing list, because it was like at that time, it was like, we'd ask people to, like, go search the mailing list, then ask your question, you know, and if you have, you know, let me Google that for you, because kind of a thing, because it was a totally self, you know, it's about survival, you know. And at one point, one of the metrics in the annual reports for the funding from NSF was like, what percentage of the email total traffic on this Discuss GNU Radio list was I doing? And it was like 20%. So it was like really a big part of my time was involved in answering questions for people, because they were, I mean, that was part of the whole thing, you know, how to do that. So I really kind of want to wrap it up there. There's lots of other stories I could tell, but this is the thing I want to just leave you with. It's community, there's support. And again, support comes in all ways. A lot of it is in relationships, resources. Some of those resources are money. Some of those resources are, I can get you funding indirectly, or go talk to these people, or just plain old skill. People have got, like, you know, we'd have professors started showing up, and they were like, oh, you guys need a whole thing about forward error correction. Right on, go for it. You know, write all that up for us, you know, or somebody's going to do OFDM. So like that. And here we got a little bit of time for questions, and then I'll be around through Friday evening. Yeah. Got a big question in here. Yeah. Part of the point of this is you too could build your own free software project.
So with software, you frequently figure out how you should design it when you finish it. So looking back over the past 20 years,
Yeah.
if you could start over now, what lessons would you have?
I'm pretty, yeah. Well, I'm actually pretty happy with how it went. I really am. A part of it is we had that whole first part with P Spectra, and we built some things in it. So we had it wasn't not like we started from zero experience. And I was pretty happy how it went. It was really the first thing I'd ever coded in C++, and it was also the first thing I'd ever coded in Python. And again, we had another person said, hey, you should put Python in here. We're like, awesome, great, we'll learn how to Python. The thing I see now is my pitch for my very favorite thing, and I've been talking about this everywhere. It's more like a GNU Radio 5.0 thing, but it's this new programming language called Mojo, which you should corner me and talk to me about. But basically, it's built by some folks at a company called Modular. They're really building AI frameworks for executing graphs, computational graphs is very, very fast. They're currently like 35,000 times faster than Python, where in their particular benchmarks, they've been running like NumPy is only getting about 15x speed up. And they handled all the SIMD numeric stuff, and they're gonna do all these GPUs. It looks like a fit for us. They're not building it for us, but it looks like it's a thing that I would, and it solves the problem of you've got Python too slow, easy to use, not multi-threaded really, and then C++. So that was my kind of to the future kind of a look. The other thing I want to do, there's actually one more slide I wanted to tell you because I promised. This is a citation for the high-speed radio that we built, this 1.5 gigabit per second. The first link has got to actually, there's a slide deck behind that also. And the second one is, they both go to the same place ultimately, but there's the paper itself. It really is quite detailed, shockingly detailed to me, that we gave away all kinds of secrets about how we built this radio. The short version of it, it was like 2 watts into the antenna on the spacecraft, but a total of about 40 watts of all the compute and FPGA power to get it done, all in the CubeSat. It was very dense. So again, thank you very much. I'll be around.
Question. We have one more question.
Yeah, absolutely.
I just want to say, for anybody that was scared off by the introduction of something like Mojo, it is a superset of Python. And so if you understand Python, it's very, very similar. And so don't be too scared, but it does seem very cool.
Yeah. And it's like strict superset, which is really great. But when just to say a couple more, and then I will shut up and you can corner me and talk about this with me. But there's like, once you get into the strict superset part, you can do all kinds of system programming. Like you completely be without the garbage collector. You can do manual memory allocation. Their smallest hello world is 20K, which is like all Mojo, no Python. So I don't know. It's the most interesting thing I've seen in the programming languages. Rust is out there. Everybody got to learn Rust, but Rust is you got to tell it everything, and it's unwrap, and just not looking like super friendly to me. So, all right, and the other thing, just to kind of into the bridge, which I'm sure you're going to do, there's like a break or something, but I'm super happy that the rest of this day is about GNU Radio 4.0. I've been kind of keeping an eye on, I've been showing up on some of the meetings and listening because they were talking about things that I cared about, like the scheduler and how do you do buffering and all of this whole fun stuff. And I'm, again, super happy that there are people that are now fully engaged trying to build the next version of GNU, really next version of GNU Radio, like all the modern C++ and all kinds of crazy business that make it go faster and be more useful. So thank you again.
Thank you very much, Eric.
Yeah.
We have a small gift for you,
Oh, a small
bit,
awesome.
bit of swag. So
Thank you.
thank you so much for coming and speaking. And I've had fun chatting with you, and everyone else should as well.
All right.
So have a great day.
Take care.
Next up is Josh Mormon giving a quick introduction to how GNU Radio 4 is going, and how we've gotten here and where we're going, and then followed up by Ralph Steinhagen talking about the results of the architecture working group over the last year and a lot of the details of what that actually looks like. So you've got a microphone there. Carry on.
All right. Thank you again, Eric. I want to reiterate gratitude for the community you've built here and also for being involved in this next phase of work. Like having your presence there in those meetings has been amazing. So thank you. So I want to talk a little bit about our road to GR4. Sometimes it feels like this might be where we're at. So we've talked the last few years about a lot of different exploratory paths. What is GR 4.0? What's going to be the next big thing? And there's been a lot of work presented, a lot of ideas presented, prototypes, development branches, but nothing to this point that's been concrete enough to say 4.0 is coming on this date. So when we say the road to 4.0, it has been a windy road, and we hope to feel like maybe we're past this point at this right now. We've gotten in the last year to a fork in the road where we've had to make some decisions about do we take the path that, is an incremental advancement from GNU Radio 3.0? Do we make some incremental improvements, make things better, bring in a lot of the things we've talked about, or do we make more radical changes and set ourselves up for a much stronger foundation for the future? And I think, I'll be introducing again Ralph, he has proposed some incredible foundational changes that we are committing to for GR 4.0 that is going to be bigger learning curve, perhaps bumpier road, but that should pay off. So I'm not going to take too long here. I want to step through the original vision for 4.0. We haven't departed from this. So the vision that we've laid out the last few years has been modularity. One of the challenges in GNU Radio is it is this one thing, directed generally towards running things on CPU and can be adapted to other platforms, but it's not generally designed for, say, heterogeneous compute platforms or distributed architectures. So that kind of modularity, bringing in different conceptual schedulers, runtimes, it's been hard to shoe in to the code base that was, conceived 20 years ago. So this is the point where we wanted to create a new architecture to take us for the next 20 years. And in this process, we want to keep GNU Radio accessible, enhance usability, be able to bring more developers, more students, enable more research to use this, keep it accessible for people. So now what is the deal with 4.0? So the last few years we've presented demonstrations, a lot of different things. Last year we saw the ability to streamline the block development process, being able just in a couple of minutes from scratch, create a block, very little code, get you right to the work function, put your signal processing there, and it runs. In the past, we showed some ideas for scheduling enhancements, such as the performance enhancements of just being able to run the simple idea of having multiple blocks running in one thread. That can be a big boost depending on what you're doing. And then out of the DARPA SDR 4.0 project, there was a lot of work around custom buffers, and then that also some extensions to modular schedulers there. So where we got to after last year's conference was a development branch on the main repo. So we committed and said we're going down this path of these incremental changes to GNU Radio. But what happened in the last year is, as Derek introduced Ralph yesterday, Ralph came in, saw what we had been doing on the development branch for 4.0. It fit his use case. Some things that, he's heavily invested in using GNU Radio at the particle accelerator. There's some things that GNU Radio 3.0 was unable to do easily. But we were at a point in the development process, bringing some features into GR 4.0. It met his needs, but what Ralph did is he identified things that could be further improved, and with his team of high performance computing experts, really is able to jump in and help the project tremendously. So this relationship has kind of taken us on a departure from what we laid out last year for 4.0. And Ralph is dedicated to improving the open source ecosystem rather than just solving his problem for his group. So we're deeply grateful for that. Let's see. Okay, so I don't want to spoil Ralph's talk. He's going to go into more of what this modernized GR core is, what the motivations are for it, but the basic aspects here are, through type strictness, able to use the compiler to do more work, change the scheduling architecture from a microservice architecture to a work scheduling architecture, and have less overhead that way. And also one of the big improvements here is the buffer architecture, able to handle arbitrary types. So we're going to see some cohesion between packet processing and streaming architecture, and those coming together through the same buffer architecture, through synchronous packet scheduling. So I want to outline kind of where the development branch Dev 4.0 got to, and conceptually how that is moving toward a more solid foundation with, I'm gonna have to, there's a lot of clicking here, so I apologize. Okay. So the Dev 4.0, it started as this new sketch project that architecturally borrowed heavily from GR3, introduced a bunch of concepts. I won't go into these individually, but conceptually, what Ralph and his team had started a fresh code base. So conceptually not completely new, but a completely modern C++ implementation that this is the GSI Fair graph library and introduces a bunch more things, strict typing, very much improved buffer structure, compile time block merging, which is an exciting one, reflection, parameter management. We'll see. I don't want to spoil the details here. Sorry, excuse me for that. Back. Okay. So now if we look at how do we actually get to a 4.0 release? So if we look at right now, we are actively developing 3.10. 3.10 is GNU Radio right now. Now, I just want to reemphasize that 3.10 is actively maintained. We should be adding features to it, using it, creating out of tree modules against it. We plan on this being around for a long time. You know, a couple of years until 4.0 is solid. What happened along the way? We started this development 4.0 branch, brought in a lot of the code from GNU Radio, but added some of the new concepts, created this as a separate code base. But Ralph's team came in with this graph prototype code with the modern C++ core. So this is what we are going to be building upon for 4.0. So if you pull anything from this talk, it's that what Ralph is going to describe in this next talk is the basis for 4.0. Conceptually, we're going to bring in some of the usability enhancements, things from development 4.0, but we're building it upon a stronger core. And then from that, the question becomes, what's that minimum set of features that we can put a stake in the ground and say, 4.0 is ready to use. We recommend, say, SDR vendors to build drivers against it, things like that. I think that is the next step. What we need to figure out is how we actually get to something we can call 4.0. So apologize for the rambling here, but that's all I had. I want to bring Ralph up to go through more detail, and that's the definitely more exciting part of this. So any questions?
I have a question for you. So I don't know a better way to frame it, but how are you planning to ensure kind of the ease of use for the people who, you know, aren't necessarily coders or developers, but have made good use of GRC and things like that? So what's the plan there?
Yeah, so the idea is that from a user perspective, you know, say if you're a GRC user, we're rebuilding the core from the ground up. The usage of how you build flow graphs in GRC should not change. You know, it's all going to be block-based signal processing. If you're developing blocks, there might be some things different. There might be some learning curves, but we have to make sure that we keep two big things in the process. One is the ability to develop blocks strictly in Python, where you can write a Python work function. Like you don't have to develop C++ and able to do signal processing in GNU Radio. And also that you can create flow graphs in Python that are running C++ blocks. So I think those couple of things, we have to make sure that we maintain the same level of usability we have now in GNU Radio 3.
Other questions? Let's give Josh another round of applause.
Boy, what an act to follow. Literally standing on the shoulders of giants, both on Eric's and then of John and Josh's. I'm here to report a bit on the progress that we made since the past year. Big. Yeah, maybe I take it out. Is this better? Thanks for being able to report on what we achieved over the last year. I'm just here to report on behalf of a great team, led by Josh with his architecture group, but also lots of thanks to Derek and the whole architecture team and all the people that are listed down there who contributed actively, technically, and with their expertise in high performance computing and expertise from other domains. And when I'm standing here, I'm literally standing on the shoulders of giants. If there's anything good, what I present here, it's the people that are named around me. If there are things that you don't like or things that are awful, that's my fault, please blame me. This is like a strict job description, separation. Everything that is good, that's the team. And everything that went wrong, that's on my account. GNU Radio was and is a very big success. I'm like, how many open source projects do you know that live more than 20 years or more than 10 years? Most, they start off when they start a PhD, and once the PhD is over, maybe they maintain it for 2-3 years, and then most of them die out in obscurity. What Eric and others achieved was that there's a healthy community around it, that people say like, okay, we carry this on, this has a very strong buzz factor. Even, I mean, like buzz factor is a positive thing, that even if you run over one person, it still lives on. And that's also like our mission. We wanted to invest in this ecosystem. Maybe we could stem it ourselves, but we wanted to invest into this community, which is great, which want to use it, and leveraging the benefit from the diversity we have. And making sure that we have a strong buzz factor, so that we have maybe 7, 8, 9, 10 core maintainers that can stem and offload the responsibility. I mean, like while Eric, it seems to be like a one-man show, and he basically, if you would do it with one man like Eric, you could redo everything in one go, but our explicit goal was that we spread it out on more people, so that the burden of being up at night and fixing things that are critical for some of the organizations that need to be fixed, to keep it a bit more relaxed and fun to work with that. So in that sense, I'm but a dwarf standing on the shoulders of giants. On the bottom, Eric. On the shoulders are Josh and Josh and Derek lifted us up on their shoulders to show the community what's around there and helped us to get a better gauging the future where we want to head for. Importantly, why we invest in GNU Radio is it's a great ecosystem with a great community, but as any projects, many software code bases grow organically, like incremental adding features here and there, sometimes always in the same line, but sometimes you have ideas that worked out as a proof of concept when you incorporated it, but when building upon it, you see like, oh, maybe now since I reached the top of the mountain, if I would have to go back to that mountain, maybe I take the more direct, easier path than the path that we actually took during the development process. And that's when I say like it's not a new development that we did. It's just that we took the experiences and the code base, so what's worth that we should preserve, and this is usability, this is the flow graph concept, that's the GNU Radio companion. This has to be the same because that's excellent. People love that, that keeps the entry level for normal users as low as possible. But there are also certain things that were necessary initially, which through new technologies, new C++ standard became sort of obsolete. And nobody could tell me like, why is this part of the code still there? I mean, it was a bit of archaeology. And then if Marcus told me like, I thought like, okay, it could be there's somebody else who uses this part of code. Well, that's important when there's like, okay, let's try without and see whether we can make it better without that. So we started with an organically grown tree and just removed a bit of the branches where we felt that they were excessive, so that we have a stronger core, that the remaining branches grow longer and survive not just for the next 20 years, but ever, and that GNU Radio is the best signal processing framework, full stop. Now, we have several modernization goals when we started off. I mean, like one is obviously simplifying onboarding of new contributors, because also our organization deals with lots of students, with academia, where people come in for half a year and they need to become effective to interact with radios and with our facility. but also for people who want to write blogs, that they can contribute more effectively without having to learn a very large, complex framework and to understand what the constraints are. So what's important for us is we wanted to rely on true industry standards. So we wanted to have as little as much as needed extraneous information that you have to get into the ecosystem, into the know, and to know what to do. We wanted to reduce the cognitive complexity because as you get older, I mean, I'm a very good code reviewer, even of my self-code, because after a couple of months, I don't even remember what I wrote. And if I read my code and I start scratching my head, why did it write that way? That's a good indication this code has to be refactored and simplified, because if I have a problem reading my own code, then probably many other people will have the same. And this has to be, if you read code, it has to be obvious and on a very small scale. So you don't have to go through the whole code base to understand a small section of code, but the single source of truth is important. And yeah, reducing the learning curve. And yeah, to promote collaboration, knowledge exchange and adoption, not just in the academia, but also in the scientific institution applications, but also to branch out to other organizations that are government funded or even industry funded. So that GNU Radio is not just a hobbyist or academia toolkit, but that this could be also used in commercial application. Because having industry on board is very, very useful, because they provide because they have a large deployment of hundreds of nodes, and the more you get their feedback, you see what works well on a single deployment scale, or where are the issues when you deploy hundreds of thousands of those devices. And this information is useful. And that helps us also growing a better SDR hardware ecosystem around that. And provide some continuity. So what is our main goal? And basically, I could stop here because I think everything is already said by Josh. But we want to preserve what is good and grow the existing diverse GNU Radio ecosystem. Python will be still in there. And there will be always a full thin Python layer over the C++ API so that you can use it in the most convenient way. But we want to make it more composable, more modular, and to opt in so that you only pay for what you need. So that you don't have to get in all the functionality that you potentially can use, but you just get that in what your application needs. And if you need some other extra, you can build it in. But if you don't need it, you don't have to pay for this eventuality that some obscure user like us, for example, needs. So without much further ado, let's show like an example. What is the hello world example for a simple processing block? And that's all that you have to write. Meaning there's no extra code generation, you don't need YAMLs, you don't need anything. You just basically write a simple struct, a C++ class. The only constraint you have to have is that you have to derive it from a CTRP template, which is called presently node. We will rename this. I mean, whenever you see a name that is a bit odd, that this node comes from the math branch of graph processing theory, where these blocks are called nodes. So we were initially not sure whether we should adopt a math terminology or adopt like the traditional GNU Radio block terminology. And for this one particularly, we went for node, but this will be changed. I just left it in this way because that's actually from the source code. So this is not slideware, that's copy-pasted from running as we have now. And if you want to write a simple block, you have to derive from this CTRP template, and then you define the ports that you need. And then you have an input port that takes in floats, you have an output port that takes floats, and then here you name them as you want to have them. In this case, it's one port called in, the other one out. And in this case, I said, like, I make a small basic multiplier, and it's like I have a simple scaling factor, but this is just for explanation, for illustration purposes. And now what's different, before you had like the work IO functions where you had to do a lot of boilerplate code, taking the ports, unwrapping how many samples you have, and putting the samples back. In the simplest form, if you just care about signal processing and math, you just have to implement a process one function because you have just defined one input port. It has one input parameter, which is the const float reference to A. And as a result, you return a float. That's all you have to do, and the rest is done with the default implementation of the work function CTRP, and you're done. And the advantage of this is the code here is the code is a single source of truth. So if you want to know anything what the block does, you can derive documentation from that, you can add annotations, And you can very well test it in unit testing, because we want to enforce in GNU Radio 4.0 a bit more, that every block that is put in is production tested, so that you can also use an industrial environment. And because of this, because of writing it as a sample by sample processing, this also allows us to skip buffers. Because the fastest buffer you can have in your signal processing chain is that you don't need a buffer. Because if you have one block, handing it directly over to the next one, it's the fastest way, and you just add buffers when you want to have those buffering capabilities, or when you have like two blocks depending on the same source block. You have noticed on the bottom there's like a small macro called enable reflection for. That's basically the compile time reflection that we added. This is something that we're working on with the ISO C++ committee, that the struct reflection will become part of the C++ standard, and that's, let's say, my sore eye. That's what we want to get rid of. So this is, for the timing, is still needed, but as soon as the ISO committee agrees that just this little bit of reflection should come in already now, because they have way bigger plans for compile time reflection, but if this struct reflection, field reflection is in, we can drop that. And it's also just needed, it would work without, but this is a convenient function so that we know that the input port in is actually called in. With this way, we avoid that we have to define a string, how the port is called. So yeah, what is, I hope I could convince you that this simplified a bit like the block development, because it allows like a standalone creation, is hopefully much more intuitive. And the code is a single source of truth. If you have issues with that or questions, please let us know. I mean, like, this is not contractual. This is a software project where soft means that we can modify it, and we can iterate upon that and make it more intuitive, or find a better naming. And that is more efficient also for functional testing, what I said. And this function, process one, is actually the one that is most efficient for the compiler to optimize in larger scales. And because you can test it during compile time already, you get an earlier warning if something is wrong in your block. So you don't have to run the block always through the flow graph and test it until you have a runtime exceptions, but already it will tell you during compile time, there's something wrong, fix it. And this should ease up the iteration cycles. Okay, now you realized I cut a bit short, because float is important, but I want to write a block for any type. That's now a feature for where you first need like really C and not just C. And then you can use with C++ templating. That's the standard. It exists already since decades. But with the C++20, you can constrain on what type of types your block is allowed to process. In this case, arithmetic, so any mathematical object can be used. But you can also write blocks with a new buffer that can have any arbitrary type, even like aggregate types, structs. The only requirements is that they're either copyable or movable. That's all. And then the structure stays the same. You don't have to write multiple blocks for multiple types, but it's just a templated process one functions, and you're happy camper. Now, some people might say, yeah, but this doesn't feel kosher. Processing one by one, that's inefficient, because, or maybe I swap in and out and have like cache line invalidations. I want to have more something like a process, like a bulk-based processing, where I get a large array of input samples, and I give out a large array of output samples, because I want to use Volk, and I want to, or I have an FFT, where I need, for example, 1024 samples in order to produce one out. And for those, we have an alternative version, which you can also use. The CRTP template, it recognizes this automatically. And then you get basically a span, which is a glorified array for the input and output, but the span is a non-owning type-safe way, which is recognized by the compiler and can optimize for that. And then you can, in this case, I used the range library. This is now where you can process it with a transform function, which is multiplying. It's basically the same what I did before. The advantage of transform is they can also use, it's automatically simplified if you use transform internally for the next library versions, for the C++ standard lib library versions. But you can also do parallelization if you say, like, I want to use the new executor policies for C++. Now, sometimes, fun fact, beware. Initially, when this was an input from Matthias Kretz. He's the lead for the ISO C++ standardization committee for numerics, so for our high performance guru. And he proposed this process 1 and said like, that's way more efficient. And my gut feeling, and hands up who would think same way, so like, no, that's never gonna be fly off. That's slower than my I loop over my array. I was one of them. But fun fact, one has to be sure of premature optimization. I was skeptical. We implemented the both versions in parallel, and in the end, you shouldn't only assess once you actually benchmarked it yourself against a real use case. And I lost. Not only is the process 1 not less efficient than this, but it's even 20% more efficient than writing the old code, the old style. And I thought like, okay, there is some gains. So you can have, from a human conceptual cognitive complexity, write simpler processing function, and you get more speed. So win-win. Now you still have some applications where you need process bulk, but as a number of samples, but you're not sure whether you produce the same input as output samples. For example, I want to consume 1,000 samples, but I produce just 2. So you have like a decimator or interpolator. And for this, you can either use the process bulk, and then you can have a consumable span and publishable span as your function signature. You just have to use them, and they're automatically being invoked by the block API. And then in the end, you can do whatever processing you have and say like from the input, you can give me all, but I just consume 3. So the buffer assumes just take 3 and the rest stay in the buffer, and you publish 2, and then the rest, next time it's invoked again, you get the remainder that you have there. And with this, you could do like a decimator, for example, or an interpolator. Equally, or you can even do something random ways, so like depending on how many processing logic, like if you want to write a PLL, sometimes you don't produce any samples, sometimes you have an arbitrary number of samples. That's the API for that. If you just want to do a decimator or interpolator, you can have it easier because that's still verbose. You can reduce this, and you can see on the top right, you have like a performance interpolation. This is like an NTTP, where you can, this is optional, you don't have to, because if you don't use this, then you don't pay for it. But if you use this, then by default, you can tell the block in advance, either as a compile time parameter or as a runtime parameter. Please instantiate this. You say the numerator is 1024, the denominator is 1, and that's basically runtime configurable decimation block, where you take 1024 samples and you reduce 1 out. If this denominator naming is not ideal, please let us know. This is all subject to change. We can adjust on that. You can set also later the stride. If you say like I want to skip every 10,000 samples because you want to take an FFT of 1024, but take every 1 second, then you can also apply a stride. And alternate, you can also access the block parameters directly. Then, because we have like 2 copies, one is the block, the single truth is like the block, but then you have to transfer it to the PMT representation. For that, you have to update the active, also invoke the active parameters to synchronize both representations. In the other way around, you don't have to, but if you do it manually, this way you have. But it's normally done automatically. And this is a big shout out to Simon Lebedev, who built this interpolator and striding block. Works fine. If you ever see him, please buy him a beer. Now, the thing is, like I showed a bit like a setting, like the numerator is a setting. Again, the same application, you want to sample, multiply by A. Now we went back to using the process 1 because it's more efficient. But sometimes if a setting changes, you want to change other internal factors of your block, because you say like, whenever somebody changes a parameter, I have to reallocate, reconnect to the device, make some other changes. And for this, you just have to define an optional settings change function. So the name is enforced with concepts. And then you get as an input, like a const reference to the old settings, and a constructing a property map, which is a map of PMTVs with the new settings. And then depending on the old versus new state, you can trigger whatever action you have. You can reset the block. You can allocate new buffers, clear buffers, so you know whenever a setting occurred. And this is optional. You don't have to implement it. And it's also not overwritten. we have like several updating mechanisms. You can either do like a thread safe getter setter on the block itself. Something that I'm very proud of that works quite well. You can also set settings via streams. For example, if you want to send the sample rate, you can set an upstream block, please change the sample rate, and that is then propagated through the whole chain so that the all blocks that are in the subsequent topology can update the sample rate and modify the block structure so that you don't have, in our case, we have up to 1,000 blocks in a row. They're all updated automatically. You don't have to iterate through all of them. You can disable that if you don't like this and still do one block at a time, or select please don't do auto update, but by out of the box, this is done automatically. Or you can also use async messages. You have like as Josh said, we have like the buffer doesn't distinguish between whether you do synchronous or asynchronous processing. Each of the block will have also like a message in, message out port, where you can send a PMT message in for reconfiguring the settings. This you can also use for packet-based processing or send any other logic that you like. So you have either one function is called synchronously, where it makes sure that all the input ports have the same number of samples, and the other group of ports, message ports, they invoke your callback function whenever something arrives, and then you have to tell something is enough, or no, please go back. I just act upon when my message port have a certain precondition met. Yeah, and here's also like a big shout out to please buy him a beer for his great work on PMTVs, because that all is based on his work and makes it much easier also to wrap to Python or to make it, to send it from one architecture, one node to the next, because this is now, independent on the architecture where you generate this. This is just some examples. This is like a pre-production code, pre-production because this is, we don't call it officially GNU Radio 4, this has to be evaluated, but that would be basically a full FIR implementation in the new API. And I showed it just for the sake, you don't have to read all the slides, but just the fact that it fits on the slide is a big achievement, because before the code was 5-6 times as much and you had to be very intricate, but you can see you just need to apply the input-output ports. You get notified when the settings change. It also shows a bit like how you handle with input and output histories. And the actual function on the bottom is just a std, like a std algorithm, std inner product, that's all. So you have just one line to implement an FIR. And I think this is how it's supposed to be. On top you can see there's the code, like code documentation, where you either can provide like some HTML pages, or for your UI, you can say the writer of that code documents inside his code what each parameter with each function has to do, and this can be then used in the UI to display how to use the code. And you can inspect that without having to launch from a developer point of view, without having to launch the GNU Radio companion to see how it looks like. This is like Markdown enabled, you can already look in the source code. So this simplifies a bit. The same for the IIR. Then we went a bit out, because for IIR you have like 4 different possible implementations, and for thoroughness we said like, let's do all of them, and then you can choose which one you like. There's certain pros and cons for each one of them, and this is also fast, and this is also like a test bed for Matthias to see whether the new C++ standard can also improve the IIR for SIMD, because it's not quite trivial for SIMD, and this is like a test case. But this is already the standard implementation, which is fast enough. Now, note for the eagle-eyed, this is not your dad's C++98 anymore. We use stun std only feature, so we minimize the library dependencies on any other libraries other than the standard one. This is just to be easier in terms of portability, so that you can run it on embedded and also high-end computers equally, or even on your mobile phone. And while we try to use as much C++ possible, if it helps the readability and the conciseness, some features, especially ranges, we held a bit back, because we want to make sure that when we use a feature that is worthwhile and that it has to be supported by GCC, Clang, and MSVC. This is just to improve portability. Clang for the reasons because we want to be able to compile into WebAssembly. And if you want to know about, because C++ receives so much love from you, I invite, there was a very great talk by Daniela Engert on the last year CPP Con 2022, like about contemporary C++ and don't want to make more advertisement, but just invite you, have a look at this YouTube video. I think she did a great talk, and after that, I felt like, what did I do wrong for the last 25 years? So it shows really the prowess and the nice things in C++ that you can do these days. Nevertheless, Python is still core. Now, yeah, about Python. Basically, if you accumulate all the different requirements, you get, of course, a phone, for example, that can do everything. The bottom line is, from while we developed the core as C++, we didn't put Python back on a back burner, but we say, like, this is not an issue because making wrappers around the existing API is trivial. And we can reproduce the same API as GNU Radio 3.10 as of now. That's not an issue. The question is now, because we're starting on a green field in some point of view, do we want to do the Python development the same way as we have been doing it now? Or is there a possibility of improving it? Is there something where you say, like, oh, if I could, this Python, writing Python code as a block would be better. For example, if you like, say, I like this process 1 and the process bulk function just being exported, we could just export that. I'm like, there's several options. We can do it as before. We can use the reduced equivalent of what we've done on the C++, or you say, like, no, having a dedicated Python wrapper is not that important. Now with the PyPy binding, where you can generate Python binding on the fly and always of that function that you want to have, this is sufficient enough. I don't have an opinion on that, but we need your feedback on that, because please get in contact with the GNU Radio architecture team, because this is an open design and we want to make it at least equivalent or possibly better. And for this, we need your feedback, whether you want as before or better. Now, I hope I put some of your fears at ease. While the low-level code base changed, the overall course functionality stays the same. I mean, it's still the same processing framework as we love and use. But we cleaned up some of the internals, where most or 90% of the end users will never ever get in contact with. Now, some of the design principles from a high level, we all talk about software-defined radius. Software must be adaptable to frequent changes. That sounds obvious, but what does it mean, soft? Soft is very critical to this, because few are library developers, more are application developers, and most are application users. And this we have to keep in mind and always remind ourselves, we all need to know what, when, and where functionalities were implemented, and we have to share the same terminology. And remain mindful also about non-RF engineers and other applications. And the goal is that to first order, we want to have an intuitive design where you don't have to explain how to use it, but people will figure it out by themselves or can. Nevertheless, we have documentation for that and examples before domain language and before the documentation of concepts. And basically, one important thing is like mechanical sympathy. I think that's at least in our domain why it resonates so well, is because GNU Flow Graph replicates very much on how RF engineers build their own equipment, where you have like discrete blocks that are connected with SMA wires and label their inputs, label their outputs, that even if you can't program, you can understand the topology, how the signal flows through this. And maybe I should calculate the complexity, the GRC complexity for this flow graph once, but it's hopefully low. Now, what does it mean? We want to favor composition of inheritance. As you see on the bottom left, many of the processing frameworks are more like libraries where you can exchange components, but the boundary conditions almost stay constant, and you have to respect the API. We want to make it more a loosely based library where you can pick and choose which part of the components you want to use. And then if you don't want to use component, you don't have to pay for it. You don't have to pay the penalty, neither in code size nor in performance for that. So the modularity is very important. And to show let's go a bit very deep dive in why this is important, why we also used not virtual inheritance. This is a compiler explorer example left with virtual inheritance and right with the new concept. You can see the assembler that is generated is 10 times more than with the concepts that we use. And the problem is that as soon as you use virtual inheritance, the compiler can't see through the virtual inheritance because it has to assume that any function can be replaced during runtime. So each function that is virtual is potentially unsafe. And thus the compiler has to make very unsafe, very safe choices, optimization choices. And that slows down the processing a lot. And we try to minimize this as much as possible, but we still have some virtual inheritance where, for example, the plugin system for runtime where it's unavoidable. Now, some clean code-based design is like documentation. Basically, you annotate the code, you annotate the block in code. You just add some small strings with an annotation class, and then basically that carries along also all the information that you need in the UI, whether you want to see a port visible or not. You can also do like language translations in there. This is an API just as a proposal. We can still change the order of priorities and adding some more better defaults. But yeah, as you write the code, it's documented. And this we can also parse and then generate, for example, without you having to modify any other files, we can generate some text output from that. So now the bit juicy is now this is like the API, nice API, that's good and fine, but is it worth to go that? Because just nicer API doesn't convince anybody to switch over to a different way of doing things. The new buffer is basically log-free, thread-safe buffer, which can be used as a multiple observer with the classic. We used our own implementation of the disruptor pattern, which we stripped down and made it to replicate also the GR use case, where you can have this classical use of a fan out, one source feeding several things. But you can also this fan in, which is used for messaging. It's the same buffer, so not two implementations, the same code base. You can do also message passing or like a message network with the same buffer without changing. It's just on whether you allow the blocks to have multiple inputs, outputs. It's the same. And in the message, we decided on using John's PMT maps. Or you can also do multi-cascade, that you can say several blocks share the same buffer so that they do in-place modifications. And you can have multiple changes, so you don't have, you conserve a bit on your memory footprint and performance. And you can also omit the buffer. For example, if you have a linear cascade, you can write a subgraph, and the subgraph is then executed on this process one, and is handled as one single block. And that was important for us, because sometimes we have very basic operations like ×2 times a certain linear functions minus some offset scaling, and then you have a chain often of 10, 20 blocks. With the old scheme and with the push-pull system through this microservice architecture, we had a very high latency because every mutex that you hit, you get a penalty of 100 microseconds. And if you have hundreds of those, 100 times 100 microseconds is slow. And if you want to have real-time applications with less than 100 milliseconds latency, you don't want that. That's the reason why we put in the low latency or no log-free buffers. Yeah, the reasons why the hopefully positively perceived is type strict. But you can pass any type that respects copyable, movable, and if you want to do yourself a favor, make it cache alignable, so you have to be a multiple of 64 bytes, because then your CPU will treat you nicely in terms of computing performance. And yeah, this simplified the async message. How much am I in time? Okay, this is the performance improvement. Red is in the old, the 3.10, and in blue the new ones, both for the POSIX compatible one and for with the portable one, which also works on non-POSIX systems. And we got at least a factor 10 improvements just for the buffers. Main reasons is, because we use atomic compare and swap paradigm and the type strictness, which the compiler can see and can optimize a bit more. Now, the second thing that we added was performance optimization is out-of-the-box single instructions, multiple data operations. Maybe some of you know this. It's basically you have one instruction, and for the classic programming, if you do virtual, one instruction, one data reduces one results. But the SIMD is basically that you can put in multiple data and apply the same instructions for all of the multiple data and get multiple results. And that basically quadruples, in this case, your throughput performance. And this maybe in the early 2000s this was not as appealing as possible because for most of the architecture here used like the Intel, you got maybe a performance boost of a factor 2 if you're lucky. But since 2012, 13, you can get a performance boost with that at least of a factor 4 up to a factor of 16 nowadays. So if you don't use SIMD in your algorithm, then basically you only use 7% of your CPU. So you have to use SIMD, you have to optimize for your architecture. And then the question is like, how do you do that? So there we got adopted by Matthias, who's the main author and lead for SIMD integration in the C++ standard, and he wrote this extension for us. This also allows like compile time merging of blocks where we can forgo the buffers and enables the compiler to see through and optimize the algorithms. And here I have a bit of like a small benchmark. On the top, you have like the merged comparison with the bottoms. Maybe you look at first, okay, the first one, source to sink, is a simple graph of one source, one sink. You can see on the top right, we get a throughput performance of about 16 gigasamples per second. This is a bit academic, but this is mainly the memory bandwidth that you have and the cache bandwidth that you have. But this shows a bit like the overhead of the benchmark. But the interesting ones are the ones highlighted in blue, where you have a cascade of a multiplier, a divider, and an adder that is repeated 10 times, one after the other. If you do the compile time merge, you get about 250 megasamples per second throughput, which is very interesting because that's the throughput that you can get over USB 3.2. So basically, you can process all the data that you can push from via USB 3.2 in one go for a very long chain of blocks. So you can do really serious real-time signal processing and then feeding it back to your transmitter. If you don't do this, you drop to 80 megasamples per second, which is still respectable. This is still a factor 10 faster than the GNU Radio 310, which at that I forgot to clock, but we're talking about 2 or 3 megasamples per second. So that is still a huge improvement. And one small highlight, this is the example of the process 1 and process bulk. That struck me, and you're faster with that. That's not the end. With the merging, also the runtime merging of blocks, some of the use cases, we should be able to bump it up a bit more. Here, like a big shout out to Dr. Matthias Kretz. Here I name explicitly doctor because he really deserves it for his work on it. He's really the doctor on SIMD. And you should buy him a beer and support his paper and give him a shout out, a thank you when he twitters. Now, tag-based timing integration. We often deal with MIMO systems. If possible, normally you synchronize it via the same RX channel being on the same DAC. That's not always possible. On our side, we have a fairly distributed system where our SDRs are distributed over 4.5 kilometers. We won't route analog signals to the same SDR, but we have to synchronize them nevertheless. And this real world problem, how do you resynchronize physically spatially distributed sources with the same flow graph? And in the end, the solution was very easy because we already opted into tags. We just said by conventions, we generate 3 tags that all sources should produce. This is the trigger name, the trigger timestamp, and the trigger, I forgot, but just 3 tags. And these are then attached to the sample where the digitizer recognizes this, and then they're propagated through the whole network for each of the nodes. And then you can have a synchronizer plug in and say, like, please buffer the samples until this trigger synchronization tag arrives. And then you push further on with a synchronized stream, and then the rest is synchronized as you want. And in our case, we are the co-developer of White Rabbit at GSI Fair. And and integrated. That's actually all. It's now out of the box. And actually, once we've discussed about it, this was useful for the several iterations we had. It's a very simple and beautiful solution. So there's some another advanced processing features where I go through this. Okay, we use the digitizer. I showed this in the talk yesterday, a bit of modernization. Initially, we had like 2 ways how to process data, sample by sample and chunked. I think I skipped this because that's obvious why it's not important. Important is that we have like 3 types of acquisitions, sample by sample, chunk-based, but also we have transient recorder where we basically continuously monitor data, but sometimes if we see an interesting event, like if a plane crashed or we created a microscopic black hole, we want to document it for posterity to know why it was created. And we have to be precise. So and for this, we need like 3 different types of processing, which by adding this tags, this basically makes it very flexible because you can use this tags to copy and paste certain segments of your samples, and they're propagated throughout the processing chains, and then you can make data sets, which are basically aggregate, which are a bit like SIGMF style data sets that are annotated and then can be further post-processed. And you can also cut and paste certain subsections and then do multiplexed acquisitions. And there we have, in our case, we implemented multiplexed processing, 2 different types, also triggered for transient recording, or the simple continuous acquisition as GNU Radio does now. And you can do other fancy function-based processing. You can take a segment of acquisition and can treat it as a function and do like a discriminator or transient detector, and then can like Cinderella, you can divide the good data sets from the bad, have two different things, write them into different parts. You can also make feedback loops. I mean, like the original limitations of directed non-acyclic graphs is dropped. We can do feedbacks now. And yeah, this is a small overview of the packet structure. So we have the same structure for data sets, packet and tensors, which largely will replace the old PMT message, not the PMT, sorry, PDUs, sorry. But it's like basically the same design and simplified a bit. In the future, we thought like, since we can do already asynchronous processing and block-based data, maybe we can go somewhere in the same direction like Unity control system and also make like some other high-level blocks for making more advanced processing, or even like UI designs if you want. And at least on our side for our UI, we will explore that direction. So broaden cross-platform support. This is like, because it's very important that you not just develop a library, you have to also see whether it works in the application. So we have like the full vertical stack. And we have an emphasis that this framework or this library is supported by GCC Clang and Emscripten so that we can support WebAssembly. And we have like a small tech demo that GNU Radio also runs in the web, a new web browser out of the box. Now comes maybe the other interesting part, the juicy. Sorry, I'm running a bit, maybe 3-4 minutes over, but this is really important. We all know that we need like a more flexible scheduler, and depending on the domain or depending on the different topologies, you have certain subgraphs where you have different scheduling priorities than for other subgraphs. For example, if you have a subgraph that should be executed in the GPU, you need a different policy than on a CPU, or if you want to have throughput optimized or low latencies, you need to change your scheduler behavior. And there's not one single silver bullet solution for the scheduler. You have to specify for this part you use this paradigm, this policy, and for this, the other one. And in the old specification, this was basically handled as a microservice architecture, which is a valid construct, but it always involves push-pull mechanism that's very inefficient in terms of data processing. And we flipped this like 90 degrees around and said like we make now a work scheduler where the work functions is, because every CPU can only execute one function at a time. So we optimize the execution of the block of the flow graph so that we maximize the utilization of the available computing cores or the latencies. And then you can have, for example, a scheduling domain for the CPU, augmented with a scheduling domain for the GPU. And then depending on your necessities, have different boundary constraints for these. And yeah, the reason is we have like, there's not one single good solution. Unfortunately, I can't go into this, but have a look at the slide later. We made some topologies that are specifically designed to trip out schedulers, which are hard to schedule, where we know that the traditional schedulers will get into their knees. And they have different policies, and the exercise here would be, if you have these blocks, in which order would you execute them with a given number of sample constraint, and you will find that they're, depending you want to optimize throughput or latencies, the order execution is different, and you have to optimize your scheduler for that. Same as like another topology is when you have two parallel branches. If you have a feedback branch or like a path that terminates earlier, how do you handle that? You want to sync 1 and 2 arrive at the same time, or do you say like, oh, I have data already sync 2, please give me this earlier than the sync 1? Or this funny one, where many people say like, nobody uses this type of topology of graph processing. Who uses AI in their flow graphs or in their applications? Nobody? Oh, okay, there. I guess you recognize that's basically an artificial neural network, nothing else. Now we can do this also with high-level blocks in GNU Radio. Now we didn't, because there's hundreds of different possible implementations we didn't implement each and every scheduler possibility, but we did, we started off with the busy looping with this naive implementation, like the old, or the simple version that was also implemented in the new 4.0 version. Then we implemented depth first and breadth first. This comes from graph theory, just to make sure that the API that you need for writing your own scheduler is sorted out and that it works and as a proof of concept. But there are many, many other possibilities. We documented them in a README. Each of this is like the most common scheduling topologies, and there's still active research. Just by the sheer number of lists, you can guess it's not obvious one which is the best. And the next step, what we wanted to do is like to have a healthy competition, like a block coding party where we invite everybody here in the States and back in Europe to flesh out all the missing blocks. And then accompanying with that is like a competition. Who writes the best next GNU Radio 4.0 scheduler? And have a bit of, for the topologies that I've shown, maybe some additional one, write schedulers that can detect and automatically optimize these topologies and give the best results for the boundary constraints that we set. And then it's like a healthy competition, and the winner or the winners will become then the new implementation. So the example implementation was done by Alex. Big shout out to Alex. Please buy him a beer. He did a tremendous amount of work. Initially, we thought like, how hard can that be? And he spent a fair amount in making this work. And we all, I guess we can agree, we all learned a lot about, not just about the theory, but also how to put it into practice. So the overall project direction, I mean, I think Josh said most of this. We identified most of the HPC limitations in Dev 4.0. I think we addressed that. Next, for the staff prototype, unfortunately, we couldn't deploy everything for this conference because we rather said, like, do it right than do a quick hack. So there's still some refactoring to be done to make it easier, better looking. But this is, I hope, a couple of days or within a month, we can transfer this also to the from the graph prototype to the regular GNU Radio repository. And yeah, we're all based on the present GRC integration, so that we use the same file description. And we want to now also tackle the Python integration, but there we would like to get your feedback to see status quo or the new reduced interface, which maybe is easier for 90% of the users, or also in any other direction. Another thing that Josh wanted to address, but I think this goes now out of scope, is the next frontier would be also we know how to integrate GPUs. That's is fairly easy. It is more like a deployment and toolchain question to make that streamlining. But the question is like how to integrate also FPGA efficiently. And there's some ideas, thought, and requirements. So that's what I glimpsed through a short amount of time. And thank you.
So, thank you, Ralph. And I just wanted to highlight tomorrow, we will be having a panel discussion, which will be open to a lot of questions, a lot of interactive discussion about what are the next steps for 4.0. And so if you're around tomorrow, that'll be tomorrow morning. It is break time, but maybe we can take one question. And then, you know, Ralph is around, I'm around. If
Yes.
definitely seek us out during the week. Any questions for Ralph before we head off to break?
They're all silent, starting to implement blocks. Very good.
Yeah, Martin.
I know we've talked about this before, but on your slides, I couldn't see how like a multi-node implementation fits in something, your network connected distributed computers, or maybe I just missed it. But
Yeah, this is the synchronization that we do. No. No. Sorry, this is basically this one. Basically, what here are to digitize the independent digitizers hardware nodes. This can be also independent receivers via 0MQ, like pub subsync, but they still receive the tag, and the data comes in with this tag on the stream, which is annotated with, if you use White Rabbit, you can put in any arbitrary pulse, but we have also like a prototype implementation for GPS receiver, that whenever you have the PPS, you tag the UTC second on the sample, and that is carried along through the network, and then at the receiving end, you have to decide your synchronization policy, what you do with this tag. Whether you say like, I start my local flow graph as soon as I receive the corresponding PPS tag, or whether you say like, I start processing and do zero padding until the data is there. These are like on the right, the different cases, how you can implement a synchronizer module, whether you say like, I wait till everything is there. This is like the A1, B1 case, or you start processing B0 and pad for the A1 channel, or the other one where you say you force synchronicity, you have the A3 and B3 use case. There's several, there's not like one synchronizer block that fits all applications. We write these different cases at least as one block implementation, but then any other use cases can either be merged, adapted, or provided complementary to the synchronization scheme. But that in the end turned out to be, we spent a lot of time, and in the end it was very, very little code to be written for that, because once we said that we make more massive use of tagged streams, a lot of the other problems just collapsed and fell, made a simple, intuitive solution. What I also forgot to mention is the process bulk function optionally is only invoked so that the tag is always the first sample of your bulk processing. So
Oh, a tagged stream block. I have more questions, but I'll ask them later. Thank you.
Thank you,
so
Ralph.
I hope maybe there's a lot to take in. If you have further questions, maybe have a look at the slides, and you can catch me on the aisle and ask any of the people who around here participate in the code distribution some more information. Either Alex is here, Josh is here, Derek is here, and the other ones are online. I know shout out to Simon and Ivan and the others who are watching from abroad, and will be maybe also able to answer some questions online.
So it's break right now, so we'll return in 10-15 minutes. We'll start back up again.
unexpected gap. But our next speaker after the break is John Soleil. So John, I don't know if you have the slides ready. And
Hey, thanks, Sam. That was a fantastic intro. So we're going to be talking about PMTs today. And I came up with a working title several months ago of PMTs of the future, saying that I would fix it later and come up with something cooler. And as you can see, I did not. So by show of hands, who here knows what a PMT is? Okay. Okay. Who here avoids using PMTs as much as they can? Okay. Okay. We are going to try and fix that. So first off, just a little about myself. So I come from a little company called B Cubed. This is where the whole genesis of this new PMT idea came from. We're a fun little place in Northern Virginia. We're hiring. We're looking for people. So if you're interested in working for a fun place with great benefits that loves GNU Radio, come talk to me. So for those of you who don't know or have blocked it from your memory, a PMT, it stands for polymorphic type. And it allows us to group arbitrary data together, much like what you can do in JSON or a Python dictionary. The problem being that C++, being a strongly typed language, doesn't let you create variables that house random types in them, or unknown types. So this was an effort to produce that kind of type in C++. So it also includes serialization and deserialization code so that you can transmit data over the network. So if you're using the ZMQ blocks, those will convert the PMTs for you and send them on the other side, so you can keep that metadata with you. And in GNU Radio, these are primarily used for asynchronous messaging between blocks. So any message block is working with PMTs, and for stream tags. It is a standalone library. It's part of GNU Radio, but you could use it outside of that. So to kind of motivate what's going on and to show examples of how things are and how they're changing, I came up with an example somewhat near and dear to my heart. Is let's say that you are working on a spectrum survey application, and so when you find a burst of energy, you're going to do some analysis on it and figure out what you can about it. And so we're going to produce, for our example here, a super complicated structure that we're going to figure out the bandwidth of the signal, the center frequency, the modulation type, and then we're going to have an integer ID associated with it. So in GNU Radio 3.10, prior to 3.10.7, this is a way that you could create a PMT dictionary with all of these fields. So I've got my structure definition up top, and then a function for converting that structure into a PMT dictionary so I can send it between blocks. So this is using not my favorite syntax, but we create the dictionary object, and then we add one key at a time. And so there's a lot of boilerplate here. You can see that in every dict add function, I pass the dictionary in, and then I get it back out as it adds that new key in. And then everything has to be converted to a PMT as I go. So there's this PMT MP function, which is a nice magic function that says, oh, you're passing in a string, I'm going to convert this to a PMT string, or you're passing in a float, that's going to be a PMT float. So with 3.10.7, so this is fresh off the presses, there's a new and improved way of doing this. So as any good programmer would do, I commented out the original code and then added in the new way of doing it. And so you can see that there's less boilerplate now. You're able to construct the object directly, so you're still casting or constructing PMTs for every object, but it is nicer and cleaner. So if you are on 3.10.7, use this new format for making a dictionary because it is nice. So now we want to get the data out of this structure. So we're going to start with no error checking.
Test, test.
All right, I'm going to hold the mic now. All right, so no error detection here, and so I declare an instance of my structure, and then I'm going to convert one piece at a time, and so I have to know the type of everything that I want to get out. So the bandwidth is a float, so I'm going to convert that to a float, and then I ask for a dictionary reference, pass in the dictionary, pass in the key that I want to get, and then you also have to pass in a default value if that key isn't present. So in this case, I'm just passing in a null PMT, which would, if I were doing error checking, would allow me to know if the key is actually present in there. So the dictionary reference function returns a PMT, not a floating point value, which is what I actually care about. So that's why I have to convert that PMT to a float. So this is a little clunky. There's a lot of typing I have to do, and we're not doing any error checking yet. So we're going to make this more complicated in a second. So you have to ask, well, what if the key isn't there, and I try and convert a null PMT to a float? That's going to raise an exception, and then my program's going to abort, and I'm going to get the wrong type error and not know what's going on. So we can add some error checking in, and this would be a lot of code. So I just did it for one value here. So the first thing we'd want to do if this is in a message block is make sure that we're getting a PMT dictionary in. So we can check and see if it's a dictionary. If not, handle the error somehow. Then we want to, so bandwidth is our first field. So we're going to see if that key is in the dictionary. And then if it is, we're going to make sure that that value is a float, not an integer or a string or something else. If that's not true, then I can handle that error and then declare my structure, get the value out just as I did before. So I can repeat this for all of the other fields in my structure. If we've got 4 here, if you've got more, it can be a lot of code that you're typing in there. And I made several mistakes as I was typing up this example. So it can be kind of tricky to do. So hopefully I provided some motivation for why we're doing something new. But just to kind of summarize, the API is kind of inconsistent. It can be difficult to remember function names. There are, my favorite case is to convert to an integer you call from long, but if you want to know if it's an integer, then you call is integer. And that's my favorite because I mess it up all the time. So as we saw, message validation is really hard. And I have made mistakes many times where one block is publishing a message and I receive it and I think that it is passing a signed integer, but it's actually passing an unsigned integer. And there's a lot of back and forth and a lot of errors thrown and pulling out my hair. And then the interface is very different from what people are generally used to when they're writing C++ or Python code. There's a lot of new function calls to learn, and C++ has evolved a lot over the years, and in particular C++ 11 through C++ 20 have introduced a lot of really cool features that allow us to get the flexibility of the PMT structure, but have it act like the C++ that we know and some of us love. So I started this journey a few years ago, and as a side note, this problem that I showed you was very similar to how I got involved in rewriting this. So I was at my desk one day, banging my head against the wall, trying to get a structure from one block to another and having a miscoding somewhere. And I said, I'm going to write validation code because I'm a good engineer. And after I fail for a while, I'm going to write the validation code. And I spent a few hours on it and was getting more and more frustrated of, oh, why doesn't this work? Or what's the syntax of this function? Or what happens here? And I now know enough that I could do it. But at the time, I just threw my hands up in the air and turned to my coworker and said, I could write something better than this. And as I went home that night, I thought, GNU Radio is open source. I could write something better than this. So I went and I contacted, sent a message on the mailing list and said, hey, I have some ideas for how PMTs could be improved, and tried to be as polite as I could in my frustration. And I got in touch with Josh Mormon in particular, who was already working on a new version for GNU Radio 4.0. And I went and got involved with that. And so we had this original new implementation, the old new implementation, if you will, where we were using flat buffers. And I presented on this a few years ago. And flat buffers is a really powerful library that Google maintains for sending arbitrary data between code. You can get fairly high throughput in it. It's used in like a lot of video games for transmitting information about different stats or characters around. But for how we do things in GNU Radio, there's a lot of limitations. And so one big thing is that everything has to be managed in one central location. And GNU Radio has a more modular model where we have our out-of-tree modules and everyone is managing their own data. There was also a lot of overhead because in, say, a video game, you may have an item that you have all of these well-defined characteristics for. And so you can define this structure and use it all over the place. For signal processing, we kind of have the reverse thing where we have lots of little structures or lots of different kinds of structures that we need. And so defining them was not as universal. And the way that we ended up using it used a lot of CPU and memory, and we weren't using any of the powerful features that it offered. So we now have a new implementation. And the new implementation uses a C++ standard variant, which be careful if you're going to Google STD variant. So the variant, which this has been in Boost for a long time, in C++ 17 it got adopted into the C++ standard. This is a type-safe union. So a union lets you have one data structure that can represent one of multiple types. The problem is with a union that you don't know which type it is. So the variant just adds an extra field that lets you know what type it currently is. What's nifty about a variant is as you're using it in your program, you have this extra data field in there, and there's a question of what type is it at this current moment, but the compiler is smart, and it can frequently say the integer up here, and now you're using the value, and it can optimize that out. And so a lot of times you pay very little in terms of cost to use a variant. The other nifty thing you can do with a variant is you can create what's called a visitor, which allows you to write one function that can work on all of the types or a subset of types within a variant. And so rather than having to say, well, if this is a float, do this. I mean, you end up saying if this is a float, do this. If this is an int, do this. But they have a pretty nice syntax for interacting with a variant without having to write a whole bunch of code. So I threw up a little bit of example code here for declaring a variant. And this particular, my variant can be a float or an integer, and I'm assigning it a floating point number. You can ask, does this currently have a float in it with the holds alternative function? And then you can call std_get, which will grab the value out and return it back to a float. So not the most exciting example, but it's a really powerful tool for representing somewhat arbitrary or one of many types. And this is the foundation of the new PMT. In fact, the new PMT really, it is a variant with some extra functions added. So most of the types that you know and love or don't love from the current PMTs are supported. We've got integers, floats, complex, bools. You can have uniform vectors. You can have vectors of PMTs. There's a null type. There's strings. There are a few things that we left out. So before there were tuples and vectors, and a tuple is essentially just a vector. Or a pair is a vector of size 2. And so you should be able to do everything that you could do before, but the interface is a little simplified by not trying to support all of the container types. So let's go over a little bit of how you would write code that interacts with these new PMTs. So the vectors and the maps are the coolest ones, and they allow you to use regular modern C++ features. And so here you can declare a regular vector of floats and initialize it however you want. You can create a PMT from that. The next line there is I'm creating a vector of PMTs. And so these are all of different data types. For those of you who aren't aware, the curly braces there is saying I'm passing in an initializer list, which is a little different than a constructor. But what ends up happening is it's going to create a PMT out of each of those objects there. And so you don't have to have any special code. If you remember from earlier, we had to do the PMT : MP on each and every element. The new PMTs will automatically do the right thing for you. We can also use range-based for loops. And so in this case, I'm adding 4 to each element in my PMT, and you're able to access them nice and easily. There's not an overhead cost to doing that, so it's just as fast as working on a vector. You're able to compare, this is one of my favorite things, is you're able to compare a quality of a PMT to any other object. And so that will make sure that the PMT is of the same type as the object and that the value is the same. And then also it works, you can do stdc out on a PMT, or you can use format, the new format library to print out a PMT. With maps, so the code that we had from before, we've got the same example here, but using this new syntax, it is very similar to what you have in the 3.10.7.0, but you don't have to declare anything as a PMT in order to use it. So yeah, yet again, it will auto-convert everything for you. You can use range-based for loops on the map, just like you can with a standard template library map. And actually, under the hood, this is, I guess to be clear, this is a standard template library map. And under the hood, the vector is a standard template library vector. It is just stored in the variant that those are some of the options available to you. An important note is that the map is storing PMTs, and like we talked about earlier with the variants, you generally have to call an extra function to get the value out. And so you will use the standard template library get function on the PMT to get in this case, the frequency out. It is nice though, because std get is a standard library function. You can find all the documentation online for it. And anything else related to the variant, it's readily available, documented, and we know it works. And it will raise an exception if you try and if center frequency is a float and you try and pull it out as a string, it'll raise an exception, much like what is in the current PMTs. And just a reminder that you can check the type with holds alternative, and so it'd be std : holds alternative float on this, and that returns a Boolean as to whether or not it is a float. So we're going to take a little detour and get to the most exciting part of this, I think. So Ralph talked a little bit about reflection. And reflection is cool stuff, and it allows you to do really cool stuff. So it allows us to inspect. In this case, we're talking about compile time reflection. So at compile time, you're able to inspect and possibly modify things related to an unknown structure or object. Or I guess it's known to the compiler. But you don't have to prime it. You don't have to code it all yourself. So this is a really common feature in languages like Python, which lets you do whatever you feel like with whatever, Go and Java. And with the recent C++ standards, this is possible in C++. And so I created, just as a taste of what you could do, completely incorrect code. But just to explain the idea, you could have a generic structure printer where you would accept any structure in, and in this case, it is printing the name, the value, and the type. So although this code isn't valid, you can produce code that does this. It was just, there was a lot of there was some clunkiness to it, and I figured that it was cleaner to show you the pseudocode than the actual code there. So how are we using reflection for PMTs? So the whole point of my journey to rewrite the PMTs is I wanted to validate that the message I was getting in was of the correct type. And so if we remember from before, what I had to do is first make sure it was a dictionary, then go through each member and make sure that that key exists in the dictionary, and then that the value has the correct type. And then I can pull out the data. That's a lot of boilerplate. It's kind of annoying to do. And so we've automated the whole thing. So in this case, I declare my detection structure just like before, and the one piece of boilerplate I need is this REFL auto line, where I declare that I've got the type is my structure, and then I declare the fields in there that I want to be able to access at compile time. That's all I need. You can use this. You can share it with whomever else, and they'll be able to run the same code on it. So from before, I am going to create my PMT from my dictionary. And here, because I defined the structure with the REFL auto part there, I can call the map from struct function, which does everything that we did before, and it will iterate over all the members and convert each of them to a PMT and add them to a dictionary. So that one line of code converts everything for you. There's also, on the tail end, there's a toStruct, which does the inverse of that. And so one line of code will convert from the PMT back to your structure. And all of the validation is handled in that validate map function. So validate map is a template function that takes as an argument the structure that you want to validate, and it goes through and it does all of those steps. It says, is this a dictionary? Does this dictionary have the right keys? Do all of the values have the right type? And if it does, then it passes, otherwise it doesn't. And so all of that boilerplate, essentially for converting your data structure into a PMT, for validating it and getting it back out, is roughly 3 lines of code that it's been turned into here. So the hope is that this makes it a lot easier to work with PMTs, put the data in and get it back out. So benchmarks are a funny thing. So I like to wait until right before submissions are due for GRCon to start running my benchmarks. And so the first year that I was working on this, we had all of our flat buffer based stuff in there, and we ran some benchmarks right before submitting the talk. And it turned out that serializing vectors was a lot slower in the new implementation than the old implementation, which is sad because we deal with vectors on a regular basis here, and it's really common to want to transmit vectors between blocks. So I found that there was a kind of a fundamental design flaw, and went back through and realized that we needed to make some major structural changes to get that to work. So that was 2 years ago. So I spent time making those structural changes, got that to be performing much better, and now a vector copy is quite a bit faster in the new PMT than the old one. But then right before GRCon last year, I said, oh, let's run some other benchmarks. And I discovered that constructing the flat buffer objects was 100 times slower than constructing the old PMTs. And I figured, if you're going to use a PMT, you might want it to be created quickly. And it turned out that the flat buffer, the way that we were using it, was just really slow. So then we switched to the variant, and I, again, having not learned my lesson, decided to wait till the last second to run these benchmarks. But this time, they were good. So the results are much better. There are some torture or some corner cases in the current PMTs. So we know that serializing a vector is kind of slow. It is roughly twice as fast. It depends on the vector size now. The map or dictionary in the current PMT, it's stored as a linked list. And so as that grows, it becomes more expensive to access it as a map. And so there was a data structure issue there. So that has also been fixed because we're using a standard template library map. But in particular, having a map with 10,000 keys in it is not the most typical use case. So I did some benchmarks of what I would consider a more typical use case, which is you have a relatively small structure, maybe like the detection structure we just talked about. And you want to, in this first case, you want to convert and then validate it. And I found that writing the code with the new PMT and the old PMT, not only is it easier to write the code for the new PMT, but it is roughly 6 times faster. For adding in a vector, so now we've got the equivalent of a PDU. So we've got this data structure, and we've got a vector with 1,000 elements in it. That a little less than 3 times faster with the new code versus the old code. And then for serialization, for taking this same PDU, serializing it to a string, and then bringing it back out, that's roughly 4 times faster. So we finally achieved easier to use code that is also more performant than what we have now. So the library is in pretty good shape now. Ralph and the team at FAIR have submitted quite a few fixes and improvements to it, and it's getting cleaned up. There's not a ton of new features that I see that need to be added, though Ralph might have a different opinion on that, and we can talk later. But some of the things that would be nice to add, C++23 introduced new float types, and they all have names and numbers just like the integer types. So we can definitely add support for those when we decide to support C++23. With complex types, I also think it would be really nice to have we'll call it an SDR time type. So in C++, they've got a UTC clock, they've got a GPS clock, they have all these clocks. It might be nice for us to define whatever we say is an SDR clock that could pass through the flow graphs. So if we did determine that that was a good thing, that would be a great type to add there. And then it might be good to do some more performance analysis, which I can wait till next September to start doing that. But it's in pretty good shape. But if you are interested in helping out or working with it, please come talk to me. It's a fun library, and it's kind of fun to work with. So with that, if there's any questions, feel free to let me know, or I'll be here, or the guys from B-Cubed as well. You can come talk to us, and we'll let you know whatever you need. So I saw a question over here. Oh.
Real quick, you mentioned serialization and that it's faster. What can you tell us about the serialization format, and is that more or less efficient than the current serialization in terms of space?
Yeah. So the old PMTs were stored as std any, and so that's a void pointer with some type safety features to it. And so to convert, say a map to the serialized format, there's a lot of pointer indirection that you have to do. Because things are now stored directly in the variant, access is a lot faster and easier. The format, which I do need to add some documentation. So if anyone loves documentation, come talk to me as well. It is a fairly tight packing. So we are packing the bytes necessary to store the data. And then there's a small header that I think is roughly 4 bytes per element. And there's a continuation field, kind of like in Unicode, for if you have a vector of elements that you can have a subheader to put that in there.
One more question for you. In the validation, do you require all of what's in that structure or any? Are they optional?
Yes. So there's actually a Boolean flag you can pass in for whether or not it needs to be exact. So right now there's not if it matches some, but you could allow for the dictionary to have extra fields that were not defined in your structure, so you'd be able to combine things together, and just based upon that flag, whether it has to be exact or not.
Thanks. Let's thank our speaker again. We're going to move on to some lightning talks. Okay, first speaker is going to be Megan Lambertson. Excellent.
Hello. Can you guys hear me? Just also take it off. Can you guys hear me now? Okay. All right. Curiosity killed the cat. Have you guys all heard that phrase before? Curiosity killed the cat. It usually means you're asking too many questions, you're being too nosy, you need to mind your own business. It's really a warning that if you keep digging in to whatever topic you're focused on, you could get yourself into some trouble. I think it's a really interesting phrase because so often in our society, especially in the STEM fields, curiosity is both presented and perceived as this really great thing, but I do think there are some ways curiosity can cause you problems. Curiosity is defined as a strong desire to learn or know something, and it's really easy to start with a simple Google search or a YouTube video on something like, what is an SDR? And then fall down a rabbit hole, only to reemerge hours later with some new pesto avocado toast recipe and no sense of how you got from point A to point B. Definitely not speaking from experience on that one. On the flip side, I think on the flip side, if you restrict your curiosity too much, you risk missing out on something that could be really great. There is a happy middle ground here that we at Rampart Communications like to call tethered curiosity. I think a good example of tethered curiosity is Henry Ford and his Model T car. Most people think Henry Ford invented the automobile, but that's not actually true. The Model T came out in 1908, and there were several decades of precursors for gas, electric, and steam automobiles all over the world. But cars were expensive, and they had to be custom built. In 1907, Henry Ford announced that it was his goal for the Ford Motor Company to create a car for the great multitude. What Henry Ford did, that his predecessors could not, was find a way to mass produce cars at speed. His real invention was the moving assembly line. And that is the magic of tethered curiosity. He was focused on his goal of getting cars to the people, but not so restricting that he limited himself to solutions inside the automobile. I'm Megan. I'm a technical writer at Rampart Communications. We're a small business building fundamentally new technology at the intersections of digital signals processing, information security, and cryptography. We are so excited to be here as a sponsor for the 3rd year in a row. GNU and open source projects in general are things that we care deeply about, and I think that stems from the fact that we like to hire people who make curiosity a lifelong pursuit. We have a mission statement, vision, and values like every other company, but one of my favorite things about working at Rampart is that we also have a set of guiding principles that we operate on. Our founders spend time with every new employee during orientation and onboarding to talk about the guiding principles and why they're so important to us. They're what our culture is built on. And the one that I have really only started to touch on here today says, science and technology advance through tethered curiosity, principled audacity, focused whimsy, stupid questions, and thinking deeply of simple things. Curiosity is powerful. It leads to discovery, it triggers innovation. Curiosity sets the stage for learning and growing and improving and finding ways to better the human experience. Without curiosity, Henry Ford may have never invented the moving assembly line. We may have never seen the printing press, the telephone, refrigeration, or transistors. And with the right focus, the right parameters, with tethered curiosity, we could change the world. Rampart has a booth set up over in the expo hall. We're hiring, come build with us, or stop by to talk about pesto avocado toast. It really was a good recipe.
All right, thank you, Megan. Yes, and please visit Rampart in the expo hall, and they have been a sponsor here for the last few years, and we're very appreciative. So thank you. All right. So next up, we have a lightning talk from Samantha Palazzolo. So we'll take it away.
Let's see. Okay. So first of all, I just want to say for Megan, I loved your topic of curiosity. My personal motto is curiosity killed the cat and satisfaction brought it back. For my lightning talk, a while ago I had given a presentation to a local ham radio club about GNU Radio. And in the process of doing that, I spent, I don't know, 90% of my time, let's see if this works, on this. Kind of got stuck in this rabbit hole. And yeah. And after Eric's talk earlier, I thought this may be an appropriate slide to bring up. So this, I really do mean I spent like 90% of my time on this. It was a very interesting journey. So I have here some dates. And also, the other thing you'll notice is that it's very heavy towards the beginning because I ran out of steam somewhere, yeah, I think in 2015. And I was like, I'm done. But very proud of the work. And I do actually have the next slide, like the references, lots of Wayback Machine things. But yeah, I was able to track down, you know, at least for me, the starting kind of date that I could find was when GNU Radio registered on Savannah. And I'm going to read these quotes because they were things that I really enjoyed finding as I was working through things. So this one says, we're moving the analog to digital converter as close to the antenna as we can get it, and then handling the rest in software. And I think that's a pretty good description of some of the goals that the SDR community has set for itself. And the other, let's see, the next that I have, I know this doesn't cover like the first meeting, but at least like this is the when Matt Edis shares his idea for the ultimate SDR with the GNU Radio mailing list. And I can't read the entirety of this one. Is there a chance that, yes, you guys are the best. Thank you, AV team. Can we just do a quick round of applause for AV, who's awesome, been so great. It's ASU AV right there. So let's see. I've been thinking about SDR for a while now, both as a ham and an EE in the communications profession. What I would like to build is the hardware for a generic SDR. So these are some of the beginnings that I was able to kind of dig through and find. Also have here, what is that, January 7th, 2007. So this is quite a few years after, you know, some of these original you know, after GNU Radio itself kind of began. And we have Joss Blum, who puts forward this idea of GNU Radio Companion, or GRC. So I've been working on a graphical interface for GNU Radio. Anyways, those were some things that I was able to, as I went Wayback Machine and things like that, that I was able to uncover. And I thought, you know, Eric, that you may appreciate this timeline. As I said before, obviously we have a few of the people who came to lead, and like I said before, like I don't cover here Derek and all the other people. Actually, no, did I put Derek? I said, oh yes, that's right, because Derek was the first elected president of GNU Radio. Before it was like the benevolent dictator, right? So it was. So Eric, and then Tom, and then Ben Hilburn, they were all the project leads. They were our benevolent dictators. And then our first kind of elected by the General Assembly was Derek Kozel, who you guys saw or have been seeing throughout the week. Yeah, so wanted to share that briefly. And like I said, here are all of the links, but it's in a PDF, and we'll post it somewhere. I don't know how much time I have left, because I wasn't, yeah. But I just wanted to share a couple things. I may do a lightning talk tomorrow, but I actually highly encourage someone else to do lightning talks. They don't have to be super formal. But I just wanted to share, like when I do SDR stuff, this is like my quick setup, my favorite setup. You know, just RTLCRs, which I know for a fact, there are a lot of them around. If you need to get your hands, if you would like to get your hands on some hardware to try some stuff out, I really like GQRX as a install, but like I said, this originated as like a ham radio presentation. I took a lot out, but I wanted to share these things. If you don't have SDR hardware or software set up, there's also some cool things that you can look at. There's something called OpenWeb RX. So these are radio receivers. And this is an old slide deck that hasn't been completely updated. I didn't double check to make sure everything still works. Another, there's no live demo, but another example is the SatNogs network. That's a place where you can go and, you know, not only get, I think, the IQ files, but also they have some demodulation available there. So there was, I think that's just about that. The rest of the slide actually had to do with being able to, in your browser, view things, but I have not properly updated it for IQ Engine, so we'll see if I'm able to present that tomorrow. But yeah, so thank you very much for letting me do my very thrown together lightning talk. I guess I'll introduce our next person, which is Clayton Smith, to give us an update. But before he does that, real quick, just want to do a quick announcement. We do have ham radio exams going on today. We have, cannot remember the name of the local ham club that has offered to give the tests. The exams are $15. I think cash is preferred. But it's basically open to everyone. Even if you didn't fill out the voucher online or whatever it may be, it is open. Make sure you go to the GRCon website and look at the details there. It tells you everything you need to know. But I really encourage people to just give it a try. I'm not gonna lie, I studied for my technician, so I did okay. I continually take my general, and I fail at that a lot because I don't study. But it's $15, so it's, it does cost some money. But I encourage people. What? Yeah, you just study. Okay, well, not everyone has time to study. I'm just saying, it's worth at least trying if you're able. Okay, here, Clayton, tell us what's going on with CTF.
All right, let's see how the screen share works. There we are. So we continue to have tons of action in the CTF. We are now up to 55 teams that have at least 1 point on the board. A lot of those teams have joined over the past day. You still have about 28 hours of competition time to get yourself in and start scoring some points. So let's have a look at how our top teams are doing. In first place, we have Andro Computational Solutions. Second place, Aerospace Team Platypus. Third place, Flamewires. Fourth place is Registration Desk Night Shift. 5 is Caliola Engineering LLC. 6 is There's No I in Idiot. 7, Kinap 35. 8 is Team Natalie. Number 9, Not the FCC. And in 10th place is 509. And if you look up here at the top of the scoreboard, you can see the top couple of teams are very close. So there's not much separating them, and there's intense competition happening right now. There's still plenty more flags to be solved. We have about 4,200 points total, and our top team is about 2,000 points. So there's still lots more to be done over the next day and a bit. So I hope to see everyone at least drop by the CTF room. It's just out the door and to the right. Drop by, and we'll show you how to get started. Or you can just go open up your browser and go to ctf.gnuradio.org. And there's a sign-up page, and you'll have the challenges, and away you go. So hope to see you there.
Hey, Clayton, I just want to put a plug in. I have a team. I'm looking for people to do points for the team. Yeah, if you're interested and you're looking to help get points for a team, yeah, come see me. We're not in the top 10, or I don't even know if we're in the top 20. But if you want to help make that, sorry, Clayton.
Absolutely. You don't need to be a team of one. So yeah, talk to Sam or drop by the CTF room. There's plenty of people there who would probably be interested to have you on their team. All right, so we'll see you in the CTF.
So thank you, Clayton, for running the CTF this year. And lunch is served in the expo hall. And we are going to meet back here at 1:15. Talks will resume again. So a little bit longer lunch. So enjoy.
Cruz to give an update on Cyber Ether. And just a reminder, there are lightning talk slots open today or tomorrow. And don't forget about the social tonight. There's information that was posted about it on the schedule, and it's like a short Uber or drive over.
Hello everyone. Today I'm going to talk about my personal project called Cyber Ether. For those who attended last year, I also gave an introduction in Cyber Ether, a very, very different software than that is today. So I figured that would be great to give an update here. It's called a metal hardened GPU accelerated interface right now. So a brief summary of what I'm going to talk about is to just say a word about why heterogeneous computing is currently important and why will be more important in the future. And then how Cyber Ether came to be, a brief story, the evolution of the software, and also where the Cyber Ether is at this moment. And finally, a little bit on how it works. I won't get into too much detail because that would occupy like 2 hours of talks, and some future remarks. So I believe most of you know about this very popular processor is Apple Silicon M2 CPU, GPU SoC. And heterogeneous computing is important because if you're just using the CPU, you're just using a tiny fraction of your silicon. Just this red box here is the CPU cores, the 8 cores, and 2 efficiency cores are contained just that piece of silicon. And if you want to use the whole extent of what you're paying for, you will need to use other things like the GPU that is in the green box here, much larger than the CPU. So, and the other silicons is SRAM, caches, and also the NPU that Apple currently doesn't let us to use directly. So it's important to have heterogeneous computing if you want to get your value from your hardware. And also, it's important because some algorithms can't be accelerated, are very hard to be accelerated on the GPU, like closed loop systems. So if you can share your memory between your CPU and GPU, you can use the GPU on algorithms that it's very parallelizable and get the same memory that your GPU was processing and process with the CPU much more efficiently, like closed loop and other PLL-based synchronization methods. So it's important to know which what to use for what purposes. So a little bit of the story of Cyber Ether right now. So everything began when I started to try to learn how to use WebGL in 2021. I wrote a very, very brief working example of a waterfall and also a phosphor-like spectrogram that you can see in the left. And also, then I decided to take this from the browser because WebGL at the time was very limited and still is. So I started to develop the thing with like native OS. And I said in that tweet that I would focus on trying to run this in most hardware possible. And then I started to use QFFT, that is the NVIDIA library for FFT, that is GPU accelerated. So I integrated that with the same code that was running on the browser. Now it's running it natively using CUDA. And then Dav sent me a reply and said, can we put that on an out-of-tree module for GNU Radio? And that's what I did. So there you go. We can use like Cyber Ether with a block on GNU Radio, and you have GPU acceleration. And also, I came back to the browser and ran the same, exactly the same code that was running natively on the browser using WebGL at that time. Then last year conference came, and this was a little bit more mature. This was the interface at that time. So you can see there the line plot and also the spectrogram and the waterfall receiving a DVB signal from GNU Radio. And after the conference, my goal was to run this on the most number of devices possible. So by December, I had a working example of CyberEther running on an iPhone. So this is completely GPU accelerated, the FFT powered by VK-FFT with the metal backend and also some kernels, multiplication kernels, complex multiplication. Apple doesn't offer facilities or header files to make this easier. So I had to write my own arithmetic header that is close to cucomplex.h for CUDA, for those familiar. And also in the right there is an example of this being used in the field by detecting a microwave. I was at a facility where they put the microwaves inside cages for electromagnetic purposes to shield the emissions from the microwave, but clearly that was not working very well because I was able to detect it with my phone 10 meters away. If my phone can detect it, the telescope would do. So that's where it is working on the telephone. And also, a bunch of people last year tried to run CyberEther on their computers, and they couldn't because most of the attendants probably use Linux, so I didn't have a Linux backend at the time. So I later, a little bit early this year, I developed the Vulkan backend for CyberEther, so you can run that on Linux and also and the orb, I like the orb. It's like a constellation, but different. So Paulo Dutra on Twitter took my code, the Vulkan code, with Vulkan backend, and tried to run that on Windows. There were some patches that he had to do to make it work, but you can see there working on Windows. So it's very lots of all the major platforms, but there's more. So Vulkan also have the Raspberry Pi 4, the Videocom 4 GPU also have a Vulkan driver, and that is open source and works on Linux. So that is the CyberEther running on Raspberry Pi 4 in full HD. It also runs in 4K, but it's asking too much for that little GPU to work with. But wait, there's more. So I took my project from 2021, 2020 that translates WebUSB into libUSB, so you can talk with your device throughout the browser without even changing the libraries. So you can use librtlsdr or libaerospy to talk with your if you're SDR using the browser. No installation required. And this time, instead of using WebGL, I am using WebGPU. That is much better. The modern GPU programming paradigm for GPUs, for graphical interfaces at least. So this is completely the same code using the WebGPU backend. So we have 3 backends, Metal, Vulkan, and also WebGPU. And those 3 can support the vast majority of devices in the world. So I think that was accomplished, running this whenever I want. This is the state of art CyberEther. So you have there's I believe 30 or 60 megahertz. I can't read. Yep, it's some more there. I think Lime SDR and receiving a LTE or 5G. I'm not sure. So, but wait, there's more. This was the where I publicized the state of the project. But right now, I have something more exciting to show. So let's start with this. Okay, so I can't zoom out, but this is the CyberEther running with with a graph interface, a nodal-based graph interface that you can access with CyberEther. So you can, here, I'm not sure if you guys can see, but it's saying that it's 244 megabytes per second being processed. This is the buffer state, so no buffer being overwritten, and then this controls the frequency. But the interesting thing here is that you can interface with the nodal graphs and also have the other and have the interfacing with the nodes. So that makes things very fluid. The scaling is a little bit weird right now because scaling turns out very hard with Retina displays. If I get this, I can add a new module here by dragging and dropping a new module. So I will add another waterfall here, and then I can like radio, and then I can drop here, and this will spawn another module. Can click preview, the same thing. But the ideal thing here is that you can, so yellow is CPU, purple is metal, and other backends have different colors, and you can do this change on the fly by right-clicking and clicking metal. And that will instantly translate from CPU to metal, and you can use your whatever backend you want to use. For example, if you don't want to use the FFT on metal and you want to use the FFT on the CPU, you can click here. Everything gets reloaded. You don't even catch the difference. And the same thing is if you break a dependency from other nodes, it will immediately know that it is broken and stop the flow graph. So there's no start and stop. It's always running. If I relink this with the other module here, it will start again, and you don't even notice. And if you are, no, let me get the spectrogram view here. Drag and drop, same thing, and then you can connect. Oops. Okay, and then preview, and then you have their spectrogram there. If you want a more traditional visualization, you can create detachable windows here and there, and then create a new stack here. There's another workbench, for example, and put them whatever you want. So this and that. And then you have a very similar, familiar interface that you can use with your signals. Another example that, before that, so if you hover here, you can see the pointer of the memory being used. They are all static, so you will always receive the same pointer to process. So you don't need to worry about that. If you want to do some actual DSP, you can try to run FM. I can't show the audio being demodulated here for copyright reasons, but this is the same thing, but you receive the signal here, you pass through a windowing, then FFT, then you apply your filtering, and then you get a single FM radio from that whole spectrum. And then you can demodulate with FM and then pass your auto buffer. That's the same thing that works on other platforms. Just drag and drop. For example, not sure if it will work, but the same code can run on iPad. Can you guys switch the monitor, please? No, okay, yeah, sorry. Okay, yeah, I can do this, okay. Yep. All right, so if it's an iPad app, it's running natively on the iPad, so if I click here, it will communicate with this orange box down here that is transmitting the signal with Wi-Fi. And you can do with Apple Pencil or touching the interface. It's very fluid. And you can work on the signal like you would on desktop. So if you can want to change the metal interface, just click here. It's metal. If you want to disable the module, you can. If you want to disable all the modules, you can very easily, no problem. And adding modules with this star here, the idea is to add more star in the future. So that's the same code running on iPad using GPU acceleration. If I stop sharing, so to prove that this also runs on the browser, I have here a browser. If I navigate to this address that is currently local to my machine, I have a RTL SDR connected to the USB part of my laptop. And if I click on this button here and select blog rtlsdr.com SDR and connect, and then reload the page, the browser will start communicating with the SDR using my translation layer, and then you can see the samples being fed to the browser. No installation necessary. It can run on CPU at the moment, but GPU acceleration backend for the compute modules will be added very soon. And the same thing here. All the functionality is the same. It's exactly the same code running on the browser and running on whatever else. So it's very flexible. So back here to the slides. So CyberEther itself. So it's made to be, as you guys can see, a portable and heterogeneously accelerated GUI for radio signals. It's built from ground up using for signal processing. But right now with the graph computing systems, you can also apply some machine learning in the future, maybe, I don't know. And it tries to run as close as to the metal, quite literally this year because it's running on metal. As possible using heterogeneous APIs and also very minimal dependencies. I believe that reducing the numbers of dependencies is good because I don't want to break my stuff because others break their stuff. And local duplications because you have, you can create a module that is kind of like a here block, so you can have a symbol of modules into a bundle and just expose the bundle to the user. So the processing, the DSP can be reused on lots of blocks without rewriting the code. And it's also easily adaptable for third-party projects. If you have an iOS app or a Windows or Linux app, you can use like the MA buff or metal surface to put in your app, just that visualization without the IM GUI thing. So it's malleable, and also the main components here is like the flow graph that is quite new. It's based on IM nodes with a little bit of modifications for it to accommodate the graphs. So you can do whatever you want there. I plan to add more examples like multi-FM demodulation with the graphs in the future. Yeah. So also line plot, you guys saw. The waterfall, that you're guys familiar, and also the spectrogram. Arguably not a good name, but it works. And also the constellation that is also called as ARB. So why and how? So it's accelerated graphics at very low level. We are not running over Qt here. We are not using any other graphical interface. We are using raw metal Vulkan and web GPU to draw the things. So we can have a very, very large flexibility on where we run this and how we run this. And also the same thing applies to compute. we can use CUDA or Metal or Vulkan or Web GPU to do the processing and support the most number of hardware possible. And as a fallback, we have CPU compute made to run when your computer doesn't have a powerful GPU or stuff. Dependencies are not mandatory, so when you're building the project, you don't need to install all the dependencies to build. Just the minimal dependencies, like one graphical backend, one compute backend, and also some very, very little dependencies for it to build. So again, low code duplication here, and the graphical modules are built upon a very abstraction layer that abstracts away the API. So the same code that you program a module will be applied to Metal, Vulkan, and Web GPU with this abstraction layer. It's a render. It's a very 2D optimized render, so nothing. You won't be running AAA games with this render, but it's optimized for your graphing needs. And also, instead of writing a new shader for every single backend, I implemented a transcoding pipeline that takes the GLSL and then to compile that to SPIR5 that's used by Vulkan. And that SPIR5, the same SPIR5 is transcompiled for our Metal shader language, and right now for WebGL shader language, there's another thing. Yeah. So this is called Jetstream render, and the back end can run. It can be selected in runtime. So in theory, you can change your graphical backend without even close the program. So I thought this was a design requirement more for the compute, but also applies for the graphical backend. And also the compute, if you want, as you guys can see, you can run your modules. One module that doesn't run particularly good on GPU, you can mix and match your backends, and that's completely supported. The internal graph solver will take all the dependencies between the modules, dependencies being the buffers, and identifying if that buffer goes to another domain. Because if you're doing like a Metal graph or Vulkan graph, you have a bunch of kernels being instantiated asynchronously, and you don't need to provide implicit synchronization between them. But if you are mixing and matching heterogeneous GPU acceleration APIs, you do this explicitly. For example, between Vulkan and CPU. If you have a graph that has a vector coming out from the Vulkan graph and going to a CPU graph, you need to synchronize that explicitly before executing the CPU graph. So this is all taken care of by the graph solver. Very, very low, high-level review here. It takes the raw original graph that you see at the interface. It will unwrap the bundles into a bunch of modules, and then it will take the modules, see if you have multiples, direct cyclic graphs. If you have multiple, it will run them independently without dependencies. And then each subgraph will be broken further into backend graphs. For example, in that image, you can see the first one being metal, and then you have you can instantiate 3 at the same time using the same dependency, metal, and CPU. So you can run the first 4 metals and then synchronize and run the CPU one. And that's what the graph solver will do for you. It's completely transparent to the user. And other example, more trivial, you just metal, CPU, and all the 3 metal afterwards. So yeah, it's front-end agnostic. All the visualizations are rendered in headless frames. So you can use CyberEther in a headless mode and just send the frame throughout the network if you want, or just run the CyberEther in another other program, and then use the MA buff on Linux to to transmit your texture and display your texture in another process. You can also integrate with Qt, Cocoa, and MTK View. That's what I do with my Apple application. I'm planning to also have an Android application next year, and it's easy to run whatever you want. So as a future, I am planning to so this is currently all supported devices, practically almost all, and some of them can run multiple of them. For example, Mac can run Metal and Vulkan with Molten VK. iPad, the same thing, and also Linux can use either the Vulkan or Web GPU program to run CyberIfer. So very also, graphical modules, you have Metal Vulkan Web GPU and CPU plus render. That is more like CPU rendering. Not great, but it's good for the debugging things, so I maintain that. Current status on compute modules, currently CPU and Metal with the compute, but I am planning to make a unified compute backend with additional supported languages, for example, CUDA Vulkan with a K, not a C, and Vulkan Web GPU. And that will try to break even further the graph, so you can take like two multiplications and merge those kernels into a single multiplication, single kernel with two multiplications, or even broadcast the arrays between like a multiplication, and you have a filter for each module, and then you can broadcast the filter with the input and get a more efficient way to run those. And for the near future here, make CyberIfer available either on iPad and iOS applications. I already have a working app, as you guys can see. I am planning to release that with test flight in very soon, and also a release on the browser like cyber.luigi.ltd, my website. You guys can, in the future, will be able to use your RTL SDR and build your own grabs, and also increase the reliability of DSP reliability, fidelity. There's no demo. Yeah, so thank you for listening to me. This is not the end of CyberIfer. I'm planning to adding more features next year. I hope to see you all to hear that next year. If you have any questions, thank you.
Yeah. I had one question. When is this going to work with GNU Radio? Or I don't know, is it going to replace it, or is it going to work with it? Because it was awesome. Oh, I was just kidding. I'm sorry. Derek gave me the meanest looking face when I said replace. When is it going to work with GNU Radio, do you think?
The out of 3 module is there. I didn't update it in a while because I was trying to make this work for the conference, but I will.
Or someone else could.
Oh yeah, GRCon23. Go there.
Time for one more question. Anybody? All right, with that, let's thank our speaker.
Thank you.
Professor Bliss here. So it's my pleasure to introduce our next speaker, Professor Bliss, who's the director of WSCA. WSCA's the host of us here at ASU. Professor Bliss, in addition to being the director, he's responsible for a bunch of foundational work related to MIMO radar, MIMO communications, and RF convergence. And we're glad to have him here. You're going to give an overview of the history. What is this? Yeah, a bunch of stuff.
How's it going? I think I'm the significantly post-lunch infotainment. So I will not have anything which is explicitly GNU Radio, but lots of things that I hope tie into GNU Radio in the not so distant future. More specifically, I'm really sort of saying you're in the right place, because this the sensibility of software-defined RF systems is clearly the future, for lots of reasons. All right, so yeah, you saw I do a bunch of stuff. We'll talk about this as we go along. All right, so if we think about the future of needs, you know, I have this sort of thing where this cartoon of a smart sort of city with integrated sensing and communications. Not long ago, this was all sort of just academics talking about doing stuff, and now there's a fair amount of interest, which you can see going into 6 and future G, about how do I use RF energy in more intelligent ways. I'll come back to this as we go along. So what else do we want? So we want more functionalities, of course. We want everything to be more flexible, more useful. We of course want lower cost, size, weight, and power. I was amusingly at a meeting now 2 weeks ago, where someone's solution for a radio system was going to cost 100 kilowatt, or sorry, a kilowatt, and I was like, you can't do that. That's burn your hand off. Anyway, so next generation of wireless systems. For reasons we don't understand, we're going to hook up everything to the internet, including toasters, which that's a real thing, by the way. That's not like a cartoon toaster. There is an internet toaster. Clearly, we're going to integrate in our base station systems or cellular systems into satellites as well. You can just see that. You can already see people starting to move in that direction. Autonomous vehicles. There's lots of P&T issues, communications, reliability issues associated with that. Once again, people are spending a lot of time thinking about those sorts of topics. Augmented reality is a really interesting problem because it's a mix of local processing, local P&T, and then stuff that's far away. And so I need to worry about communications, I need to worry about how this stuff working. And the loads are all going to be dynamic, and the applications are all going to be dynamic. The notion of a single function system will not survive very long. One of the things we do in my lab is we generally call cardiac radar. So we do use small scale radars to estimate things. We can actually, the blue line you see there is an individual heartbeat measured remotely using a radar. So we measure the R-to-R intervals. We actually now have papers where we have measured the sound in the chest remotely using a radar. Anyway, you can imagine using the RF front end for a cellular system. Now it's multifunction. Your phone could also be measuring your health remotely and in ways that a wearable system like what's on here just can't do. And then, of course, we sort of enjoy cats for some reason, and so you know at some point we're going to have some augmented reality cat simulation system, which is going to lay over the course of your real life. You can imagine cats all over the place here. It's just going to happen. It's not my fault. All right, so thinking about what the future holds, right? So we're going to have multifunction systems. I'll talk about that a bit more. We're going to have integration of cellular systems from the kind of traditional cellular systems and satellite systems. It's going to be always best connected, right? You're going to be moving through these systems, and you won't even know what's going on. Once again, from your perspective, this is a highly dynamic, flexible RF system that you have to have. How do you actually do all these sorts of things, processing the RF signals, constantly changing, right? Right now, the modem processor in my phone, while incredible and a work of art, can do one thing, right? It literally switches to a different processor if I switch standards. Forget about trying to switch really fundamental things that I'm trying to do. Distributed coherent base stations, these sorts of things are coming. I'll talk about that a little bit more. And then, of course, we're back to the internet toaster for some reason. So when I talk about the idea of spectral convergence, once again, this is where GNU radio capabilities come into play. I want to do multi-function systems. I want to be able to enable functionalities that I didn't even realize were available before. So once I start mixing sensing, positioning, navigation, and timing, and communications in a flexible RF use environment, right? I open up applications that people didn't even realize were things that were possible before, right? So my phone is now a radar. I'm actually can potentially sense the attention of people that are watching me by watching the fluctuations in their heart rate, right? I can maybe have the sensing of augmented reality, identify the people that are falling asleep. I know who you are. Out in the audience, right? while it's augmented because I'm doing the sensing of the RF energy all at the same time. It's overlaid in what I'm doing. Very precise positioning, navigation, and timing, which would be required for doing interesting augmented reality, right? I'm going to try to do all these things. To do this, though, and do this intelligently, I've got to do this very flexibly. And, of course, so it doesn't have a kilowatt sitting on my forehead. It has to be incredibly efficient, right? So we need to sort of solve all these sorts of things. And when I have multiple RF functions happening simultaneously, I want to improve the overall system of systems performance, not have these being competing systems that degrade each other's performance, right? So this is an active area of research right now. There's certainly examples where we've made lots of progress. We can do simultaneous communications in radar. We can use communication signals to do radar. Things that historically would have been considered interference that causes the entire system, both systems to fall apart, we easily disentangle now. So multi-functions in the same spectrum we can do. All right. So I sort of already talked about the idea of having simultaneous, using my RF system, my millimeter wave front end for gesture control or being able to use it as a radar. There are lots of automotive applications. I'll talk about one in a second. And then there are lots of military applications as well. All right. And these ideas are all enabled by recent technical advances. Some on the RF front end side, which I will talk less about because I'm more on the algorithms and computational side. But all the RF front end work is incredibly important. But I think you're probably more on my side as well, trying to figure out how to implement algorithms on computational systems. All right, so just once again to sort of motivate this idea of I would like to have a simultaneous system or a system that does multiple functions simultaneously. So some of you may know that there is a standard for how cars talk to each other. It of course is an entirely separate system than the system that cars have, which are pointed at each other, which are radars. If you think about it for just an instant, you're like, why do I have a full system intended to point at the car in front of me? But when I want to talk to the car in front of me, I'm going to build an entirely independent system to talk to the car in front of me. It makes no sense at all. But our radar system is not built so it can talk to the car in front of me because it's too dumb, right? So it's a clear opportunity. The RF energy is there. We can do all sorts of things there. So imagine a scenario where we have multiple vehicles. We have some legacy vehicles that are not connected to the network. We have vehicles which can talk to each other. In this particular case, I have a legacy vehicle that's going to run a red light or whatever it is. And the car behind it, which is tracking it with a radar, goes, I see that car is going to run the red light. I can simultaneously use the same radar energy / comms energy and talk to the other car, which is now here vehicle 2. And while I'm talking to it, using the same energy that I'm using the radar in front of me, I can also do relative P&T. I can get insanely precise positioning of that vehicle because it's working with me. So it turns out if you do timing strange techniques, two vehicles are talking to each other, you can get timing. There was a discussion of actually doing distributed coherence. It's the same sort of technology as that. We can do that over RF. At the same time, that vehicle number 2 can then talk to vehicle number 3 and say, there's a car running the red light, you can't see it. It's hidden by the building, but it's coming, and I want you to be careful. All right, so in order to do this, you have to make some trades, all right? This is just a notional theoretical result, but I can do everybody's favorite radar waveform here, which is chirps. So I can do various pulse chirps. I can actually do the communications we're using pulse position modulation. I can do the relative P&T between the vehicles using same sort of techniques. In this case, I assume that it's not particularly intelligent system, and I'm separating some of the users by having different spectrum. And then what I can do is I can do an overall system optimization where I get really good relative positioning, really good data rate, and really good ranging from the radar information as well, right? And it turns out that I can work out the theoretical performance bounds, and I have this manifold of theoretical performance bounds, which are pretty close to being achievable, where I can move along there depending on what my system needs at that moment, right? And so in general, this is one of the things we think about, which is I have multiple functions. I'm going to figure out what the manifold is, and what that manifold is of joint operation of all these functions, and then my system can move along there, and my RF system has to change its functionality and its processing dynamically to deal with this. So So once again, software-defined RF systems are the only way to do this. All right. So we're working through this. This is a real thing that we're thinking about. And once again, I already said it. This is why you're in the right place, which is thinking about software-defined RF systems is the right answer for like the future of how we're going to use the RF. We already talked about the range of broader use. So one of the concerns here that immediately comes up is everything I'm talking about is relatively expensive computationally, and it needs to be flexible. So you know, if you think about sort of types of solutions for processing, currently we're sort of in trouble for lots of systems. Like, so when your phone is downloading the 4 simultaneous cat videos using 5G, you feel it get a little bit warm. The modem processor is actually burning about a watt. So it turns out the answer, the limit you can actually have is about a watt. So if you use a general processor, this is a disaster, right? You can't put it in a little package. So that sort of processing doesn't work. And you can actually think about, well, what about FPGAs, the next step up? Certainly an improvement for a certain class of things, but still FPGAs are very power hungry, and don't make me make fun of GPUs. So, you know, great for what they do, but once again, still a wrong answer. At least not what we want. We would like to be able to get something close to that modem processor, which we all grown accustomed to, but it's single function. It can only do one thing. You change it a tiny bit, you have to go buy a new phone. All right, so that's what we're thinking about. So if you take a look at the computational performance in terms of power, so I would like to do something interesting. Interesting things are half a teraop per second, right? Really interesting things might be several teraops per second. Right? So you know, serious problems. You're trying to do that with a general processor, right? It's hundreds of watts. Your phone, once again, the modem processor in your phone gets to do it for less than a watt. And because it's single function, it's designed to do one single thing, that does it very efficiently. And what you see on the plot in the upper right is sort of a surrogate for time, which is actually node or feature size on the IC. We are now heading towards 3 nanometers. Most of our work, by the way, is at 12 nanometers. And you can see that the full custom ASIC is more than 2 orders of magnitude more efficient than the general processor. And basically everything else still doesn't work so well. So we have had a DARPA program for quite some time where we've been working on doing a processor, working on developing a processor to try to address these problems. And in general, you can't. I mean, general processors are rather power hungry because they're general processors. They got to solve all problems. And so there's this trade. So the trick is to recognize that there are a domain of operations. And if I focus on a particular domain of operations, in fact, there are a small number of computations which are the expensive ones. And there's lots of busy work, right? So that's the idea here, which is if I take a look at a multi-antenna receiver system, it turns out expensive things are matrix multiplies, QR, back substitution, the forward error correction, and filtering, and these sorts of things. And then there are a gazillion other operations which in fact are really boring and don't actually take a lot of effort. So the answer is clear. Make the hard stuff efficient and don't worry too much about the rest, right? Don't sweat the small stuff. Okay, so that drove us to, there we go. That drove us to designing a SoC with an architecture, which is a coarse scale heterogeneous processor. It has a number of ARM processors for the boring stuff. We have a full custom, but flexible FET accelerator, FIR filter accelerator, and we have something which we call the DAP, which I didn't really explain, but it's a systolic array processor, which is very good for doing linear algebra sorts of things. That goes back to our matrix multiply, our QR back substitution. It basically was within a factor of a couple of full custom, even though it's actually completely reconfigurable. I can reconfigure that, not like an FPGA where it might take many seconds to reconfigure. I can reconfigure the DAP in the order of a few hundred nanoseconds, and it's also much more efficient than an FPGA. It's because it's a little more limited in what it can do, but it's the stuff I would care about. And then we have some flexible FEC accelerators as well. So a range of FPGAs, polar codes, Anything where you have this sort of message passing decoding, we're very efficient. We tend to be on an order of a factor of 3 from full custom implementations, but those full custom implementations do a single code type with very little flexibility, and we're pretty close to it. So, great. Why doesn't everybody do this? Well, one, it's kind of weird to ask so many different things of RF historically. It was hard enough to get anything to work. Goodness knows, trying to get something which does everything was just too much to ask. But now we're starting to ask that question. That's one reason. The second reason is that a few people have built core scale heterogeneous processors, not as good as the one we built or we're working on right now. We have a tape out in 6 weeks. But the problem is that the programming, the threading of the data through the chip is so complicated that literally there'd be a person on the planet who could do it. So a big part of what we worked on is actually the compile time and the runtime software, which does the resource management, so humans are not involved. That way we can actually run 5 or however many you want, different applications simultaneously with dynamic loads. We can introduce new applications dynamically. It kind of interacts like you're just interacting with a general processor, although functionally it's completely different, right? Big part of it, like half the program was actually on the software side. And we have been trying to figure out how we can integrate the work we've done with GNU Radio. So this is, we have been thinking about this. We have a second program. We're not as far along in this one. We're now, on this one, we're doing basically a special modem processor for optical communications, in particular for space optical. This is another DARPA program. On the previous one, by the way, ASU is the prime, I'm the PI, but lots of great people are involved. It's also true this one. I guess you can't see because the words are all over the top. My colleagues are all there from University of Michigan, from University of Arizona, from University of Wisconsin, and from DashTech Integrated Circuits, which is a company we started out. We started in order to support this work as well. And I guess I'm already running over, so I'll quickly finish this up. We have another project which we're doing some work with DARPA and now doing some work with Space Force. We're working on building distributed coherent systems. So in the lab, we currently have a demonstration of an array of radios that all work together like they're one single wired up system. The universe does not want you to do this. So we transmit. So in astronomy for a long time, people have been receiving signals in a distributed coherence fashion. In some sense, that's very hard, but easier than this. When you transmit, you have to be completely exactly phased aligned at the instant. You don't get to fix it later. That's the moment, right? And so we can do distributed coherent beamforming. We even can do other distributed coherent system things, which are really a lot of fun, but I'll go very quickly. And for Space Force, because no great surprise there, they're interested in doing satellites. We were thinking about the implementation of that for a group of small sats. All right, so I'll repeat this. The stuff that goes on here and thinking about how do we make it easy to implement lots of functions and software-defined systems is the right answer. Well, lots of people are already thinking about this. I just sort of encourage you to think beyond just communication systems, just sort of general RF systems. And then we need to do a lot of work of figuring out how we can make all this stuff a lot more efficient. And maybe one last point, just because my university would like me to say this. Anybody involved in companies here, we have a particular opportunity for doing sort of small startup projects with the university. So it's New Economy Initiative. Anyone in some company that wants to team up with professors, the state of Arizona throws in some money, the company throws in some money, and it's an easy way to start up sort of interesting research that's on the small side, but potentially higher risk and in the long term, hopefully higher payoff. That's it. Thanks.
Do we have any questions for Professor Bliss? No? All right. Well, thank you very much. Santosh around?
A reminder, the amateur radio exams are happening right now. It can be $15 at the door. You just can look up more information on the GRCon website about getting what to do beforehand, but it's walking in and everything is pretty simple, and they're really happy to help. So just a reminder. Thanks.
If anyone knows where Santosh is, our next speaker. What? Oh, Jason, yeah, we're a little late anyway. Jason, we could skip to you if you're around. Okay. So we'll skip to the skip one slide deck so we can get Jason's up here. Perfect, thank you.
Okay. All right. Well, hi. My name is Jason Merlo. I'm a PhD student from Michigan State University in the Delta Research Group, advised by Dr. Jeffrey Nanzer. And I'm going to be discussing some of the work that we've been working on high accuracy wireless timing synchronization using software-defined radios. So just to get started, we'll talk about some of the motivation and applications. Some of these may sound a little familiar, and we'll talk about the synchronization technique that we've been implementing, and we'll give an overview of the software implementation and a short demo of the software itself, and go through some experimental results of it actually being used in an application outdoors. So just to kind of give a brief motivation of why we're doing this. So the motivation that we're looking towards is distributed coherent antenna networks. So the idea behind that is just to have a distributed array of antenna elements which are coordinated together wirelessly, so they can be spatially moved around and operate as if they're one large antenna element. So some of the applications that you can achieve if you are able to achieve this type of synchronization are, for instance, like in next generation satellite cellular networks. Commonly, these employ very large antenna arrays that are costly to deploy and are difficult to repair once they're on orbit. So if you were able to achieve this synchronization, you could deploy this in an array of small cube satellites, which could be deployed over, say, multiple launches. And if an element fails or as it degrades over time or you need to upgrade things, these can be kind of gracefully decay and be replaced as well. And since these all bring, of course, their own power supplies as well, the thermal management becomes a little bit easier as well, since you don't need to operate on such a large, high-power antenna. Some of the other applications, for instance, in precision agriculture and sensing. So if you want to do like a passive radiometry, do soil moisture sensing, you could use an array of like a swarm of drones that are coordinated together coherently, or you could do also precision crop yield estimation as well in a radar type operation. Distributed V2X sensing, if you had autonomous vehicles coordinated together, you could use that to perform radar operations, increase your spatial diversity, and improve the probability of detection, in this case of a pedestrian. And finally, just to kind of drive the point home, say you have a rover on the surface of Mars that has a video link, for instance, or high bandwidth link that it needs to send back to Earth. Typically, you'd have some sort of low gain antenna on there that could broadcast back to an array of CubeSats that was deployed with the same mission, and that could then beamform a high gain, high bandwidth link back to Earth to stream that data. So of course, in order to accomplish this, we need to make sure that the array itself is synchronized, and that would be in time, phase, and frequency. If our timing's misaligned between the platforms, that's going to limit the total coherent gain that we can get to the destination location. So in this case, we're showing a BPSK signal that's shifted by maybe half of a bit cycle. You're going to get coherent nulling for half of that bit cycle, and you're effectively going to get only a fraction of your coherent gain at the target, which obviously is not the goal when you're coordinating this. And that just scales with larger arrays. Same for phase alignment. You need to make sure that you know accurately where the position of each element in your array is at all times, so that when you beam steer into a certain direction, you're not losing power at that target location. And then finally, if you're not synchronized in frequency or syntonized, then you're going to get a beat frequency at the destination location as well. So sometimes you'll be coherently adding, and sometimes you'll be nulling yourself, which is no good either. So all three of these need to be accomplished. This work specifically is focusing on the timing synchronization, since that's a kind of a convergent problem. So I'll be discussing the timing synchronization part. And then for our final applications, we'll also be going over a kind of an adjunct frequency synchronization circuit that we've used as well in conjunction with this to perform fully wireless operations. So the synchronization technique, so I guess to get started, you can just model the time at each one of these antenna nodes, in this case software-defined radios, just simply as a function of the global true time, small t, plus some time-varying offset, we call that delta sub n of t at each node n, and some zero mean noise term as well. So our goal is to estimate the time offset at any one of these nodes relative to, in this case, we choose some arbitrary node to be the primary node, node 0. We want to determine that timing offset to compensate for it. So to do this, we use a two-way time synchronization exchange. And this just depends on the link itself being reciprocal during the synchronization epoch. The synchronization epoch is the amount of time, or the duration that it takes from the first node to send a time delay estimation pulse, the second node to receive it, and then the nodes to transmit back to the initiating node. So this kind of back and forth exchange. So the link needs to be reciprocal, and that kind of implies that it's quasi-static. So these time estimation pulses are on the order of microseconds. So it generally is not super super limiting unless you're moving very, very fast. But generally, this isn't a very limiting assumption. So in order to determine the timing skew estimation, you just take the apparent time of flight in either direction. So the apparent time of flight would be the time that the initiating node, so if you look at the orange line, for instance, the time that that node timestamps the transmitted pulse, and the time that the receiving node receives it on its local clock. You take the difference of those, and you do the same thing for the reverse. Take the difference of those apparent timestamps. You get the apparent time delays, or the local timestamps, sorry. You get the apparent time delays, subtract them, and divide that by 2. That is our estimate of the time difference between the platforms. Similar way, if you just average these apparent time of flights, you can get the internode time of flight, and multiply by your propagation constant. You're going to get the speed of light in the medium. You're going to get the distance between platforms as well. So in order to do this, of course, it needs the accuracy with which you can determine the time estimates is going to limit how well you can synchronize between the platforms. So we focused on the waveform design here specifically for what waveform we want to use when we're performing this time estimate. So if you look at the lower bound on time delay estimation, it's really bounded by the signal-to-noise ratio. So the inverse of the signal-to-noise ratio, which in most practical systems, that's already optimized, so you want to have a high SNR. and then also the reciprocal of the mean squared bandwidth of the signal. And so really, on the right-hand side here, we're showing a plot of the mean squared bandwidth of a signal based on where the energy is distributed in that. So in the lower right-hand corner, we're showing for a linear frequency modulated waveform, which is commonly used in radar for time delay estimation. However, if you move all of that energy towards the ends of the spectrum, you actually get a higher accuracy. So in this case, you have a two-tone waveform, and that's shown in the upper left-hand corner, so with all the power separated to the ends of that spectrum there. Kind of more importantly, though, this is a much simpler waveform to generate. So if you have, say, a two-channel SDR, you can actually split that up onto those two channels and just generate those two narrowband pulses, and you can get much wider tone separations by tuning those channels to different carrier frequencies, which, of course, you can't really do if you have a continuous bandwidth signal such as an LFM. So then moving on to how we actually estimate this time delay. So we use a matched filter here, and matched filter is just the convolution of the received signal with the time-reversed complex conjugate of the transmitted signal. That can be efficiently accomplished in the frequency domain as well. So that's typically how we would do it for larger signals. So effectively what this looks like for a two-tone waveform is shown on the right. We have approximately a cosine squared waveform being windowed by a triangular function. If you look at the peak of that, that's going to be discretized by the sampling rate of your platform. So in our experiments, we've used EDIS X310 SDRs. So those are sampled at 200 megasamples per second, so 5 nanosecond discretization. If we want to get down to picosecond level, we still have a lot of refining to do in order to get down to that level. So the next thing we look to do is refine that further. And so to do that, we use a technique called quadratic least squares fitting. This is commonly employed, again, in radar systems to refine the echoes of typically an LFM scatter, but to refine it down to a single point. It's been used for quite some time. So essentially, you take the peak of your matched filter output, and you just fit a parabola between that peak and the two adjacent points. And then there is a way to solve for that in a closed form in order to pick the direct peak of that parabola, shown here on the slide. And so just to kind of visually represent that, as you fractionally move between two delay bins, in this animation on the right we're going to show here, the true time delay is the dashed red line. The dashed blue line is the peak of the matched filter output. And you can just kind of follow the peak of the quadratic least squares interpolation and see that it follows quite closely. And so using this computational efficient technique, that gets us pretty close to what we're looking for in terms of refinement. Of course, if you were following closely as well, you can perform some interpolation just by zero padding in the frequency domain as well in the matched filter step, and that can improve things as well. So finally, we perform a refinement on top of this as well. So because the parabola is not a perfect fit for the matched filter output, there is still some residual bias left over, and this is a function just of the waveform parameters and the sampling rate. So we can correct for this using a lookup table ahead of time, since we know ahead of time what the sampling rate and waveform parameters were. Yeah. So now to kind of discuss a bit of the software that we've implemented in GNU Radio for this project. So we had some challenges that we wanted to address when we started out to employ this in software-defined radios. We wanted to make sure that this could be run on relatively reasonable computing hardware. We didn't want to have to build workstation, desktops, gaming computers in order to be able to run this. So one of the things we looked for was to use a bursty transmission scheme, so TDMA, and we just use short bursts of the sampling on the SDRs in order to accomplish this. So to do that then, we also wanted to be able to manage our latency in an easy way. So we looked to using just a PDU-based graph and sending messages around rather than using the streaming-based format. And then, so finally, the kind of between each of the blocks, we also kind of developed our own way of time aligning all of the samples. So initially, we created a wide PDU, which was our protocol data unit, wide protocol data unit. And that ended up not working so well since it doesn't work nicely with the blocks that already exist out there. So we are kind of migrating towards just sending lists of PDUs as well to more nicely use the great set of PDU-based processing blocks that have been introduced recently in GNU Radio. And then some of the guiding principles. So we wanted to focus on code reusability since we are a research group. So we created a separate package called the Delta Python package where we do most of our processing, and that allows us to use the same software for simulations outside of GNU Radio and as well as offline data processing that we may be doing as well. And then our speed of implementation and ability to iterate. Of course, we also use Python for that as well. And then if we need to, we will implement things in C++. Although thus far, we haven't run into many issues where that hasn't worked for us since it is mostly vectorized NumPy operations in the code. So just to kind of reiterate the time delay estimation process, we generate our waveform samples to begin with on the primary node. We transmit those in a TDMA window. Of course, these windows aren't going to align perfectly because the clocks on the different platforms will be slightly offset. And we have our pulses. In this case, we've been using 10 microsecond pulses. So we know the clock tick that our samples are sent at with pretty high accuracy. We want to estimate the receive samples. So on the receive side, we perform the matched filter, the peak finding, quadratic least squares estimation, and then after that refinement process, we get another timestamp. So we have the 2 timestamps in one direction, and we just repeat the same process in the other direction to get the other 2 timestamps. From those 4 timestamps, we can determine with really high accuracy what the timing offsets between the platforms are. So just to look to how this actually is employed in GNU Radio, I've tried to color code the virtual sources and sinks to be able to follow where this is going. But I'll discuss kind of some of the blocks in here that are really doing the grunt work here. So we start with our waveform generation block. This just generates the PDU samples for each the samples which are stored in the PDUs for each of the channels that are to be sent to the SDR. It can take some parameters on the input to generate those waveforms. And on the output, we have the samples in PDU form, so a list of PDUs for each channel, and a dictionary which describes that waveform as well. And that is just used for the matched filter block. So we actually have a reference of the waveform we transmitted. So next, we developed our own usurp sync burst block, and this is basically just to take in those PDU samples and perform a timed transmission. I know that this is probably possible to do using the streaming API, and that's something that we're looking into with the built-in block, but this was a design choice we made early on to get off the ground quickly. But essentially, this works in lockstep. It transmits and receives at the same time on the same channels. So we're going to get the same number of samples out that we put in, and it comes out in a PDU list of PDU format as well. And then that goes into our matched filter block, where we perform our matched filtering based on the reference waveform that we transmitted from the WaveGen block, so we can get those time delay estimates. And we perform our quadratic least squares interpolation and any correction that we need to make on that. And then it goes into our time sync controller, which essentially just performs that two-way time transfer logic where we fill matrices based on the side of the array and determine the time offsets between the platforms in the array. So this kind of version of the flow graph is, I'll say, a monolithic flow graph. So this is all controlled by one computing node in this version here. So all the SDRs are connected to it. So essentially, this would actually run around this loop twice in order to perform that two-way time exchange for 2 nodes. And we've been working on the distributed version of this code as well. So I'll just give a quick demonstration of this running here. So this is in our lab where we have the software-defined radios. They're on 2 carts. In orange here, underneath the carts, we have the X310 SDRs. And then we have just a regular desktop computer, which is coordinating those. So we have a coordination fiber Ethernet connected to both of those SDRs. And then on the top, we have the time transfer antennas. In this demonstration, we have the frequency connected between the two SDRs, frequency references. In the following demonstration, we'll show it fully wireless, but this is just a quick demonstration of the software. In the upper right-hand corner, we just show the SNR estimates. This is pretty high SNR. We have the matched filter outputs being shown in the middle here. And then at the bottom, just have the time domain of the different waveforms that we're transmitting back and forth. And shown in the upper right-hand corner in a second here, the standard deviation of the timing corrections between the platform here is about 4.5 picoseconds. And the total offset in timing between the platforms there is about 22.62 nanoseconds. So this is, I guess, moving on to more of an actual application of this outdoors. So we have some work that we recently did where we were performing some beamforming to a target location. We have the similar setup with the two carts and the SDRs in those carts. In this case, we added an addition. We have a signal generator, which generates the frequency reference for the whole system. So the reference out of that is just disciplining the local oscillator on the software-defined radio on the primary cart. We also transmit that at a carrier of 4.3 gigahertz over to a two-tone frequency locking circuit. So the two tones that are being generated are 10 megahertz apart. We just self-mix that with itself, put that through a low-pass filter, and we're able to get 10 megahertz fundamental frequency out of that to discipline the local oscillator on the other cart, secondary cart. And then the time transfer is happening on the primary channel of the SDRs, and then we perform a beamforming operation to a downrange target on the secondary channel. So the way this works, initially we had GNSS receivers to perform just a single pulse to roughly align the systems on the order of tens of nanoseconds to make sure that those TDMA windows align when we do our bursty transmission to synchronize the system. So once we do that one time at startup, we perform the two-way time transfer exchange, get down to the residual picosecond level of synchronization. And we transmit the beamforming pulses to the oscilloscope, in this case, target location. And at the oscilloscope, we estimate the time difference of arrival of the two waveforms, as well as the phase difference of arrival, so that we can perform performance metrics. And in this case, we also performed a calibration on the very first pulse. We took those pulses and used them as an alignment to make sure we are beamforming to the target location. In some of our more recent works as well, we've demonstrated this with the nodes moving, so not just calibrating to a static target location as well. So just to keep to discuss how the performance evaluation occurred, we had two different types of waveforms we transmitted. In the first waveform were orthogonal LFM waveforms so that we could easily separate those out with a matched filter at the oscilloscope, an up chirp and a down chirp, one from each of the SDRs, followed by a pulse train of continuous wave rectangular pulses, where the central pulse was overlining. So when these sum together, we know how much power each of the two nodes was contributing, and then we know what the total sum of those was. We can estimate the total sum of the power as well. And from that, we can determine what the coherent gain of transmission is to make sure they're actually operating coherently. So this is just a picture of the outdoor setup we have. So we performed two different experiments, one with a 2-meter separation, one with a 5-meter separation between the nodes. And we were beamforming at 1 gigahertz in this experiment to a downrange target shown on the right, which is just an oscilloscope connected to an antenna. So this is the results of our experiment. On the left-hand side are the absolute values of the measurement. So the top row, the absolute values of the measurement. On the right-hand side is the standard deviation of the measurement. The top row is the self-reported corrections the system is applying to its local clock. The middle row is the timing offset of the time difference of arrival at the oscilloscope of the beamforming pulses. And the bottom row is the phase difference of arrival of those beamforming pulses. So in the middle here, we blanked out the frequency transfer circuit just to really demonstrate that the time synchronization is actually performing the corrections. And really kind of the takeaway from this is if you look at the beamforming time delay accuracy on the middle row and the right column, when we blank that out, you can see that the time slips, about a microsecond for that period. However, the standard deviation of our beamforming waveforms is, really not impacted by that that loss of timing or frequency alignment between the platforms. So then to show just a sample of the results from the coherent pulses that we have here. All of the results showed coherent gain above 90% in these trials. So this is just a representative sample that we just kind of picked to visually represent it and just kind of see what the waveforms themselves look like when you line them all up. So takeaway from this, based on some of our previous work, we've done some analyses on what these timing standard deviations should be able to achieve based on different modulation schemes, and as well as the phase stability based on our frequency transfer circuit, what the maximum supported carrier frequency should be. So based on those theoretical analysis, we should be able to hopefully achieve on the order of 4 to 5 gigabits per second based on these experiments at carrier frequencies of 2 gigahertz roughly. So just to kind of wrap up and discuss the status of our project and conclude. We're working on standardizing that communication between the blocks to make sure that using lists of PDUs rather than some custom type so that we can more easily use the existing PDU infrastructure in GNU Radio. Working on implementing that fully distributed compute model, and that's actually already been done, and the testing is underway. And currently, we see the same level of performance. And we're working on adding and improving the documentation of both the Python module and the GNU Radio blocks that we've been working on. We plan to add some test cases for the continuous improvement or continuous integration deployment of our code. And we'd love to be able to open source this in the future. And so finally, some of the planned work that we're looking into is trying to also use the streaming interface for GNU Radio as well to be able to utilize some of the more, some of the existing streaming features of existing streaming block sets in GNU Radio as well more easily with this code. So I'd like to thank you all for listening, thank our project collaborators and sponsors, and open the floor if there's any questions or comments. I'd love to discuss this.
Any questions? Right behind you.
Thanks for the nice talk. So my question is regarding the 10 microseconds that you have chosen. So based on what have you chosen this value?
So the estimation of the time of arrival estimation is bounded by the post-process SNR. So your pulse duration is going to improve that. So as that increases, you get longer integration time. And we've just found that 10 microseconds is empirically a good value that we've.
And how many cycles? What was the frequency, the local oscillator frequency? How many pulses and how many pulses do you actually transmit?
So this is happening in both of these demonstrations. It's synchronizing every 500 milliseconds.
Every?
500 milliseconds. So one exchange every 500 milliseconds, half a second.
Okay, and the one cycle itself, the 10 microseconds, how many pulses do you transmit?
Oh, just the one pulse in each direction.
Okay, thank you.
Any other questions? All right, let's thank the speaker one more time. So we've got a few lightning talks and then break. And if David Cavion is able to go early or is in here. Yeah, if you're okay with going early, we had one speaker not arrive. Did you have slides? Ooh, oh, they had. Okay.
Just waiting for my slides. So is anybody here looking to build their own STRs? Probably not, right? I don't recommend it. Just saying. Right. So in case you are looking into building that, and I truly don't recommend it, but in case you are, I have the next best thing pretty much. Next slide, please. Oh, I have this clicker, right? Cool. How about we build a modular interface? How about we make a motherboard cheap enough that everybody can afford it, and we build an ecosystem around it, right? So all of the tricky bits, like the, say, ADCs, DUC, signal, power, clocking, Ethernet connection, SOP interface, everything is handled by the motherboard. And the motherboard has, say, the cool stuff being routed out through those very inexpensive DF40 connectors. There is 2 of them, and they are symmetrical. And basically, what are those? Oh, wait, next slide, please, not reset. What are they carrying? They're carrying 2 ADC pairs, IQ pairs, 152 megasamples per second, 1 DUC. So that's a total of, since like we have 2 interfaces and of course 2 IQ pairs per pair, that's like 8 ADCs. So if you want to have the sample rate, you can have a 8-channel coherent receiver for like $299. There is a CI5510, which is a very nice clocking IC, which has an NCO on board and stuff like that. Power, GPIOs, PPS in, etc. A nice, say, tool that's also in there is some very simple logic that's designed to switch the, say, hundreds of GPIOs that you can have on the daughter boards with like microseconds accuracy. And that's all controlled by the PHY timer inside the 9310, which is the main ADC. So what can you build? Anything you want, right? Anything. I mean, I've built a couple of boards. There's going to be a reference design online, etc. You can, for example, build a microwave front end going out all the way up to 20 gigs without, having to decide between that and buying a new car. And you can build your own custom signal acquisition and etc. The idea is that the difficult bits are handled for you, and you can have fun. That was my very, very brief lightning talk. I guess.
Any questions? We have some time. Any questions? Yeah, thanks. So if John is, we're a little early, but if John's in the room, oh, yep.
All right, I'm back. I'm going to try not to break the mic this time, but we'll see. I was working on something where I needed to dynamically generate flow graphs, and originally I thought of something very simple and came up with my own file format. And as I kept adding features to it, I realized, oh, this is kind of similar to the GRC file format. But there were some things in GRC that I didn't care about, and there were some things that I needed that it didn't. And I'm aware of others who have come up with extensions to the GRC format or done other similar things. And so I asked if there was a way to generalize this. So I've put some thought into it, but I wanted to talk to you guys and get your feedback and get your ideas so that we could try and come up with some nifty things for GRC. So I've got some ideas of why would we possibly want to change things. So what I have found is that the GRC format is very GRC specific and very Python specific. So the format is not publicly documented in, say, a schema or something. And so if you really want to know what fields are allowed or what you're allowed to put in there, sometimes you end up having to go to the code and dig through things to figure it out. So it'd be really nice to have a well-documented schema. My ideas range from really simple like that to crazy. So yet again, come to the workshop. It's going to be Saturday, 9:30. So you can talk me out of the crazy ideas or come up with your own crazy ideas. But you can also put Python expressions that, such as at the bottom here, I've got 0 in brackets times 8. That's a valid Python expression. But we can create a Python flow graph or a C++ flow graph. And if you try and put that into C++, it's going to crash and fail. And so a hope is that we can make it easier to produce flow graphs that'll run in Python or C++. My end goal is that with what's going on with GNU Radio 4.0, there's going to be a lot of compile time optimization that can be put in. And so you would do your development in GRC just like you do today, and you would have access to the new 4.0 blocks. And then when you're ready and happy with what you have, you can push a button, it'll generate the C++ code from your flow graph, and when you compile, it'll be able to optimize all sorts of things for you, and so you'll be able to get something that may run, I've seen cases where it's running 2 or 3 times faster because of compile time optimization can do when it knows all the parameters. And so thinking of a way forward to make it easy to do something like that and easy for someone to come up with their own custom application. I have one more slide that I completely forgot what I put on there. Okay, yeah, so here are some of my ideas. Please bring your own. So right now it's a GRC format, but it's really a flow graph format. And so to make it more generic, rename the extension, come up with a schema. One of my crazy ideas is to have a JSON-like expression language that you're putting in there. So rather than a Python expression, you're putting something that looks like JSON in there, and that's easy to translate to Python or C++. Or if someone wanted to write something in JavaScript or Rust or whatever, it would enable us to have more language support in there. It would be really nice to have conditionally enabled blocks. I don't know if you guys do this, but you add a Qt block in there and then for debug, and then you pull it out in production, and then you find out it doesn't actually work, and then you have to go back and resurrect the old file, and it can be really annoying. So conditionally enabling a block based upon a variable, and then also having loops available as well. And by loops, I don't mean a cycle within your flow graph. You may have data where you're, say, parsing out n channels from a signal, and that n is a command line parameter. And so you may be instantiating a block or a set of blocks n times based upon what someone passes in. It'd be really nice in GRC to be able to specify something like that. And this would just add more power to GRC, so there's more cases where you can stay in the nice GUI and not have to be writing code. So the workshop's going to be Saturday at 9:30. So if you guys are around, it'll be great. I'd love to have some good discussion, talk about my ideas, but also talk about whatever complaints or issues or ideas that you guys have as well. So thank you.
Any quick questions or comments related to GRC, since we have a minute? No? All awesome ideas. I love it. It'd be great to be able to still enter in Python, but have multiple language support somehow. And last up for lightning talks, we have Josh. Oh, sorry, Rob.
No worries.
Rob.
Up there. Thank you, sir. Hey, so good afternoon, everybody. My name is Rob Miller. I'm with Paraton Labs, and I have the honor of giving a sponsored lightning talk. So I have no slides. Please don't throw anything at me, and I do understand that I'm in the way also of the break. So rather than giving an embarrassing plea for hiring and needs, I just wanted to start out and say that GNU Radio itself has been amazingly impactful for Paraton Labs in terms of furthering research and allowing us to do, really novel, interesting signal processing development that, 10 or 20 years ago wasn't possible, right? Good algorithmic ideas pretty much died, on paper or maybe in simulation. And given all of the amazing collaboration and contributions of this community, both in the software-defined radio realm, from a hardware perspective, and then also from a signal processing perspective, have really enabled really awesome applied research to be brought out into interesting prototypes to solve real-world problems, right? So historically, we've done a lot of very cool things, from advanced sensing to waveform development, and I'm not going to go into all of those details, but I will say that there are a couple of highlights, one of which would be in the realm of GNU Radio 4.0, right? So Josh Mormon is one of the folks on staff at Paraton Labs, and he's played a pretty big role in, I guess, providing a vision for GNU Radio 4.0, in addition to a lot of interesting work on the heterogeneous compute side of the house. And then for folks that were here at GRCon in DC last year, We had released an RF machine learning open source toolkit called TorchSig. So that was in conjunction with Peraton Labs and also Laboratory for Telecommunication Sciences. And so we do have an update. So this is a forward-looking plug right after the break with Dr. Garrett Van Hoy, who's going to be giving interesting updates on that toolkit. And then, a plea for collaboration and feedback, because without collaboration and feedback, ideas tend to die early. So very, very excited for, the great discussions we've had with everyone here over the last couple of days. Look forward to what's left. And, I will end with the consummate plea for we, are of course hiring. We have locations in New Jersey, Maryland, and New Hampshire. So if anybody's interested in talking about not only employment opportunities, but also cool, interesting collaborative ideas, please come see any one of us. A lot of folks are over there. If you guys don't mind just raising your hand real quick, or you hear Peraton Labs, come and chat. We'd love to hear it. So thank you.
All right, with that, we have a break, and there's also some slots for lightning talks tomorrow afternoon. And we'll come back after the break for Garrett's TorchSig update. Garrett here with a TorchSig update.
Okay, so we'll get started. Okay. All right, so good afternoon. My name is Garrett Van Hoy. I work for Paraton Labs. I've been part of this community, learned a lot through GNU Radio about software-defined radio, signal processing. So I'm very thankful to be at this conference and part of this community as well. So today I'm going to give a brief update on this Python package that we introduced last year at the GNU Radio conference. We had a presentation on it and also a workshop, and I was pleasantly surprised to see the kind of interest that people had in it. That workshop was very full at that time. But this is a package that's kind of a blend of RF signal processing and machine learning. And if you've been going to the GNU Radio conference for a few years, you'll notice there's been in the past a lot of actually presentations on machine learning. So this is, even though this is not specifically like in GNU Radio, there's a lot of different ways that machine learning can be integrated into GNU Radio and used for a lot of wireless applications, which I will talk about today. So that's how this is related to GNU Radio. So I just wanted to provide an update of where this has gone in the last year. We just kind of open sourced it like pretty much right before the conference last year, and where has it gone and what updates there are to it until then. And personally, you know, even though I've been contributing a little bit here and there to GNU Radio, definitely trying to maintain a piece of software like this is a new experience to me. So I have a new appreciation for what GNU Radio has been able to do as a project. It is not easy to maintain a piece of software like this that is used by such a large community and also a very core part of a lot of projects, both research and commercial as well. So this presentation may not be as visual as some of the others, so if you're interested in this topic, please note that a lot of the pictures, a lot of the figures, and a lot of the code you can find is on GitHub. I'm specifically referring to things that you will find on a branch on there that will be merged into the main branch soon. But also there are 2 papers that we presented last year that I will kind of briefly refer to what those results were if you want to know about some of the data sets that we actually talk about today. Okay, so I'm going to give just a brief overview of what is TorchSig in case you haven't heard of it, what is this about, why am I talking about it, and then some of what's actually new. Okay, so what is TorchSig? One of the things that it is, it's a collection of highly parameterized synthetic RF data sets. This can serve a number of purposes, but one of the big motivations of making this was actually being able to establish some kind of RFML community-wide benchmark, right? There have been various different RFML data sets that came out from like maybe 2016 onward. But what we found when we were trying to prototype new networks on it and different algorithms on it, you couldn't actually show any improvement using those same data sets. So those data sets didn't provide the differentiation that we needed to be able to say, okay, our new network, our new layer, our new learning approach is better at all. So trying to make these kinds of data sets where people could see transparently how was this generated, how could it be improved, things like this. This was one of the big motivational factors of making TorchSig and the data sets in there, and also just creating toy data sets. Like if you want to be able to show and also share your results in the research community, you need to be able to, or it's very helpful to be able to create, you know, just a BPSK, QPSK data set with a certain set of impairments, because a lot of the results I had seen up to then, you know, there would be a paper saying, hey, these are great techniques, but when you add this specific channel impairment, they don't work. So here's a way around that, right? So we wanted to make it so that, you know, testing that and demonstrating that while keeping all of these other assumptions intact, that was a big part of what we wanted to do. So a lot of it is about being able to just provide an easy way to get access or to have these highly parameterized data sets, which are very helpful for ML research, because we saw this in the CV community, the computer vision community, having these kinds of data sets like ImageNet that allow people to just share the results very easily and demonstrate like this is making this much progress and being able to compare. We wanted to bring that into the RF community. Another big thing is actually having a suite of RF and ML domain transforms, and those serve many different purposes, but one of them is channel modeling. Channel modeling, it allows you to train on something that is closer and closer to realism as much as you can, or as much as it's useful for machine learning, and also data augmentation. If you've done any research in RFML, yes, there may be an abundance of data that you can collect using an SDR, but can you simulate that same data going through any number of RF channels? A lot of the times using synthetic transforms to emulate this kind of channel is very helpful, both for training, for validation, for a variety of different reasons. So that suite of transforms there is where we think the most a good chunk of the value of TorchSig comes in. And trying to bring in some of the state-of-the-art progress has been actually already achieved in the ML community, because they have these networks, and these deep learning networks actually work not just on one domain, but they work across several domains. So trying to bring that network into the RF domain so that we can at least use that as a baseline and say, if we're going to improve, probably it should start from here in some way, right? So that was another thing. And then utilities for bringing in your own data set, right? If you can't bring in your own data set, it's not all that helpful. Okay, so when we were making it, the big things that we wanted to try to do is try to resemble as much as possible these Torch Vision, Torch Audio kind of APIs, so that those that were familiar with actually doing machine learning research in those communities could come and also play along and try to show it if their network actually is better. It actually would also presumably be better in the RF domain, even if it is designed and thought about in some other domain. Okay, try not to focus on a specific ML framework. So TensorFlow and PyTorch are two big ones, but there's others out there that we didn't want to force people to use. Make it easy to use new data sets. Make it easy to bring in your own impairments, because if you don't think that the channel model is of sufficient quality, make it easy so that you can write your own that kind of models whatever radio that you're dealing with at the time, and provide as many examples as we can to be able to show you how to use the framework. Okay, so if you actually look at the package, this is what you'll see. If you see it on GitHub, there's a few things that have been added since we introduced this a year ago. But again, a big part of it is still the data sets, and there's a lot of structure under there about how those data sets get generated. We've added a lot more examples and scripts. So because we've run in collaborating with other groups of people, we found there are plenty of people like, that's great, you have a cool library, just give me the data. I already have what I need at this point. So we kind of made these scripts to where we can generate static versions of the data sets that we talk about, so that people can just look at the data, see if it really fits what they're expecting, and try their own algorithms on it without needing to use almost any of the rest of the library at all. There's a few models that we support in there. EfficientNet and Exit are two kind of popular baseline networks that demonstrate two different kinds of networks in the computer vision community as well. So we support at least just showing how to use those things, but there are many more models out there. There are many more variations on these models, but we have them there to show you that our intention is for you to use it with things like this. Lots of transforms. It's a huge list there, and that actually is not even a complete list of what kind of transforms are in this library, but just to show you some of the ones in there, you see things like target SNR and add noise. These things are related to RF channels impairments, but there are other things like time reversal, which you might ask, like, why do you have something like time reversal? Well, that's not like an impairment. If you could, make that happen in reality, that would be cool, but it's actually there because it helps with machine learning, right? It's actually a common augmentation for other kinds of machine learning, and it actually turns out to be helpful in learning even in the RF world as well. Okay, and there's also some utilities. Okay, so what's new? Where have we tried to go with this from the time of its release? Try to make it more usable. At first, it was I would say it would be at least usable by somebody who's interested in doing research in that domain, has some time to actually look at the code, has some time you know, that it's worth their time rather than doing everything from scratch to look at the code and try to make it work for them. But trying to get it to work off the shelf may be a little difficult in the form that it was in. There were certainly some examples that worked off the shelf, but not as extensive as you would hope if you just wanted to play around with it. So trying to go more in that direction is what we spent some time to do in the last year. So what that's looked like, actually this is an exception to that. We did actually release the wideband SIG53 dataset, so I'm not going to go over what the SIG53 dataset is. That's one of the things that we introduced last year. But we introduced a wideband version of that dataset. So the wideband version of that dataset is significantly more substantial. The SIG53 dataset kind of emulates, you knew where the signal was, you knew about what bandwidth it was, and you knew about how long it was on, and you captured it just perfectly like that. But the wideband SIG53 dataset is now, imagine you're just a radio receiving stuff, and all these SIG53 signals could just appear anywhere in that spectrum. They could, each of those signals that, even though there might be multiple of them in that spectrogram, imagine that they all go through their own independent channel, and then they all go through one not independent channel, right? The receiver affects all of those signals all at once. So that data set is there, and there's quite a lot of structure to it underneath. But this data set, the way we set it up, is to be able to train a network to do semantic segmentation, instant segmentation, or object detection, specifically draw boxes in a spectrogram, right? We want to be able to time frequency localize. So the data set is certainly set up for that, but you could use it for all different kinds of things. You just have to change what the labels are, right? If you wanted to just make a detector for a specific kind of signal, instead of drawing boxes, you change the label to is the signal there or not. It becomes a two-class problem. So we spent a lot of time on that one, and the results that we have for that data set are also there in that paper. That paper was something we also mentioned last year. So just to mention very briefly what the structure of that is underneath, we wanted to make this library so that it would be easy for people to add on to it, to expand it, easy as possible, right? It's not going to be that easy, but the way the data set works is that in the wideband data set, you basically, yeah, I'm not sure. Yeah, in the wideband data set underneath, what it does is that you define a burst source, right? So you would think of some other transmitter, it's emitting bursts that are all of a similar-ish type. And so if you can define a burst source, then you can actually plug into this wideband data set and you can include your own transmitter, right, in this new data set, as long as you can get that class to produce a burst of certain specifications that are on for a certain amount, bandwidths a certain amount, things like this. Then you can also kind of use this data set for your own purposes in that way as well. Okay, so some of the things that we spent some time on is accelerating the data set generation. Because RF data, it can get very large and take up a lot of disk space. We thought that it would be good to have an option to generate it on your machine, but SIG53 is like 70 gigabytes. Wideband SIG53 is, I believe, several terabytes, so not everyone's machine has that amount. And also allowing it to be downloadable is a little bit difficult. So we just accelerated generating both of these. Depends on what kind of machine that you originally generated on, but just generally speaking, we reduced the amount of time it takes to generate SIG53 down to a couple of hours. And wideband SIG53, which used to require GPU acceleration to even get it to be generated in less than a month, now you don't need a GPU, and it should still take like at most a day or two to be able to generate that whole data set. And we did that by doing better DSP. There was a few lines of code that kind of are always the culprits in these things. You know, doing frequency domain filtering instead of time domain at the right time, and also doing multi-threading, which we kind of got for free using PyTorch stuff. Okay. So other things that we added on there is now there are scripts for generating the data sets. I mentioned this earlier. If you don't want to know anything else about TorchSig, if you just want a data set to see what the signals are like and be able to play with machine learning, there are some scripts there that are now included to be able to generate both of these data sets on your machine and different sizes of them. So if you just want to see an example of what those data sets look like, you can now do that. And if it's convenient for you, if you're familiar with Docker and Docker is easier for you to install, then we also have some options to use Docker, and simplified it so that you can actually just We made it so that if you can generate these data sets, we provide a class also so that you can just use that class only in like a notebook and then just view what comes out of it without, again, using the rest of the library if you'd like. Okay. Other things that we added is there's some examples for generating and analyzing either a static version of these data sets or an on-the-fly. SIG53 and these other data sets, they can be generated on the fly, and then you can train on them on the fly, so you can have as many samples as you want because it is randomly generated. It's just much slower when you do that on the fly because you have to generate it on the fly. But when you can read it from disk, it's much faster. There's also some examples of using different visualizations for time domain, frequency domain, even constellation plots so that you can see what are you training on. That's always very important. Before you train on something, you know what you're training on. Okay. Other general improvements that we have is we've updated the documentation, done a lot of refactoring underneath so that that documentation can also be more understandable itself, adjusted some of the structure that's in there, and we added tests because there actually weren't tests when we originally released this at all. It's not so easy to test, especially numerical stuff like this, but the best thing that we could do is now every time we give a release, now figures will come with that so you can see if those figures change from one major version to another, benchmarking and hashing the named data sets so that we know if they've actually fundamentally changed or not as well. Okay. There is still activity on this. You know, it's only a couple of people that are actively, I would say, monitoring this specific project and repository. It says 60 commits there, but that is squashing of many, many other commits underneath. So if you have issues that you put on there, at least there's been response within about a week. So it is an active repository in that regard. And if you're curious as to where the project is going, there is actually a GitHub project that you can view and see what's going on there. Okay. So in the future, things that we're hoping to work on, obviously pull requests are always welcome, but trying to make it so that we can wrap some of the custom data sets, like in the last 4 years especially, a lot of custom data sets are out there. They may be behind different kind of accesses. I think a lot of IEEE stuff, you have to at least be a member to get those. But even just having the class that if you have access to that data set, just making it so that you can actively use something like that is something that we would hope to get in there. Better transforms to emulate more sophisticated channel models, I don't think is that far away to be able to do that, and showing canonical examples of different RFML tasks. So we have classification and some object detection and things like this, but there are many other RFML tasks that we foresee being able to put in there saying, hey, you know, this is how you would try to use RFML to do this maybe classic DSP thing. Okay, that's all I have for the presentation, and thank you guys for listening.
Any questions? All right, no questions? Next up. We need the next.
Okay, thank you.
So here's the clicker. Anyway, good afternoon, everybody. My name is Kevin McQuiggan. I'm an amateur radio operator. My call sign VE7ZD, and I have an American call sign as well of KN7Q, and I'm here today to talk for a little bit of time about amateur radio, DSP, and GNU radio. One thing I will say up front is this is a non-technical presentation, and it's, you know, I think I'm speaking more as an advocate of amateur radio and the value of the hobby to STEM and to industry and to academia and that kind of thing. And so it's just what I'm summarizing are observations I made over about the past 20 years or so. If I'm not really representing anybody, but nominally I'd be associated with the university in the Vancouver area called Simon Fraser University, where I did my graduate work and that kind of thing. And so we'll get into some of the details here. So to summarize the presentation, amateur radio, it's a popular hobby that draws people from all their operators in the group today or in the attendees at the conference today. But a characteristic of hams is that really they do come from all different walks of life, and most of the operators, most of the people who get licensed have no formal technical training in technology. What they learn through the process of studying for their license and the experience they get after they have been licensed as an amateur radio operator. Now, despite this, you know, amateur radio has generated significant innovation precisely because of this lack of formal training. Maybe that doesn't compute. Maybe that sounds like it doesn't compute, but it is actually true. If you look back over the history, we're going to look at some examples of innovation within amateur radio. And the reason these innovations come about, and I think they continue to come about, it's one of the challenges with the hobby for today, you know, or in current times, is that amateur radio operators because they come from a non-technical perspective generally, and they come from all different walks of life, they have a unique perspective, and that can contribute that orthogonal point of view in terms of looking at problems and issues and opportunities and everything. That can generate innovation, and it's very, very interesting when you look back over the history of the hobby, the kind of innovations that have come out of it. And so I can summarize that by saying that hams don't know what won't work, right? And so I think if you work in academia, you work in industry, you have graduate degrees, all that sort of stuff, you have a very, very good idea. You know, because I have technical background as well, you know, computing science, math, et cetera. But in any case, there's like a, you know, we sort of know, we have a good idea of what won't work, but hams don't have that limiter, they don't have that filter. And so very often amateur radio operators, you know, going back to the 1910s, the 1920s, that kind of thing, they didn't know what wouldn't work, and so they are willing to try things that in a professional context would never try that because we know that it won't work, right? And that's not to denigrate the knowledge. It's great knowledge and great technical ability and everything of everybody who works in academia and industry. But there's the odd little kernel, the odd little thing that comes up, and it's a really, really interesting discovery, right? And typically, when that has happened, that gets folded back into industry, and it starts, you know, folded back into industry and developed and all that kind of thing. And so that's an interesting characteristic of amateur radio. Anyway, it faces some challenges. The hobby itself is facing some challenges, and I can talk historical challenges and what they are today. But the current challenge is the balance between technologists and communicators within the hobby has changed significantly in the last 4 decades, since about 1980. We'll talk about what technologists and communicators, how they differ. And so there's a lower focus on technological skills within the hobby, and that tends to reduce the value of amateur radio to government and to industry. And so GNU Radio comes back into this. I'll fold it back into the presentation by saying it has, you know, they can help modernize training, enhance the skill set, enhance the ability and the experience of new hobbyists so that they hopefully can continue to innovate, continue to serve under the mandate of amateur radio. Okay, so I've said a little bit about me already. I've been involved as an amateur since 1977. I've been involved in many, many aspects of the hobby, and I've studied the innovation process in amateur radio for many, many years through graduate school and post-grad school. Okay, so what is amateur radio? For those who aren't licensed, we'll have a brief summary of what it is. Amateur radio is non-commercial use of the radio spectrum for experimentation and personal communication. It's an international activity. It happens in all but I think 1 or 2 countries in the world. It has about a 120-year history. And the licensing standards for amateur radio operation are controlled by the ITU, but they are managed in each nation by the, it's called ISED, Innovation, Science, Economic Development in Canada, the FCC in the US, and similar agencies in other nations around the world. But the international standards are set by the ITU. Why do people get involved in amateur radio? From the user's perspective, from the hobbyist perspective, it's the excitement of talking to other operators all over the world, and also the development of technical skills and experimentation, innovation. I've been involved in many projects, with an innovative component, experimentation, trying new modes, trying new things and everything. And for me, I am what we'll see is I'm a technologist, right? I'm interested in the science and the technology and the reasons why and everything. And so that is the other reason why people get involved in the hobby. Now for government, why does governments the world over, they support amateur radio? The reason they support amateur radio, and there's common thread in the legislation in many, many nations, and it can be summarized as, say, advancing the state of the radio art. Government recognizes the amateur radio as a hobby activity, can help advance the state of the radio art. That's very interesting, right? Because the government looks to this hobby to help with technological development, with the development of radio systems. Now, historically, federal governments, they viewed amateur radio as a way of supporting a technical reserve of citizens within society, with the idea that in the event of an emergency, a disaster, a war, that these people are widely dispersed throughout society. They can be called upon to provide communications. Great example of that would be World War II. World War II, most of the, when the United States, when Great Britain, when the war broke out, the governments called on amateur radio operators and Signal Corps and military communications agencies were largely staffed by amateur radio operators who stepped up. And government, in fact, approached them and tried to recruit them because they had basic radio skills. Right, they're able to come in and provide service immediately. So those are the two reasons. Government supports amateur radio because it advances the state of the radio art, and there's a technical reserve of citizens. So the characteristics of amateur communication: it's communication using several modes on bands allocated throughout the electromagnetic spectrum. And if you're a ham, but otherwise. Amateur radio has allocations throughout the electromagnetic spectrum. It's the only service other than the military where the users, the hobbyists, can choose the frequency, choose the mode, choose the level of power at their own discretion. So hams have agility. As an aside, this is of value to industry because if you have people in industry who have amateur radio licenses, it is fantastic for gaining access to spectrum at many different frequencies. And another key about amateur radio is it provides unmediated direct communication that is not dependent on commercial infrastructure, right? And so it's fine to say, and that's one of the things about motivating young people to get involved in amateur radio these days. Well, why should I care about talking to Japan or talking to South Africa? I can just text. I can go on. I can go on Twitter or whatever, but the difference with amateur radio is that it's unmediated. It doesn't depend on billions of dollars of commercial infrastructure. And so that is really, really cool, right? It's unmediated communication. So there's significant history of innovation within amateur radio. I'll touch on these very briefly. Propagation theory, the ionospheric model of HF propagation was actually, it was not well understood, and in 1925, it was an amateur radio operator, a number of proposals, discussions, papers were written and everything. And this ionospheric propagation model was actually originated by a guy named John Reinhardt, who was an amateur radio operator. Single sideband early experiments and development of that mode took place within amateur radio. Low bandwidth image transmission on the shortwave frequencies, microsatellites, small satellites. We know them now as CubeSats and small sats, but a lot of the initial work, is an organization called AMSAT that developed the first small satellites going back to the 1960s, 1970s. Another good example of packet radio, low rate practical digital communication. Right, that originated. A lot of that work in terms of point-to-point networks and amateur radio communication that arose within amateur radio in both Canada and the U.S. In the late 1970s. And I would say a current example is weak signal communications. Weak signal communications. There's a mode that is currently very popular called WSJT within amateur radio, and it is unique. It is really revitalized communication on the HF bands, 3 to 30 megahertz, because it takes advantage of forward error correction, convolutional encoding, and that kind of thing. And it's largely the result of work by Dr. Joseph Taylor from Princeton University. And it's existed for about 20 years. It's well developed, but it's certainly taken off, and it's revolutionized, I think, the ability of amateur radio operators to make long distance contact in conditions of poor propagation on HF. And so innovation continues. Oh boy, I could use some water, but in any case, Anyway, we should talk about innovation within the hobby in the mid-20th century versus the 20th century. What has happened? If you go back to 1950, 1960, in the pie chart on the left, and these are purely subjective figures, right? I don't have any data other than years of experience to support these figures. The orange slice of the pie, right? That was innovation contributions by amateur radio operators. It was quite significant. You could say it was 75%. Or 75% industry, academia, and other, but there was significant percentage of contribution by amateur radio operators. Fast forward to the 21st century, thank you very much. That's better, it's the humidity. We must hydrate. Fast forward to the 21st century, and the percentage of innovation, has really shrunk. It's just a sliver. It's small percentage compared to what it used to be, the contribution of amateur radio. And so that's too bad, right? Amateur radio could lose its relevance, it could die out, right? And that could be we'll see why that's not necessarily a good idea. I'll go very quickly. I think I'm concerned with time, so I'll go very quickly. Licensing and qualification. Amateur radio operators have to be licensed by the respective federal governments because federal governments regulate and implement the regulations of the ITU. And so there are technical, operational, legal components of that license. Why do operators have to be licensed? Because of the global, because of global propagations of signals, especially on HF, or in particular on HF. And so governments are concerned they don't want amateur radio operators interfering with other government services, with military, and that kind of thing, and also to ensure the effectiveness of communication. So the impetus for licensing internationally is really to prevent interference and within nations, and between nations as well. So the standards have changed with the proliferation in particular of personal communication devices and the internet and that kind of thing. And so the examinations in the 2000s, since the turn of the century, they focus more on legal and operational aspects rather than the technical details of radio. So that also erodes the technical skills of the people involved in the hobby. Right, so the examination looks at, emphasizes non-commercial use and prevention of interference with government and commercial telecom services. The bottom line is because of changes to the regulations, changes to the licensing standards, new amateurs have weaker understanding of radio technology than they did back in the 1950s, 1960s, that period where innovation percentage by hams was much greater than it is today. And so we can call these people technologists, right? They would be, people interested, technologists and communicators. In 1980, right, go back to 1980, we're interested in the technologists, the blue in this. Most hams, most amateurs, they were technologists. Fast forward to today, and it's a small percentage, maybe 10%, 15%, if that, of amateurs are technologists. And so the communicators, we're going to see who communicators are, what their characteristics are. Communicators have taken over the space within amateur radio largely. There's still a core of technologists, but they're mostly communicators now. And so technologists, the technologists are amateurs who focus on technology, radio science, right? Designing, building equipment, experimenting, writing software, getting involved, as I can say for most of us, for the hams who are here, SDR, DSPs, GNU radio, experimentation, weak signal, getting involved in all these interesting new modes. We are all technologists for the hams who are here, right? And technologists, their motivation, it's all these questions, right? I was going to take them out, but really it's all these questions like, what are radio waves? How do they radiate? How do you build an antenna? Why does an antenna work? All those questions, right, that for me, started when I was a little kid, right? And you just want to get answers to that. You're curious, that we could allude to the earlier presentation about curiosity. Communicators, the other group, they're less interested in the science of radio than the question of how radio can be used to communicate. Right? The communicator uses amateur radio to advance social goals, coordinate community events, manage disasters, manage emergencies, simulate disasters, they are users of the service rather than interested in how it works. They understand a little bit about how it works because they too have to get licensed. They have to have that basic understanding, but their motivation is how do you use radio? How can radio be used to communicate? And so they're focused on the communicative capability of radio and its ability to help others and solve problems. So as a consequence of this shift, this big shift, this reduction of the technological interest, technological focus within the hobby has receded. Many often, and really a lot of amateurs, they do retain curiosity, innovative spirit, but because they have lesser understanding of the technology, there's less opportunity to innovate, to truly innovate, as amateurs did many, many years ago. Okay, so we gloss over this. The key thing here, you know, is these are licensing standards, the 1970s, 2020s. If you look at the licensing process on the left, there was an in-depth technical interview, written examination. You had to draw and explain schematic diagrams. You had to have a component level understanding of radio. Of course, it was analog radio in the day, right? I left Morse, there was a Morse code examination. I put that in brackets because that wasn't, that was a, that, you know, that, I guess that was a hurdle you had to get through, but it's not really relevant today. In the 2020s, the standards have changed. And so now to get qualified, you have a multiple choice examination based on high level concepts and regulations, right? So, so it's really, really changed. The exam is based on a published question and answer bank rather than going away, studying and having to sit down. And I remember sit down with the radio inspector and you're just, I was 17 years old, I'm sweating bullets and the guy's, well, what if we take out this capacitor? What if we take out this, what if we short this inductor? What will happen? Right, so much deeper understanding. Now, how does that affect on the right-hand side, relevance to industry, right? In the 70s, the skill set of you as an amateur, me as an amateur, it supported participation in radio science, engineering work in academia and industry. It prepared you very well for going to engineering school, right? For joining industry and designing radios, building radios. What happened now, because of the changes in the licensing standards, amateurs have the skill set it's insufficient. You can't work in industry, you can't work in academia, and it would be minimal foundation, I think, for going to, applying to engineering school, for example, right? And so that all affects the ability of the hobby to innovate. And we'll get back to where GNU radio is relevant in a couple of minutes. So some people would say, oh yeah, there's no problem. The complexity of radio technology is greatly increased. I see from some of the presentations today, I have computing science, mathematics, electronics background. I learned, sort of learned on the job and everything for electronics, but it is incredibly complex, incredibly specialized compared to many, many years ago, right? And so maybe it's no problem because amateurs, there's no way they could ever innovate. There's no way they could ever really contribute because the field has become too specialized. So that's on the one side. You say, oh yeah, it's no problem because it's the too specialized, they couldn't contribute anyway. Or it could be a significant problem. The lower level of skill, it undermines, remember, government's objectives, advance the state of the radio art, right? And also provide a technological reserve in time of emergency, time of disaster, right? Well, it is a significant problem to have less literate people or less technologically literate people involved in the hobby because they can't contribute, right? It undermines the government's goals for having amateur radio in the first place. And so amateur radio could be lost, right? And I would say it shouldn't be lost because it can still contribute. It just has to change a little bit, right? If amateur radio was lost, you do lose a source of non-traditional innovation. The chance of really, really creative innovation is lower than it was before, for sure, but there's still things out there. Look at this, look at the weak signal propagation modes and that kind of thing. Lots of innovation coming of that. There would be no community group that can be called on in time of emergency if amateur radio was lost, low level of technical preparation for academic programs or industry. That is directly related to STEM initiatives in Canada and the US and other nations around the world, right? Sort of cutting our own throat by having people less prepared to go into science technology. So what's my opinion? I think I've stated my opinion. We'll just summarize, right? I think amateur radio still has contributions to make. Government is wrong to rely on commercial infrastructure for communication in time of emergency. If there's a disaster, there's an emergency of some type, commercial infrastructure, chances are that it's going to go down. I studied disasters in grad school before I decided to look at innovation in amateur radio. One of the characteristics of a disaster is that infrastructure fails in unexpected ways. You know, you try to mitigate, you try to plan and everything, but stuff goes down and it's always in a way that you didn't expect, right? So it can be a real mess for the citizens, real mess for society when that happens. And so it's good to maintain amateur radio, because amateur radio, the operators are widely dispersed in the community, everybody has their own equipment, and at least it gives you a chance of being able to communicate when these events occur. Hopefully they never will, right? And so, as a result, efforts should be made to return more technical focus to amateur radio, right? Build a more capable service, try to restore some of that. And so how could we do that? That's GNU Radio's role in this. And so the challenges to the training, question-answer bank-based examinations, right? People can memorize, and a lot of people take the test, because you can get the question bank, they memorize it, and they don't have any real depth of understanding, but they're able to get through the licensing process. There are also problems within the amateur radio community of classes that teach specifically to the examination. Right? You want to learn. You want it to be you want to have education, not training. You don't want to memorize things. You want to, you know, class it is wrong, I think, for people within the community. Amateurs provide the amateur community provides training to the new, you know, or provides classes and everything, but it's wrong to teach to the exam. And there's also very little hands-on experimentation, right? You see things, and how am I doing? How am I doing for time? Can somebody tell me? You're doing all right? Okay. And simplification of the testing process for the convenience of government, right? Government needs to update that. So I'll try to speed up a little bit. GNU Radio, it's an ideal tool. It's open source, cross-platform, straightforward user interface. I've been a user for 7 or 8 or 9 years, and it's really, really powerful. I have learned so much from playing around with GNU Radio. It can improve technical understanding of radio for students, develop a better understanding radio science technology for existing amateur radio operators as well, right? It'll restore relevance by bringing the training of current amateur radio operators into the digital realm, into the digital area. Because and that's another issue, as we'll see, right? It'll help amateurs make the leap from analog to digital. And it can also attract younger people from related communities, such as those in the maker movement, the maker community, right? So we'll give some quick examples of training and things that could be improved through use of GNU Radio. Amateur radio exams evaluate students' understanding of radio at the block diagram level. And so you could use GNU Radio Companion for that to demonstrate, to develop and demonstrate working and non-working examples. Right? If you had the students use GRC to develop try to develop some receivers, other circuits, they would see what works, what doesn't. They would gain a block level understanding of radio systems. And you can replace analog focus with modern concepts. This is used courtesy of a group called Surrey Amateur Radio Communications, right? And this is some of their current training material, because the federal government sets the standards for examination, right? The training material has to reflect what's on the exam. But you see, it's a classic focus with analog approach. CW, single sideband receiver block diagram. High frequency oscillator, these things, this could be translated to a GNU radio flow graph, as we'll see. Modulation, demodulation, right? The examinations in most nations still refer to analog concepts, but it'd be better to bring people in, bring new students in, bring existing operators in to the digital era by talking about INQ and complex arithmetic and that kind of thing. Right? Part of the problem is people think, the people within the amateur radio community think this stuff is really, really hard. I would say it's not easy, it's different, but it's not, I learned it myself, it's not really, really hard. It's certainly not as hard as they think it is. And so there's reluctance, there's resistance within some amateur radio organizations for change, right? And so what's happening in Canada, it's a positive thing. There's the federal ministry, ISED, that's responsible. They're reviewing the exam material. They've asked representatives from major clubs, major amateur radio clubs across Canada to look at the question bank, suggest revisions. And one of the things that is happening is they're looking at putting DSP, SDR type of questions into the exam, because everybody realizes that this is happening. Now here's a quick analog reference. This is again from current training material. We're talking about filters, right? The filter following the mixer may be a mechanical, crystal, or ceramic filter, depending on the receiver. Okay, well that's a question on the exam. But it doesn't reflect modern technology, does it? Right? You want to have a SSB receiver that looks like that, right? And comment, it's Weaver method, and everything. It may not be the most efficient, but in any case, there's an SSB receiver. It's better to teach that than talk about things like this low-pass filter that's on the left, right? Coil 1 is 178.9 nanohenries, all that sort of stuff. Students, especially because students come from all walks of life, they don't have experience with that. That doesn't resonate with them, right? Let's give them low-pass filter on the right, right? Decimation 10, sample rate, cutoff frequency. Yeah. Well, when it comes down to it, right, I think we know ultimately radio is analog. It's an analog mode, right? But you want to hide that. I think it is, yeah, sure, we like it. Yeah. Oh, I yearn for the past. Oh, I yearn from the 70s. In any case, I actually took my amateur radio exam in tubes because it was in the period where the examination was translating from tubes to transistors. And so I had a choice, tubes or transistors, and I knew more about tubes because of the people who trained me. Right, they taught in tubes, and so anyway, vacuum tubes. But in any case, that's another story. Okay, training issues, exam format and content. We've talked about that. Instructors from the hobby, instructors in courses come from within the hobby. They have an analog focus because, like me, they were trained. Most of them are older. They're old guys, old people, and they were trained, trained in the analog era as well. It's because of their own training. They don't have, I don't think there's any bias or there's any negativity there. People train what they know. They haven't updated their skills, right? And I mentioned the perception that SDR's digital concepts are too complicated, right? You gotta realize it's it's different, but it's not really, really complicated. You can certainly learn enough of it to play around. One thing I considered, I thought programmatic approaches. I use, in addition to GNU Radio, I use Liquid DSP. Right? And so it's programmatic approach for solving these problems and building receivers, demodulators, modems, and that kind of thing. But I think that's a bad idea because most of the students coming into the courses, they don't have a programming background. And so that's an idea, right? But I think that would have to be, we'd have to, if we stick with the GUI like GRC desktop, there'd be far greater likelihood of positive uptake there. And so it isn't suitable for typical students, because they need coding background and generally they don't have that. So what's the path forward? I think it's important to preserve amateur radio because it continues to generate technological innovation even though it's at a lower rate. I think if amateurs became more aware, had more understanding of DSP, SDRs, which they could gain from from things like GNU Radio, then that would potentially generate more innovation in years to come. Right? Unmediated communication not dependent on commercial infrastructure may prove crucial in an emergency. Right? Don't want to lose amateur radio because we need those people dispersed within the community who are able to provide aid in time of emergency. And also diffusion of radio skills throughout society serves to increase technical literacy and provide recruiting function for industry academic programs. I think certainly, and one thing I noticed from the presentations, most people are hiring, right? And if you have it gives you a leg up in terms of having a chance for some sort of entry-level job in industry or applying to an engineering program, right? And so the amateur radio's training focus would be really, really nice if it can change to reflect modern digital technology. And key to that will be refocus of the instructor's role, the instructor's knowledge base as well. And so that is about it, but I thought that's about it. I'm, I guess, but I just wanted to have a couple more diagrams. These are from my thesis. I wrote my thesis in the, of a 5-year period ending in 2001 and everything. And this is just an interesting thing that I like to show when I talk about this. And this is a diagram from 1914. And there was an organization in the U.S. that was formed in the early 1900s. It's called the American Radio Relay League. And the idea was amateur radio could be used to pass messages by Morse code all across the United States, all across North America. And so in 1914, this guy named Hiram Percy Maxim, he and other amateurs developed this communications network, CW Morse code relay stations across the nation. So the diagram here is from a magazine called QST in 1916. It shows the trunks, it shows the lines, it shows the communication trunks that were used to pass messages coast to coast in those days. doing research for my thesis, I'm looking also at the early internet, see if there are any similarities. I came across this diagram, and this is, I can't see here, it's from 1980 or, anyway, it's a recent diagram, but it's the initial NSF net. And that really struck me, and I think it's fun to show that because everything old is new again. Things are reinvented, right? And I don't know how I go back on this thing. Oh, here's how I go back, but it just struck me the similarity. 1914 and 1970, 1980, or 1988 when that, with that diagram. So anyway, with that, I hope it was interesting. I hope it was, what I was trying to do was make a case for the preservation and modernization of amateur radio. And, I think it still has something to contribute, and, certainly, but I would say if the hobby is lost, right, then I think society will be at a loss, because it is important, right, to have this, it is important to, spread this, raise the level of general technological understanding among people other than us, right? So that is it for the presentation, and thank you very much. Thank you for the opportunity to present to the conference organizers and everything, and I'd be happy to answer any questions. Oh, thank you.
So before I open it up for a couple questions, we actually just got the last call for ham exams was announced. So if you are motivated, you have like a minute to go and go run over to the ham exam room. You can still do the exam. I think it's like 10 minutes or so to actually take it, right?
Yeah, it would depend. It's 50, I think it's 30 questions or 40 questions. The technician level, the entry level, I would say for anybody here, technologically, you'd probably have no trouble with it. The only challenge would be regulations and that kind of thing. And at this point, there's no penalty if you fail. So just yes. So say what sounds logical.
Yeah, if you don't study, there's some randomness, but might as well give it a shot. So yeah, but go now. They just announced last call. So we have time for 1 or 2 questions if anyone has any. Yep.
So thanks a lot for the interesting and exciting talk, and I agree with everything that you have said. I'd like to ask the question. So basically, you're trying to close the gap between the communicators and the technologists. So what about the gap between the technologists and the professionals? So clearly, there will still be a gap.
There will still be a gap.
So
absolutely.
what's your ideas or philosophy or your experience on how to close that gap, given that there will always be a gap, and what is the advantage of closing such a gap?
I think by closing the gap, you gain access to people. People may decide to go into engineering, go into industry, and be able to contribute. You maybe by closing that gap and increasing the level of technical understanding of those technologists, right? That ends up being a net gain for society, because it's a gain for education, it's a gain, a gain for academia, it's a gain for industry, and so I think yeah, there will always be a gap, especially these days, because of the exponential increase in technology over the last 10, 20 years in terms of SDR and, technology in general and everything, but it's better than letting it fade away, right? You get people closer. You get people closer to being able to contribute and do well in engineering programs and eventually contribute to industry.
Okay, thanks.
Time for one more question.
There's somebody over here.
Yeah, hi. I loved your presentation. Thank you. Look, I've used citizen band, but never amateur band in the 80s, and it was primarily used for communications, and I know amateur band was used the same way. But now amateur band is in competition with every other type of communications. It's no longer just a primary way to communicate. What's your opinion on how it can actually compete with the other communication technologies?
I think that really amateur radio. It's often a target of industry because amateur radio has allocated spectrum that is incredibly valuable to the telecommunications industries, right? And so the industry is, You know, and this was more of, I think it was more of a problem 20 years ago when I did the initial research, right? They depict amateurs, they're anachronistic, they don't make efficient use, they're not good, they don't, you know, we really need that because that can serve the community and everything. And so, but I think the fact of the matter is that amateur allocations are generally secondary in nature in the spectrum of interest, in VHF, UHF, and amateur radio has frequency allocations up to 47 gig. But they're usually secondary, right? There's a few primary allocations and that kind of thing. You know, but I think the amateur radio has to be able to defend itself and say, no, we provide good public service. We are a source of innovation. And it's a self-defeating, it's a self-fulfilling prophecy if you continue to you know, you accept that the technological capability amateur radio goes down, then amateurs have less of a case. They can't make a case as valid a case to say, no, we need to preserve these frequencies for those reasons. But I think it's a long answer, but I think also government makes lots and lots of revenue through spectrum auctions, and amateur radio, you know, they may be less supportive of amateur radio than they should be. Let me put it that way. For that reason, because they are short-sighted. They forget that amateur radio is a source of, you know, it has those benefits, right? Those benefits of advancing the state of the radio art and supporting, you know, diffuse communicative ability, you know, through society in the event of emergency or, for example, time of war, right? Source of technologists.
Let's thank Kevin one more time.
Okay. Thank you very much, everybody.
Next up, we have Robin from MathWorks. As well as John.
Here's the clicker. It was here first, right? Oh, the clicker won't work on my laptop. There we go.
Yeah, okay, thank you. I'm John Kraft, I work for Analog Devices. I'm joined by Robin Getz at MathWorks. And we're going to talk about general purpose phased array learning kit and give you kind of a cool example of null steering and its impact on signal quality as measured by EVM. So in this presentation, we're going to go real quickly through kind of some phased array principles, some common topologies for phased arrays. But then we're going to build a model of a phased array antenna, and we're going to use that model and compare it against actual measured hardware to see where the imperfections are and how close we get and those kinds of things. We'll look at some concepts like beam tapering. We'll apply a taper and see, does that tapering profile between simulation and the measured data, does that match? And then we're going to conclude with, I think, kind of a really cool demo on, or some results from null steering. So this is the idea where we have a jammer or an interferer, and in addition to pointing the beam in a certain direction, we can also point nulls in a certain direction to cancel out sources of noise and interference. So, I mean, obviously RF spectrum is a valuable resource, and we just heard about how people are fighting over the amateur radio bands and stuff and how they want that. And so we've had different ways to traditionally divide up this resource and make efficient use of it. A couple of common ones, like dividing it up into frequency bands where we have a certain uplink frequency and a downlink frequency, so we can communicate simultaneously but on two different frequencies. We can also divide things up with time. So we're transmitting at a certain time, we're receiving at a certain time, and so we talk and listen generally at the same frequency. But phased array systems now give us this other degree of freedom, which is spatial separation. So we can talk and listen to just a specific device or region and reject other regions. And so we can combine all of these things together in new and kind of cool, interesting ways by pointing our beam in one direction if we want to talk to a certain device or a certain area, but then also pointing nulls or doing like adaptive beamforming where we shape the beam in such a way that we maximize the signal to noise ratio with the device that we want to talk to, and rejecting clutter and noise, jammers, interference in other spatial directions. So it's a very cool combination of things that we can do now. So we can, again, point in other directions, and we can switch these things basically instantaneously. It's a very nice advantage. I mean, it's a great advantage to the phased array topology. You couldn't do that with a mechanical rotating antenna. You couldn't switch it instantaneously. There's inertia there. There's reliability issues with the motor and stuff like that. But with a phased array system, I mean, in microseconds or less, we can switch that beam and even have multiple beams going on. So we can talk to multiple targets at the same time or track multiple things with a radar system. And use those antennas, the diverse array of antennas in different ways to do things like null steering and adaptive beamforming to shape our beam pattern in real time with the data that we're collecting. So real quickly, phased array systems have been around for a long, long time. Maybe it's got to be close to 100 years, if not more than that, from the very first kind of conceptual demonstration of this. But increasingly in recent years, they're finding homes in areas like different kind of radar systems, automotive and aerospace and defense radars, wireless communications like 5G, MIMO, millimeter wave beamforming, satellite communications, especially the LEO satellites that operate close to the Earth's surface, so they zoom across the sky pretty rapidly, and so in the phased array system, you can track multiple of these satellites and communicate with them, and then different acoustical arrays.
And in the satellite systems, the phased array is not only in the satellite; it's also on the ground station.
Yeah, for the pointing things
Right,
around.
yeah.
Yeah. So, kind of primarily, there's sort of the three topologies of these beamforming systems. There's analog beamforming, and in analog beamforming, this is probably what most systems are or have been historically. And in analog beamforming, we do our beam weights, we do our delays and our gain adjustments in the RF realm. So at some frequency, doesn't have to be the frequency of the signal, but at some frequency, we shift things in phase or time delay and an amplitude for each of the individual elements. Then we sum them together into one ADC receiver or into one transmitter. And so this has been, like I said, kind of historically how most array systems have been. It's generally the lowest complexity, it's the lowest cost generally, and the lowest power utilization. But you only get one beam. Kind of the other way to do this, or the exact sort of maybe opposite way to do this, is digital beamforming. Digital beamforming, we're going to digitize all of the RF spigots from each of the different antennas, and then digitally we're going to adjust the gain and the phase of each of those different streams. And this is very cool. You can do a lot of cool things in digital beamforming, like decide where you want to point the beam after you gather all of the data. So you can pull all the data in, and then you can say, okay, now I want to point the beam in this kind of a pattern so that I optimize my signal to noise ratio, so that I'm getting I'm nulling out interferers, and I'm forming the beam in such a way that sources of noise don't sum into the signal of interest that I'm trying to track. But this digital beamforming requires a data converter on every antenna element, and so it generally is higher power, higher cost, and it's a lot of data to deal with and to process and to move around. And so right now we really see a lot of activity in what we call hybrid beamforming, where we divide up the array into subarrays, and then we digitize each of the subarrays. And this allows us to kind of share some of the benefits of digital beamforming, but also some of the benefits of analog beamforming in terms of cost and complexity. And so with hybrid beamforming, we can apply delays in the analog realm. We sum those together, and then we digitize, and then we can further split things up and to do things like monopulse tracking in the digital realm. And so that's what this little hardware board is. If you've stopped by the Analog Devices booth, maybe you've seen this. This is our little phaser X-band phased array prototyping and development kit that we have. And it's composed of a receive antenna array and some analog beamformers in the front, and then those analog beamformers get summed together into two digital channels on this Pluto on the back, and then it's all controlled via this Raspberry Pi on this side here. So we have effectively 8 linearly spaced elements across this array, and we do the analog beamforming in this 8R1000. They get mixed down with this mixer here and to each receive port that goes over to the Pluto. And then also we have for the LO on all the mixers, and there's a transmit path as well. So there's one transmit output. All 3 of those mixers share the same LO, and that LO you can program it to chirp, so you can develop like a 500 megahertz chirp bandwidth. And this is some kinds of chirps that you can program in with just a couple of SPI rights. You can do various kinds of sawtooth and triangle chirps. This is for radar FMCW processing. And here's kind of a close-up of what those mixers look like. That LO gets distributed to all 3 of the mixers, so we do something called stretch LO processing, which allows us to have a 500 megahertz wide chirp, so very wide bandwidth chirp that gives us great radar resolution, but we only have to digitize the beat frequency. So essentially these frequencies get subtracted with the RX and TX mixers. So our beat frequency is less than 20 megahertz, so it's within the instantaneous bandwidth of Pluto. So we can use this little Pluto device. And maybe you guys have seen our little Pluto software-defined radio. It comes in 2 varieties. The older version had one channel transmit, one channel receive. And then this newer version, if you have a Rev C or Rev D and you crack it open, inside will be little U.FL connectors that will allow you to pin out that second channel for transmit and receive. The 2 transmit channels are phase synchronous, and the 2 receive channels are phase synchronous. So you can do the hybrid beamforming or some simple digital beamforming with a 2-channel array. So that's what we use. We just grab that Pluto, shuck it, and bolt it onto the back of this phaser board. And then what we're going to use for this little jammer, this interference source here when we do the null steering, is this little HB100. This is kind of a cool little guy. What is it, $1? $1.88. Yeah, it's this little guy that they use at like whenever a door opens for you automatically. It's probably one of these little HB100s. They operate at about 10.525 gigahertz, but I mean, I've probably measured over 100 of these devices, and
not one has been the same.
Not one has, nor has it been 10.525 gigahertz.
Yeah.
You know, like, yeah, they're not the same. They could be anywhere from 10.1 to 10.7 gigahertz. So kind of goes back to that frequency division that we talked about earlier. Anyway,
well, so that's actually great for those educators because you can actually do large classroom setups and nobody interferes with each other because they are actually unique frequencies.
Yeah, we've done workshops where we had 15 of these phaser setups going all at the same time, and nobody sees anybody else because we're separated on enough frequency. Okay, so that's kind of the overview as well as the hardware that we're going to use. And now I'm going to turn it over to Robin.
Yeah, sure. Thanks a lot, John. So, you know, I think when people talk about phase array challenges, you just like designing the array, doing mutual coupling, trying to understand what that is. Like when you're doing your hybrid beamforming, what's your analog summation versus your digital summation? Do you really need to have elements that are digitally controlled that are side by side? How much coupling are you going to get from each? What's the signal processing, the interference mitigation, calibration, and not just calibration from a PCB standpoint, but these phase array systems are incredibly expensive. And so if you have a bad element on a board that's incredibly expensive, you ship it anyway and calibrate, you know, let that problem be the DSP guy's problem. And that's what happens. The system level calibration is like super important. And you know, the waveform design. So all of these things kind of like John was talking about in his presentation yesterday, you know, it's RF and antenna design, system engineering, digital hardware design, signal processing, algorithmic design, not only from a waveform design, but now you actually have to add a little bit of extra math for your phase array pieces, and that's software, firmware, HDL. And, you know, I think we wanted to try and establish a common design language, common framework. So, you know, creating algorithm and device models, simulating those pieces, seeing how they react in the simulated world, and then actually validating with hardware. And that's kind of what we'll be talking about in the rest of the presentation. And when we talk about this at MathWorks, we kind of talk about a model-based design where we talk about trying to, define what the problem is, simulate the problem, implement the problem, see it work, and then integrate all the pieces together, make it form factor, and then ship it. Because there's got to be some economic value of doing all these things. It can't just be writing papers, unless you're an academic, which is totally fine. But you have to understand, even when you're an academic, people are paying you to go to school, paying you, you're always asking for research grants, and those people that you're asking money for need to have some economic value out of what you're doing. So sometimes it's about what you're doing and who's going to take that output, what format do they need it in. And so, like John said, the challenge was take the phase array system and see how it can improve a real-world communications example with null steering. And so in this research phase, what I did is I looked around at existing examples, and there's an example called like LTE receiver using software-defined radio, where it captures LTE signals off the air from a base station and then decodes them and shows EVM and does these kinds of things, which would be great. I could have used this, but it makes it problematic in terms of every time I move from my home to my office to a hotel room last night trying to figure things out, it all changes. So you look around for a different example, and it's like, okay, well, in this example, it takes an image, it creates that LTE signal, it actually transmits that out of Pluto, which is great, because that's what's on the back of the phaser, and then it decodes that and gives me an EVM measurement. So that's kind of the example I decided to use. So we actually take an image, which is this photograph, we encode it, we get some samples, we transmit and receive it over the radio, we decode it, we get some EVM measurements, which is that physical layer metric, because what you want to make sure you're doing is having some quantitative, some qualitative measurements, and then making sure things are correct. So we can look at that both in terms of simulation and no impairments, and look at our EVM. When you have simulation and no impairments, EVM better be pretty good. And then we can also see, Pluto with just a cabled across, and you can see there's some impairments, some EVM. EVM is about 0.8, which is pretty good. And then we can kind of go from there. So like from a wire to an antenna, because the Pluto is, if you just attach two antennas, you really only have a 2-centimeter channel, which is not super interesting. So then you put some cables on, you separate things out, and you realize like, oh, maybe 64 QAM isn't going to work very well over a meter. And then you say, okay, well, I'll do QPSK, and then QPSK actually works pretty well. And then so you kind of like incrementally go along from your QPSK at 1 meter, and this was transmitting at 2.2 gig, and say, okay, well, how is it going to really work at 6 gig, where the radio may not work as well, or the cables may not work as well. And this was using a dipole antenna, and switching the antennas around even to this antenna that's actually included in the phaser kit, which is a Vivaldi, so you're pointing most of the energy at the right place and receiving it in a certain direction, actually makes the EVM much better. So, I thought this was a pretty good example to use, and using this example on the phaser kit, just ported it over, it took about an hour. So on the phaser receive path, when you look at the data sheets for these devices that are on the phaser, there is no specification for channel-to-channel match. There is no specification on the LNAs for device-to-device match. And there is no specification on the PCB coming back from the PCB manufacturer, like how well they actually manufactured it, what the tolerances are, to understand what the calibration issues of the PCB are. So, and the answer they don't have these is because it doesn't matter. Even if they gave you a spec, it would just cost them test time and cost complexity, and it really doesn't do any good because you have to calibrate them anyway because there's so many other things in the system that are variable. Most of the things in the system that are variable are one-time manufacturing pieces. So, analog devices could test this, calibrate it at final test, put the calibration pieces in the device itself, and then everybody would get this pre-calibrated. But that wouldn't be a lot of fun. So they let everybody kind of solve these problems themselves, which is great because calibration is a super interesting topic that a lot of people are actually doing research on. And so we can actually see In free space, when you calibrate things, it actually does match when you can see the uncalibrated versus calibrated versus the theoretical, and the calibrated and theoretical actually match pretty well. You can see that on the hardware versus the theoretical, it kind of looks like sawtooths everywhere. Does anybody know where that's actually from? Oh, John, you know where it's from. Does anybody have any ideas? So in the real world, in the real hardware, we implement things in fixed point. It's a 5-bit phase shifter. In the simulation, we simulate everything in floating point. You have an infinite precision phase shift. So we get nice smooth curves and these kinds of things. But in reality, 5 bits you can actually see just on the plot. And then you look at things like the antenna design. So we actually measure array factor, not array pattern, which is a super subtle but very different kind of thing when we're doing this. For those people who are super deep into phase array, this is like a super important point to make. And if you're not into phase array, you'll learn about this kind of like later. But your antenna pattern is kind of like this array factor. And so depending upon what you're doing, you can have like uniform rectangular arrays, circular arrays, custom arrays, linear arrays. And we actually treat this device as a linear array. So these columns are tied together with Wilkerson combiners on the back of the board. So from a signal processing perspective, it's just a single element. And then these 4 get added together to increase sensitivity. So that's what we do. And we can actually see here, when we do that and measure it, we get this array factor to get our array pattern. And we can see it actually matches pretty well with the pure simulation pieces. But we can see from here that the side lobes are directional pieces. It's really only maybe 12 dB down. And that's not super exciting. That's a lot of work to go through to get 12 dB a gain. So we actually can use some classical signal processing techniques that everybody kind of understands based on windowing functions. So, you know, that 12 dB down comes from just a boxcar window because that's what we had things set up as. So meaning that the array across here is set to the same values. When we can set them to different values based on a windowing function or tapering function. So this is always one of my pet peeves, is that every different discipline has to rename something that somebody else already figured out. So in phase array, it's a tapering function. Signal processing, it's a windowing function. It's exactly the same thing. But you don't think of a windowing function being applied to physical things, which is what we're doing here. But when we start doing that, we can actually see the side lobes going down and see the signal processing benefit of actually doing these phase array pieces. And we can actually get the same benefit by actually spacing out and using a different antenna pattern. So you can see that just from the antenna pattern, we can actually get signal processing benefits. Now, the penalty you pay is the antenna size. So it goes from like 8 lambda to like 60 lambda. But your beam becomes much narrower, and your, that may be what you want, and maybe you can afford to do it because you have a giant array. Lots of people will actually do like the Hamming thin mate system, where they will actually have patches on the antenna, so everything looks like a uniform array, but they won't actually tell you which ones are actually connected. So it actually makes it much harder to reverse engineer as well. And then we can kind of see the tapering example. And here, my side lobes are down about minus 25 dB, minus 24 dB. And now it's starting to get a little bit difference between the theory and the simulation and the actual hardware, just from the inconsistency of the hardware. And when I put them together, you can kind of see the Hamming window versus the boxcar. The side lobes go down, but the beam gets a little wider, just like FFT windowing functions. So it's the same kind of classic things. And I can actually move that beam back and forth, and you can see that everything moves, all the side lobes, all the nulls. And in this case, since we had an interfere, since we had our array, our HB 100 off to the side at a 25-degree angle or 30-degree angle, what we want to make sure we can do is point the beam any direction we want and keep a null exactly where this thing is. And we can actually do that through other signal processing, called null steering. And what that null steering gives us is we can cancel out that interfere while we point our beam at our signal, and that signal can actually move. So that's what we kind of have here. We have our LTE signal coming out of our Pluto, going up the out converter, out from an antenna, pointing at the device. We have our interfere over here, and we have the interfere was 25 degrees off. So you can see there is a null. Let me just turn the pointer. There is a null here at this 25-degree piece, and that adding the null to 25 degrees is not free. It does actually shift the main beam over a little bit, becomes a little less sensitive, makes it a little wider, makes this side lobe a lot higher. So it's not there's not a it doesn't immediately fix everything like in any DSP kind of technique. There's always some trade-offs. But what it does do is if we had no null steering turned on, we would get an EVM when we're doing our test of bit error rates of 40%, which is meaning that we're not going to decode the picture properly. When we turn the null steering on and point the null at the place the interfere was, we get an EVM of about 5%, so we can decode the picture fine. So we can actually prove that we do have that spatial sharing that we weren't able to accomplish before without some kind of without the phase array system. So the conclusion is it works. Simulation matches with the real world, which is always good. We tested it over the air, which is also good. And all the code is up on either GitHub or on the Analog Devices Wiki for those people who want to try things out. And for more information, there's actually Brian Douglas. He actually did another a set of seminars or set of videos on phase array that are excellent. For those people who like to watch science videos and these kinds of things, I'd highly encourage anybody to go see them. I think even John. Yeah. But, thanks very much. If anybody has any questions for John or myself, I'm sure Mark would like to run around the room and get his exercise. Yeah. Thanks. Here's this one. John, do you want to come up?
Questions?
So you mentioned about the precision issue in one of the diagrams where you had the difference between the measured and the simulation because of the precision floating point. And so later on in one of the figures, this kind of difference between the measured and the simulation kind of disappeared. Was this by coincidence that the values that you put in simulation matches the 5-digit precision?
Well, so sometimes they're smooth and sometimes they're jagged, and it's really the 5-bit pieces that. So part of the other issue with the analog phase array that's on phaser is not exactly. You don't get independent control of gain and phase. So it depends which way you're actually pointing the beam. It can actually negatively affect gain or negatively affect phase, which can also cause inconsistencies, I guess. So there's all the knobs are very interrelated. You turn gain one way and phase changes. If you change phase, then you have to go back. So calibrating is a big challenge. And
So,
it's yeah.
Yeah, I mean, I don't know if that's, so the jagginess in those pictures, I don't know that it's from, because it's actually a 7-bit phase shifter, so it's actually really good. We don't really suffer from, let's say, like quantization side lobes. I think what it is, though, and it's kind of related to this, and you see if this sounds right, is it's only an 8-element array. And so with an 8-element array, when you space your delays in a certain way, it means like if you wanted to steer to, say, 13.2 degrees, that's where you want to point your beam, your beam steps are such that two of those elements may actually have the same delay time, same phase delay. And so it's not as perfect as if each element was actually a multiple of 2 to the 7th phase shift, like a 2.87, 2.8 degree phase shift, right? Two of them are going to have the same. In a large array, that all gets averaged out, and so it's very smooth. But in only an 8-element array, if you try to steer towards places kind of in between where those phase steps want to be, then you get something that's a little bit off. You can think of it like a 80C kind of kind of a step error.
No, that makes sense.
And so I think that's kind of what you're getting at. I think it's more though from the smallness of the array that's 8 elements than anything with the phase shifter.
Yeah. So an 8-element array is excellent for like understanding the basics. It's a great learning kit, but it's not really meant as a production deployment to track airplanes or.
Yeah, and it's really cool. And starting with a linear array too is one of those things where it's great foundationally because all the math for a linear array is much more straightforward.
Yeah.
And if you want to go to 2-dimensional array, it's the same, but it's like a nested loop, in 2 dimensions. So it's nice just to focus on the linear array and the fundamentals there. But yeah, in a real world, yeah, you'd want a 2-dimensional array and you'd want a larger array. Yeah.
Any other questions? I got a quick one while I'm walking. So you mentioned the amplitude and the magnitude and phase are sort of related. You can't change one without messing with the other one, but is there a way to maybe model that and sort of overcome it?
There is, yes.
So I mean, and that's not totally true
No,
either.
it's an IQ mixer inside. You can't change phase without changing gain.
No,
Sorry, man.
There is an IQ mixer, and that is how we control the phase. You could also control the gain that way, but that's not how we do it. There's a separate attenuator block that actually controls the gain. So we have some customers who get very clever with that IQ mixer, and they use it to control both gain and phase. And doing that, you can do really cool things. But in the general case is you keep the IQ mixer the same, so it only rotates phase, and then separately than that, you have like a 20 or 30 dB attenuation block that you can slip in. That's like 7 bits.
Okay, that makes sense. Yep.
I was just curious how you did the calibration or what the general process for that was.
So calibration, there's definitely, so we calibrate, on this device, we basically have a reference channel, which is like channel 1, and then you turn off the, channels 3 and 4 and try and actually null out 1 and 2. And then you're trying to actually go to a local minima in terms of where they cancel out each other so that you know they're 180 degrees out of phase. And then you go actually from channel 1 to channel 3 and from channel 1 to channel 4, and so that you try and minimize the error across the array.
Like with against a known source, or you're saying from
With a known source. So typically
Okay.
what we do is we'll take the HB100 and put it out front and hit calibrate.
Ah.
And so in like a real production system, people will actually add extra transmitters and extra receivers on here for calibration. But that would complicate things and make things more expensive and that kind of an idea. So HB100, $1.88 seems like the right solution.
Very good. Thank you.
Yep.
Any other questions?
Let me I just kind of remembered one other thing. MathWorks and Analog Devices are kind of co-sponsoring a competition for the IEEE Radar Conference in May of next year. It's going to be announced on that website probably the next week or so. So if you're like in universities especially, and you want to form a team to do some of these phased array radar kinds of principles, we're going to this submittal for abstracts is coming up. You can submit an abstract with your team, and then if the committee selects you, we'll send you one of these phased array kits that you can have for the year. If you present at the IEEE Radar Conference, and you keep the kit for your university and for future development or whatever you want. So if you're in the university kind of realm or want to do some research in this and you want to know how to get your hands on one of these for free, the IEEE Radar Conference is a great way to do it.
Which is going to be in Denver next.
It's in Denver next year, and we're doing that with MathWorks. So.
Yep.
Very cool. You know, the Pluto was also made for education, but people have done some crazy stuff with those.
Yeah.
So I really look forward to seeing what folks do with the phaser over the next several years. All right. Well, thank you very much.
Thanks a lot.
Thank you.
All right, so that is all we have for talks today. Want to do one last announcement here about our evening social. It is at the Arizona Heritage Center. It's about, I think it's like 3 miles away or so, but it's very hot. Don't try walking it. Apparently there's a bus. You can get there. I have not ridden the bus. I don't know how that works, but you know, get people together, grab Ubers if you want to try the public transportation. But it should be a good time, 6 o'clock. Hope to see everybody there. So, all right, have a good evening. We'll see you guys over there.